networking You are currently the only person in this conference. You are currently the only person in this conference. You are currently the only person in this conference. You are currently the only person in this conference.
limitations of the ioctl interfaces and the fact that we were using fixed format C structures to pass arguments into the kernel calls. And Netlink, I think it might have been inspired by IPv6 extension headers, or I don't know, maybe XML a little bit, because it was created in a similar time frame. It basically allows to be more flexible about which fields are basically present in a system call. So you can, it looks like an IPv6 extension headers for those who are familiar with that, but it's also possibly slightly similar to an XML where basically the structure is defined, but the contents are up to the user. Unlike an XML document, though, Netlink is a binary format, so it's not self-describing. Every member of every attribute in Netlink is turned into a C structure effectively. So the information about like the meaning of the fields is kind of lost when it's translated into the binary format. Every attribute is a TLV structure, so it has a type, it has a length, and then it has data. The type is defined inside an enum, so the binary message that goes into the kernel just has an integer ID, and you have to know basically which enum the ID is taken from to interpret what is there. The length is fairly obvious, and the data is, again, requires some prior knowledge because there's no information inside the Netlink message that would tell you how to interpret the data. You have to know whether it's a string or an integer or whatever else. And one thing that I haven't mentioned yet is that one of the strengths of Netlink is that you can nest attributes. So you can have a structure within the structure, and it can be variable size. There's no problem. Basically, you can do nesting and create sub-attributes. And the last bit of information that's like listed on the left side is the command itself, which goes into a fixed format Netlink header, and there's other fields there. But that's basically the message structure. I hope it provides sufficient clarity for the purpose of this talk. There's three basic message exchanges between the user and the kernel in Netlink. The most simple one is the user space sends a request, the kernel responds with either an ACK or an error. The second communication pattern is a notification. So we can have a user which registers for notifications, user one in this example, and when another user makes a change or an event happens asynchronously in the physical world, like someone unplugs the cable, the user which registers for the notifications will get notifications about something changing in the state of the system, which allows basically an efficient way of waiting for events and monitoring for things happening in the system and maintaining a copy inside the user space of the state that's in the kernel without like polling for changes. And the last message exchange pattern is a dump, which allows the user space to basically get information about all the objects that the kernel knows about. So the user makes a request to get some object information, sets the dump flag in the request, and then right here. And then the kernel, instead of sending a single response, will send multiple responses, basically listing all the objects that it knows about. And at the end, it sends a done message to delineate that that's the end of the dump. So that's pretty much it. I wish that was all there was to say about Netlink. Unfortunately, you know, everybody has their own ways of tweaking things. A few things that I'll mention just briefly that make Netlink relevant still and interesting, I think, is I think it solves all of the problems that people complain about UAPIs in general. So it gives people the ability to do introspection. There's no need to probe for features. Netlink can basically tell you which commands the kernel supports, which attributes it understands, like which ranges the attributes can take, and a lot of things. So there's no need for probing, basically. It can support error reporting, both in a machine-readable form where it like basically points at an attribute and said, this attribute was wrong or this attribute was missing, or you can just send like a message string that says what was wrong in English. Another thing that most people are not aware of, and I wasn't aware of, to be honest, until I started this project. Netlink can maintain local objects that are local to the socket. So you can create some objects in the kernel using your Netlink socket that you opened. And when you close the Netlink socket, those objects will be torn down automatically. So the wireless folks make use of that. I wasn't aware that that's the case, but it's actually there. And the last one is that we usually do communication between user space and the kernel, but it's also possible for the kernel to call the user space if things are set up properly. So yeah, there's a lot of flexibility and a lot of advanced capabilities are there. So now to the main point of the talk. Why are we talking about YAML and what I'm trying to fix by use of YAML? And I mean, I don't have it in the slides, but the short version of it is I'm not capable of writing user space code. At least I'm not capable in covering all the languages that people want to use. So I'm trying to find a way of basically making it possible for people to use Netlink with whatever language they feel like on the day, without me having to write a library for them that will parse all the attributes and do all the manual work in Netlink. So right now, when you write user space, we usually write the kernel side, and then we write some user space tooling like a CLI, usually ipv4. And that's the extent of like what the kernel developers do. But obviously, users may want to call the kernel directly instead of shelling out to a CLI. And our story about how to discover the Netlink protocols is pretty bad. It usually ends up being like reading the kernel code and figuring out what the kernel understands instead of having a documentation. Like I think ethtool is the only Netlink family that I'm familiar with that has a proper documentation that lists all the attributes and all the things that are possible to do. And everything else you have to read the code. So the YAML specification is supposed to fill in the gaps and describe the protocol between the user space and the kernel to make it possible to basically make Netlink serializable and deserializable for any language, any modern programming language. So if you ever worked with like JSON or a YAML file in something like Python or Go, you just load the file, and then the file that you loaded gets translated into like the typical structures and typical types for the language. And for Netlink, we have to do all of that manually. So the point is, if we have an external description that specifies what the kernel is sending, we can basically do this serialization and deserialization automatically. So this example is for the getlink and setlink command that I was showing in the previous slides. We specify the operations and the attribute sets. This is obviously a single specification. I broke it up for the slide. We specify the name of the commands and then basically what attributes they take. And then we define all the attributes that the messages can contain. And the important bits of information here is the name, because Netlink binary representation does not have any information about the names. And if we want to translate the message into something that the user, the programmer can interact with, like a dictionary in Python, we need to be able to name the fields. Then we have the type, so we know how to deserialize the value. And if for nested values, we also have basically a link to the attribute space, which will be nested within that value. So basically, we can do chaining of the attribute lists. So if we have a YAML description like that and a generic Netlink library that just understands YAML descriptions, does not understand any specifics of the family, we can write Python code like I have here on the left, right? So it's almost an exact example from what I had in the RFC patches that I posted. We have a YAML Netlink implementation here, the YNL library, which is generic and doesn't know anything about any of the families. We just give it the YAML description of a family, and then we can make a call and specify the attributes like you would normally for an RPC call in Python. So just a dictionary of fields, with fields. Extra details on the YAML specification. So obviously for setting, we only have the request. The reply is pass-fail, basically. For getlink and other commands, there might be attributes going in both directions. So we have a section for the do command, and then there's attributes for the request and the attributes for the reply. And similarly, there's a dump, because the commands usually can do both. The get commands can usually serve both as a get and as a get dump. There's two sections for a get command. There's a do section, which is used when the dump flag is not set, and there's a dump section. Dumps often do not take any attributes on the input, so there's often only output. Another thing that we have to provide in the spec is the IDs. So we want to be able to use this from languages that are not able to include C UAPI headers. So we need to be able to enumerate exactly, for instance, that the netdev attribute has the value of 1. So the way I implemented it, the enumeration between the attributes listed in the specification and the integer IDs is the same as for a C enumeration, right? So the first one will be 0, the second one will be 1, and so forth. But if we have to override it, we can specify the optional value property, and it will give that value to the current attribute, and then the next one will be +1, and so forth, like it would be in a C enum. We can do that for attributes and for operations. So yeah, that's the value basically that goes into the type element. And one more thing is when we specify the interface between the kernel and the user space, there's often enums or flag fields and information that we really want to be able to translate into a string representation, as well as the attribute names themselves. So there's a section for definitions in the spec. This is an example taken from the DPLL work, where you have a status of a DPLL, and the value inside the netlink message will be an integer representation of this enum, but in the code, we probably want to use like the string names. So the YAML spec also contains definitions of enumerations and flags. So flags name bits, so 1, 2, 4, 8, 16, etc. And enums are enumerated 0, 1, 2, 3. And that's the difference between the two. And then we can link that in the attributes and the YAML specification. Basically, that's how the YAML specification expresses that a given field can use those string representations. And last thing is, because we want to generate kernel code, so we don't have to write both the YAML specification and the policy inside the kernel, there's extra fields that are like basically kernel use only. Flags for the operations, example, admin only, which means you need to be basically administrator to run the command. And checks, which is what we use in the policies for range checking of the attributes. I have an example of min-max, but we also have mask checks, etc., for the policies in the kernel. So with that YAML specification, we can generate the UAPI header automatically so that the user doesn't have to write all the information in two places. We can generate the operation table automatically for the kernel and the policy tables, and hopefully documentation, and then require people to actually write documentation. And on the user space side, obviously it gives us the ability to automatically serialize and deserialize, and whatever that means for a language. For a modern language, it will probably mean some dynamic typing, hopefully, and dictionaries and stuff. For a less modern language, like C, you can just generate a parser and like format the messages into C structs. One more word on the error handling. So I said that netlink can report errors in both a string format and basically pointing at an attribute and saying that the attribute was wrong. It's all great in theory, but currently we actually don't make much use of the point at an attribute and say that it was wrong, because the user space does not have a full attribute table, and it does not know how to translate the message that it sent itself back into the attribute ID. Like when you type a command in IP route, it will go through all the arguments and basically put attributes into the buffer, but it is not able to go back and like link up what the exact attribute was and what it meant. But if we have the YAML specification, we can map the IDs back to names, meaning we can figure out, basically when the kernel tells us this argument was wrong, we can figure out what this attribute was. Basically, based on the ID, we can get the string name and go inside, figure out based on the ID of this attribute what it was, and print it to the user. As I already mentioned, Netlink is slightly more complicated than I wish it was. So I have levels of API specified. So for the new families, I hope we can basically stick to what I presented in this presentation, and that will be it. That's basically the entire spec. But people have found various inventive ways to make use of Netlink, and to be able to describe those families with YAML, we'll have to get another type of YAML specification that will be a superset of what we have here with some extra attributes that will basically account for the weirdness. And for Netlink, the classical Netlink that is used to configure the IP and routing stack, we need yet another layer of complication because it's not generic Netlink based. In terms of progress, I have the code. I posted, I think, 2 RFCs. It covers the new families, obviously, because I can nudge them into fitting into this paradigm. It covers foo pretty well. It can be used with ethtool and devlink, although they do fall into the legacy category, unfortunately. But they don't need too many quirks. And I have talked to, I think, the PyRoute maintainer, and he seems to be on board. So hopefully the Python support will land soon as well. That's it. That's all my slides.
So you mentioned quirks. Can you briefly give an overview of how bad those quirks would need to be?
So there's, I have a list of them in the documentation. The 3 that immediately come to mind is the older families make use of fixed format structures. So you would not have an attribute for an integer and an attribute for a string. You would have an attribute for a structure. So you need to also support like basically formatting structures. So you can put in the YAML spec basically, a description of a C structure, and then that will be the value in the attribute instead of it being a single member. There's also like magic use of the flags in Netlink. There's flags defined for like create, append, and stuff. And there's like a couple of families that make use of those flags, even though they seem like an idea that someone once had, but they don't really make much sense. And then a lot of families also use different enumeration for things going to the kernel and from the kernel for some reason. So yeah.
So a comment, not a question. I mean, I really like this idea. I work on systemd, and we have this as the Netlink library for formatting of messages. And it has been like an internal thing, but we are just working on making it public. And I think this could be useful as a basis for user space. And I would love to generate our code that writes the Netlink messages this way.
What language do you have it in C?
In C.
Right.
This is awesome. I think we talked offline. The biggest problem with all this is the name, right? Netlink.
Well, you have suggestions?
Netlink. So what if we go one step further, right? We do kernel link. We keep sockets in Netlink, but we do new, let's say, syscall, where the data is passed like through the memory. We keep the TLV, all the schema stuff, but it will be just like a syscall, like we have in Bpf, right? But this format will be flexible, extensible, and maybe will not depend on networking, and maybe core systems will use it instead of ioctl.
I mean, I don't. Yeah, maybe. So you mean like don't use a socket at all?
Yeah. Why do you need a socket? It's just like you need just a chunk of memory where you can marshal and marshal the stuff, right?
Yeah.
Technically.
Yeah, I mean, it's, I don't have the need for that, to be honest. I mean, it would be good for people adopting it outside of networking, but for the use cases that I have, when I want to convince people to use Netlink,
You need the file descriptor for the purposes of context. So for example, when you're doing a dump, you have to remember where you left off before you finish.
Can I just dump everything into a huge chunk of
You don't
memory?
have infinite memory to dump.
yeah.
You have to do it piecemeal.
Yeah, you need a file descriptor.
You need something,
yeah.
something.
Okay, but maybe that, again, maybe that's something that's networking specific and we need huge dumps. Maybe some people just need like small pieces of data back and forth.
I mean, if you have file descriptor, you can still do multiple
Oh, yeah.
reads, right?
I had a question, which is, you mentioned generating kernel code from the description. How much would be generated / how would that work?
So I was hoping that it would generate the parsers and a lot of the manual looking at attributes inside the kernel as well automatically. But people have found very amazing ways of writing that code. So at the existing, when I looked at the existing families, there is no single family where I can simply like take a manual parser out and put an automatic parser in. Everything is really like all over the place. So I can only generate the tables that the kernel already has. So the policy table, the operation table, and the UAPI header. But like the parsers are really hard to replace.
So a bit smaller scope of what was suggested over there would make sense to re-implement all the quirky bits in terms of GE Netlink with a view to retiring the old Netlink in a decade or two. It's like if you're automatically generating it, just having an automatically generated translation bit would be fairly straightforward, I guess.
Yeah, we could do a translator basically that would take GE Netlink and turn it into a Netlink route. Dave has a comment.
So we could say that any new Netlink family or GE Netlink family should use the YAML format to generate.
Right. I think Talk wants to get like being able to set an XTP on a link. You still need to go to the very old Netlink families, even though it's a new feature. So it would be good if we can do like modern things over modern interfaces, right?
Yeah, and also just like so that you get the automatic compatibility with GE Netlink, so that eventually we can have one nicely designed format instead of all the old quirky bits. And if we have automatic generation, we could, if the kernel could maintain a compatibility layer so that new user space tools only need to know how to speak GE Netlink and not the old Netlink.
Yeah, that's a good idea. An intern project for next year. Okay.
Very quick question, which is, what is the plan for making sure that that this description and the actual implementation stay up to date together? Basically, like, is there do you have a plan for like, I don't know, whatever, like a CI check to make sure that it actually the description that like if you add a new feature, the description is not missing?
So if we generate the policy table, you will not be able to use any attribute that you edit inside the kernel unless you update the YAML, because there will not be, it will be rejected by the kernel. On the output, yeah, we will need to catch it in review.
You could even use the YAML to automatically generate test cases.
Yeah. Oh, someone, I think Ido mentioned that we should talk to the Sysbot people so that they can learn how to fuzz Netlink better over using this, yeah.
Missed it. So as a potential Netlink library author, how does this help me? Like, what does the flow look like? Because I guess I still need to know like the binary format to send over the Netlink socket, right? So what does this YAML spec give me? How does it save me time?
Yeah, I mean, if you need to write a library from scratch, it just removes the need to update it later on. You still need to know how Netlink works and all the details, basically. But the hope is that you just do that once, and if your colleague later on needs to add an attribute, they don't have to worry about all the netlink bits. They just regenerate the code, or they just use a new YAML description, right? And there's no work to be done there.
Cool, thanks.
Okay, the second talk today will be by Daniel, and he'll be talking about kernel data bus. It will be very exciting.
All right, so hello everyone, and welcome to the talk about the Cilium BPF's kernel data path revamped. So what I want to talk about is essentially 4 parts. One is the motivation on what happened recently as an incident in one of the user environments, which motivates this whole talk. The next step is a little bit around context for the TC object model and what Bpf links are. Then the third part will go into the revamped design of the TC BPF data path, and the last one is the Bpf link integration for it. So, interference at prio 1, handle 1. For this, I want to give an overview how Cilium's Bpf data path looks like. So essentially, we attach Bpf into a lot of things. You can see here the host and also a Kubernetes pod. Most of the programs we attach to are inside the host. The core data path in Cilium is based on TC BPF. That's where all the forwarding happens, where the policy is implemented, various other things. We also attach to the XTP layer on the physical devices, and we also use the socket address layer for the east-west load balancing in the socket layer. But the core of it is in the TC BPF side. In general, Cilium assumes ownership of the data path. So in Kubernetes, you have a so-called CNI plugin, which takes care of networking, and there's usually one main plugin that does all of that. There are also CNI chaining options where you can, where kubelet, which is a component in Kubernetes, calls into multiple plugins, and it works generally, but what they usually do, if there's a minor plugin also attached to it, it will set up, networking devices. It will move them into the target network namespace for the pod, and then it will typically set an IP address or a route, but that's pretty much it. And then the rest, Cilium is taking care of. It's attaching BPF programs to it. In case of Cilium, so if you don't have chaining, then Cilium does all of what I mentioned earlier, and it also installs BPF programs as a CLS BPF instance in direct action mode with prio 1, handle 1. And there are some options for more advanced users. If they want to, they can set a different priority or handle, but then all bets are off, because whatever the program is doing that is running before Cilium, it could terminate the pipeline, and Cilium might not see those packets. So essentially, if you have policy enforced in Cilium, this would be bypassed if something is going wrong with the other CLS instance, right? So that should be well understood in general. So one tale from a recently that we run into in a user staging environment, luckily it was only in staging, was an outage. So essentially the user reported that clusters have been unhealthy, multiple pods, they run into crash loop, and it wasn't clear whether it was workload or Cilium pod. And something suggests that routing is going wrong, or something on the underlying fabric. So we did some more debugging together with the user, and he said that, pretty much he has the same configuration in Cilium and other versions where it's working. And the only difference in this environment was that there were nightly reboots, but the rest is pretty much the same. They deleted all the policy to make sure that there are no policy drops that could cause connectivity failures. And some nodes in the cluster were good, some others were bad. So after a lot of debugging, it really turned out there were no failures in the agent log. Everything looked reasonably normal. And from the systemp, which is something where we grab all the commands that are useful for debugging in the system and we put them into a zip file, all the states looked reasonably normal. No packet drops and no issues from the policy angle. The routes look good and also nothing suspicious from netfilter. So until we noticed this, right? So Bpf tool net saved the day because we were able to introspect what was going on. So Cilium is typically creating LXC devices. Those are weave devices that we create for the pod. So there's like a one-to-one mapping. So that looks reasonable. We attach to a CLS act. We attach to the ingress and egress. That looks okay. And our programs that we install, they are typically called, like for the containers, Bpf LXC. And we have two sections called from container and to container, where Bpf programs handle the input and the output. But then those programs, they looked suspicious because they were not installed by us. We don't have anything that is named like this. And when we were, like the first thing I tried when trying to find the potential source for it was searching on GitHub. So who names classifier egress security? And it turned out there was a result, which was from the Datadog agent. And actually, this was really it. So this was the bingo moment where we saw that the agent was actually running in this user's environment, right? So what essentially was happening, that the third-party agent was, removing all the CLS Bpf instances that we initially set up earlier, and it's exactly using the same priority one, handle one that we had. And the Cilium agent assumed everything is fine, but actually it was not. And removing the third-party daemon set and restarting the Cilium one, where it then reinstalls the program, everything got back to working state, right? So that's the that's the initial motivation of the problem we want to solve, which is the ownership problem. And one way to do that would be Bpf Links. And I go a bit into more details what Bpf Links are. So Bpf Links essentially represent an attachment of a Bpf program to a Bpf hook point, right? So it's an abstraction on top of the Bpf programs. They contain a Bpf program. They hold a single reference to make sure the Bpf program doesn't go away. And one interesting thing, which is in contrast to Bpf programs, so the hook points, they do not reference the Bpf link. So the Bpf link is only referenced either from the application or when you pin it to the Bpf file system to make sure it doesn't go away when the application exits, right? The Bpf link also holds metadata, which is specific to the attachment. You can create it, update the program inside of it, detach it, and so on. So there are a typical set of operations that we have in Bpf. And the application only has to deal with the Bpf link file descriptor after it did the setup. So after it installed the program and it created the link, but then it can close the program file descriptor because the link has all of it. And it was originally designed to explicitly allow to prevent the proc detachment on when the process exits, right? Because if you have a file descriptor, they typically get cleaned up as well. But when you pin it, the Bpf link, then that would solve it. For example, think of a tracing app. If you want to upgrade the app while the program keeps running, that's possible this way. It also coexists with non-link attachments for various hooks. And one of the key properties that are quite useful in this context as well is that Bpf links, they cannot replace other Bpf links. They cannot replace non-Bpf links, and also the other way around. Non-Bpf links cannot replace Bpf links. Only if you don't use a Bpf link, you can replace that with something else. So that's important to keep in mind for later. There are currently 9 Bpf link types. that exist today. They're mostly relevant around tracing and some of them in networking, but there's no TC Bpf link. So now a little bit of context around the TC object model and how we could relate it to Bpf links. So as probably most of you know, so we have a TC ingress and egress hook. There's like a, like a fake QDisk, which is only a container for various, for a list of classifiers. They can be Bpf, they can also be something else. For Bpf, we have the CLS Bpf. The direct action mode there means basically that we install a Bpf program, as you can see in this case, which does a bunch of things, and then it returns in like an action code directly. This is, like the typical way you have classifiers is down below. So you have a classifier. If something matches that classifier, you execute an action, and if it doesn't, you go to the next classifier, right? So that's like the old style that is there for a very long time. And the action codes is you have TC act unspec, which means you go over to the next program because like you continue in your pipeline. But you can also terminate it with various other action codes, either TC act OK, where you either push the packet up the stack or down to the driver, TC act short, where you drop the packet, or redirect, where you redirect it to a different networking device, which is also what we make use in Cilium itself. And there are a bunch of other action codes, but they're not really relevant for Bpf. This is how it typically looks inside Cilium. So we just have really simple. So we have the TC ingress egress hook. We have the CLS act QDisk. We have one single instance of the Bpf classifier with the program in it, and it returns something where we then also terminate the pipeline. And this is also needed because we, as I mentioned earlier, we implement complex things inside Bpf programs, such as firewalling, load balancing, local forwarding, and so on. So the question is, how can we marry both together? And it's a bit tricky because TC has its own object model, which I just described, and it doesn't really fit well together with the Bpf link, right? So if you think of tracing, the idea was to actually twofold. First of all, to safely clean up everything when you destroy the link, and to leave nothing behind. And the other thing is to also keep it alive when you have it pinned. The keeping alive part exists today with CLS Bpf because you can just terminate TC or whatever loads it, and that still keeps running. But there's no good concept around the ownership. Like going back to the original or all the discussions on the mailing list, it's actually interesting. So for Facebook folks, the whole motivation around TC Bpf links is around the safe auto detachment. So they run into an outage where an application crashed and it got rescheduled, and then it left the CLS Bpf instances behind, and then they drain resources from your machine, or they were dropping packets, so the behavior turned out to be inconsistent because of leftovers. And the other thing is, like for tracing, for K-probes, U-probes, it was kind of implicit, and like until it has been made explicit with the Bpf link support for it. And really the contract that the Bpf link must provide here is to guarantee that the Bpf program will be executed. And in case of Cilium, it's exactly the other way around. So we need some kind of flexibility. So in Cilium, it's what we want to do is to be able to upgrade the Cilium agent to a newer version while the Bpf program stays alive in the data path and while traffic can keep flowing. So so how can you marry those two things together? So basically, the Bpf link would kind of have to prevent CLS Bpf proc detachment, like with similar semantics from around the tracing. But it's not straightforward transferable because, in the TC side, we are not FD based, right? So, for example, the CLS act QDisk, they could just wipe the CLS Bpf instance and, everything is gone nevertheless. And also the other thing is other classifiers around TC, they don't really fit into the picture because, Bpf is just one of them. So it doesn't really fit well into TC internals. And just to show you, there was an attempt earlier to try to make it fit together, and it's kind of intrusive and kind of very specific to Bpf, where you have to touch TC core bits, which is a bit ugly. So some additional thoughts here. I mean, like the motivation that I mentioned earlier is the safe ownership model for TC Bpf programs in Cilium. So, you know, like cooperation between Bpf programs, it can be possible, I mean, through the TC Act unspec, but you really have to make it explicit. So you cannot have implicit, like an implicit cooperation where, you know, when both programs assume they own the data path, it's just not, you know, possible oftentimes to make them work together. So the Bpf link should really act as a, you know, safeguard to potentially to protect those different components from stepping over each other. So with that, how does the RefM design look like? So if you take a step back, you know, like back in 2015 when we originally merged it, it was like, you know, at that time it kind of fit. But nowadays, you know, the usage around Bpf has skyrocketed. So, you know, I thought, well, can we do actually better today? So some of the lessons, you know, learned from the TC data path, which are, you know, kind of obvious in retrospect nowadays, are that, you know, the relevant parts from the QDisk, they are like on the actual queuing, like the FQ or FQ coddle, and for the, you know, like those fake QDisk, for the ingress and egress hook, they are mostly used around two things, I would say. One is like, you know, oftentimes a slow path for the hardware offloads, such as the Open switch. And then the other thing is also on the Bpf side, where we really want to have a fast path. From the user experience side, you know, the CLS Bpf has been hard to use. LibBpf helped a lot with that. So, you know, like small extract, how you can program this today. So it really abstracted away a lot. But it's also not perfect because given there's no ownership model, there, like the cleanup part is also not really fully clean, because the CLS Act QDisk, for example, you cannot remove because you don't know whether, I mean, it could be racy, right? So yeah, basically requirements we want to have if you want to redesign it. So it should be FD based so that the Bpf links blend in perfectly. It should have multi-attachment, but it must be efficient. There should be minimal overhead going into a Bpf program. It should be easy to program and to consume from an API perspective. And ideally, we don't want to, you know, add yet more hooks to the networking stack. And it must support a migration path, you know, where people still use old style CLS Bpf, and, you know, they want to migrate over. And the TC programs ideally should not be changed, so they should be supported as is. And, you know, this is what I came up with. So you have essentially the TC ingress egress point. Here you have a small array, and then you can call, like all the side here on the right is still the old style. So there's no change in behavior or semantics. But what you could do is you could add additional entries, and you could attach Bpf programs into it through this, you know, new style of attachment, which would be FD based, right? And if that Bpf program does like a TC Act unspec, it will continue in the pipeline and continue with the old style QDisks and classifiers, right? Just as in exactly the same way like the old TC framework does. So you can, you know, add multiple of those. But what you also can do is if you don't use any of the old style TC stuff, you can just terminate and that's it. So the attachment here is through BPFnet, ingress and egress. So this is through the BPF system call. That's what I implemented. And the native, like the data path side, the code in here looks as follows. So I'm just taking the ingress as an example. So you have the schedule handle ingress. So that's as is, and now the new implementation essentially, you know, runs a bunch of BPF programs and really only handles the essential TC return codes, and the scat-run procs just looks like this. It's just a simple array, which is then also, you know, more cache friendly. And if there's TC unspec, we go over to the next one. If there's not, we terminate the pipeline. And the old style TC basically also blends into this by having, you know, by being one of the elements that we have in this array that we can call out to. So like for comparison, From the entry point with the old style, we go into TC classify. Inside there, we have a list of the various classifiers, and then we have this indirect call to classify. Then we go into CLS Bpf as one example, and there again, we have a list of Bpf programs, and only then we go to our actual program and execute it. Worst case, even we have to do an allocation on the return path if there's like a TC act unspec, which is not so great, but that's what is there today. And with the new style of attachment, you just go into the run procs, you go over the array, you run and execute the programs, and that's it. So doing a micro benchmark, we were basically able to halve the cycles needed for just going to the Bpf program, having a verdict. Of course, that's all when cache is hot. So I would assume the diff would be bigger when it's not hot in the cache. And yeah, how does it look like from a user API? I also did the implementation in libBPF. So essentially, you have an if index, and there's a priority. Priority can be 0, which is pretty much similar to the old style TC, where it would then auto-allocate a priority, or you set it explicitly. And then you have Bpf proc attach ops, where you specify the file descriptor, the if index, the location, and then your additional options where you want to replay something or not, and your priority. Same for query. You can query at the ingress or egress location of a given net device in your network namespace, and then you can gather all the information related to it. And the output is essentially that you get back like a program ID, here a link ID. I will go into this a bit later, and then the priority. So you get the list of programs attached to that. And the detachment is also pretty simple. So you just specify the priority, the index, and the location, and then it gets removed again. So essentially like this FD-based data path, now that we have it, we can implement Bpf links on top of it. It also allows for like an initial migration path for application, because before they implement all the link management in a later step. And this multi-attach array that I mentioned, it's right now I picked a 32 slot each, because if you have more than that, it will probably slow it really down, but it can be made dynamic. It has the same priority concept as the rest of TC, and the auto allocation and the TC action codes and the semantics are also pretty much the same. And for the ingress and CLS ACK, they basically use the same API internally from within the kernel. So the integration with Bpf Links, that's the last topic. So from the kernel side, they are then supported for the new FD-based TC Bpf data path. They contain the, like a TC link object for Bpf contains the device priority and location attributes. They implement the attachment, the atomic update, and the detachment. And they solve this initial problem of the ownership that I mentioned in the introduction. So that's essentially how it looks. And from the libBPF, I added 2 new TC sections. One is for the ingress and one for the egress, because then we can also map this to the 2 new enums that we use. And the Bpf Link implementation for that looks also really straightforward. So we specify again the if index and the priority. And after we load a skeleton, but I mean, that's for libBPF, for others, they don't have to. Then we have a Bpf program attached TC API where we just specify the individual program with the if index and priority. We get the link object back, and this can be cleaned up naturally. So yeah, that's it. I have a POC code with everything I talked about in here in a private branch and cleaning it up. And yeah, goal is to send it out sometime around next week. So yeah, thanks. And yeah, any questions?
So you said you had an array of programs, so you're still doing like the indirect calls into each program?
Yeah, I mean, for Bpf, you have this anyway, the indirect calls, right? I mean,
Yeah.
like from this array to the program itself, yeah.
But would it make sense to, like, for XTP, we have this generated trampoline stuff. So you get rid of the indirect calls, that you can basically generate the array thing as direct calls that loops through.
Would be possible, but then the problem is right now, I mean, this needs to be supported on all architectures, right? We could do this in the future, but you know, like I didn't see, you know, a straightforward way initially, at least.
Oh, okay, so but it could be a performance optimization. Just
It could be, yes.
architecture.
I mean, it doesn't prevent it. I mean, from the user API perspective, it would be the same, right?
And as far as the API is concerned, I think it makes a lot of sense. Can we have the same thing for XDP, please? Like
Again?
with the can we do the same thing for XDP with the multiple priorities?
Probably, yes.
That was exactly my question. Like, it feels that, like, if we adopt this concept for PC, like, we can do the same for XDP and just say, well, finally.
I would be, as someone who has implemented this in user space with a libxdp, I would be in favor of moving it into the kernel. It's basically the same concept that we're doing. So that would make a lot of sense.
Yeah. It could be used for sure, yeah. I mean, the one thing we probably have to get rid of is like this this branch funnel that we have, like the branch generator from Bjorn. That's the trade-off.
But not necessarily. That could be replaced with the generated trampoline.
Yeah, probably.
And we could share that code between TC and XDP.
Yeah.
So I have a different question. So why are you still calling it, like in the code, you're still calling it a scheduler? There's nothing scheduler in there. Like SCH, I'm assuming is scheduler, right?
Yeah.
And why you still call it TC? Like, why is it all TC? It's nothing to do with TC, right?
I think like I mean, most people have it these days as a mental model, right? I mean, yes, it has nothing to do with TC, but it's like the whole layer that we talk about. So we have XDP layer, TC layer, and socket layer, whatever, you know. So I think,
yeah,
you know,
but like, can we call it SKB layer? So we have like XDP, which is like packet-based frame, and here like SKB. So that's the first thing like SKB does, and well, maybe call it SKB layer, because that's kind of what it is. It's not this. TC has so much like legacy, including like all of the opcodes. Like, can call it TC, I don't mind. It's just like, it feels like if you're doing like a clean slate like design, and like we can preserve all of the like action codes to be like compatible, but instead of calling it TC act unspec, call it whatever, SKB drop, or like SKB redirect, SKB pass. Well, because that's what it's doing.
Yeah,
I don't know,
like
just an idea. Like TC also kind of makes sense, like not to confuse people because it's exactly the same, but still, just scheduler and TC.
There could be some more unification between XDP and TC here as well, right? Have net ingress XDP, net ingress FKB, TC, something, but like the attachment could be pretty much the same.
Yeah, I'm fine with that. I mean, the one thing maybe like, how do you then call the, I don't want to, you know, like how do you call the C group ingress egress thing where we have an SKB hook, right?
Yeah, C group, C group SKB, but there like we have a C group prefix, so it's not the biggest, but
yeah.
So, by the way, one small comment like about this TC act short and all that stuff. You should probably start defining them as enum so they get into vmlinux.h and you don't have to like pound define all that stuff. So, but actually, what I wanted to mention that would it make sense to support cookies as well there? So, like, imagine you have like the same sort of BPF program that controls multiple interfaces, right? By attaching the same program, just specifying that this is interface 1, 1, 2, 3, and all the stuff, and then fetching that through. That makes sense, right? And like you, a new program. So
it makes sense. Yes, I agree.
I've seen you do priorities again, isn't it? You mentioned on the first slide that you've got in into the problems because of that. Should we maybe do something similar to what we have in C groups, where you can, when you attach the program, you say, my program plays nicely with others, so the others can either override me or they run all together, right? We have in C group, we have this chaining. Should we also have something here saying like, oh, I want to be exclusive program that owns this interface, or I know I can play nicely with the others? And
I mean, if you know you can play nicely, then you don't have to specify a priority, right? You just let it out allocate, and you just need to make sure that you have this TC act unspec or like SKB continue, whatever you call it, right? I mean,
but I guess the problem, right? You have this one data daemon set that wants to do something, and then you have Cilium. Yeah. I don't think this solves it, right? They still ordering still.
I don't think you can fully solve it, because like there are different teams, you know, they implement different programs, and maybe some of them expect ownership, others not. You actually have to talk to each other to really make something work, because you have all the actions where you want to drop or where you want to redirect. So it's not really possible, I would say.
But yeah, and playing nicely with others can also be unilateral, right? You can have a program that can work with Cilium, even though Cilium doesn't think it can work with it. If it's just something that monitors the packets by becoming
that's possible, yeah.
So you like if you make it up to the program and say I am exclusive, everyone is going to say they're exclusive, and we really need the operator to be able to override this and say no, I have this monitoring program that I need to run before that.
Yep.
By default, but you can say maybe not with links. It might be by the only if the links are used, though. Yeah.
Cool. We're doing amazing today. Everyone is just perfectly on time, half an hour each. So the next talk, next half an hour before the break, Anton from Isovalent will talk about new map. I think he sent the patches, and I think you had like plenty of comments on the mailing list. So
okay, hello everyone. I'm Anton Protopopov from Isovalent, and yeah, let's talk about how to do packet classification using Bpf, and in fact using one single map in Bpf. So we will look at different algorithms which can be used for online packet classifications, and then I will review the API of this new map and show some numbers so that people can see how it works, how it fits inside Bpf. So packet classification in general, we have a set of rules, then we have a stream of packets, and we need to match common packets with rules. And rule can be as just simple, like we filter by source address or source prefix or a port range, or it can be a combined rule where we have several fields inside packet and we want to match all of them, like 4 or 5 tuple or something else. And of course, a requirement is that we have fast lookups as fast as possible because we have a stream of packets. And online packet classification, like in white papers, it's the same, but it also requires fast updates so that updates can be made not by operator typing things, but just by a robot. So use cases for packet filtering are pretty like obvious and generic. So software-defined networks, any kind of firewalling, routing decisions, etc. In Cilium, we have at least 3 use cases, which fits well with this map. One is the Cilium Max DP per filter. It's a simple DDoS mitigation mechanism right now, it supports filtering packets either by source address or by source header. And in the first case, a hash is used. In the second case, an LPM tree is used. And new map actually tends to work faster than LPM. So we can pretty simple optimized Cilium with this new map. Also, we can let users to specify more sophisticated rules if they want, because when they provide configuration, we can just set up a new map with different configuration. They can filter using not only source address, but other fields as well. The second example is packet recorder for our standalone load balancer. There was a talk last year by Daniel and Martins about the packet recorder. It kind of supports wildcard for tuples, but actually doesn't, because we do not support port ranges. And sometimes when you update map with a new value, it requires recompilation of programs. So it is not an online algorithm. It can take seconds to set up a new rule or to delete a rule from a table. Another example from Cilium world is Kubernetes and Cilium network policies. Cilium provides container networking interface for Kubernetes, and the latest Kubernetes version made port ranges the standard feature. This means we need to support it, and we currently don't. We kind of can implement this using LPM, but LPM, again, is a little bit slower than this hash. And also, we can't implement real ranges with LPM. We can implement prefixes, but not ranges. So what is like design decisions for this new map? It should support easy configuration between different rule structures. Even in Cilium cases, we have 3 different rule structures. In the first case, we filtered like source prefixes. In the second, the for tuple. And for Kubernetes networking policy, we have a security ID plus a port range. So it's 2-field map. It obviously needs to support fast lookups and fast updates as fast as possible. And one thing is that complexity. For Cilium, complexity is a concern because we have way different configurations running on different servers. They support different kernels, and the solution should be as simple as possible. And in case of map, the complexity is as simple as possible, because to insert a rule, you just do a Bpf map update. And for matching packets, you just do Bpf element lookup. So what are algorithms which can be used for packet filtering in general? So the simplest one is brute force. You just take a list of rules and then you match them one by one. And this obviously doesn't scale to more than, 16 rules. So there are other 2 family of algorithms which solve this problem to be scalable. One is hash-based, the other is tree-based. Obviously, hash-based provides something like constant time lookups, and tree-based logarithm time lookups. And the basic idea between all these algorithms is the same. You take a huge set of rules, you split them into several buckets or tables. It's called tables in most times. And then you do brute force on top of tables. So for each table, you do a lookup. If it matched, then okay. If not, then you go to next table. So let's look at times which this algorithms provides. I took this picture from the Tuple Merge white paper. And here we see several algorithms. The tuple space search on the right, it's used in OVS, and it's hash-based. The original one, hash-based algorithm. The partition sort is tree-based algorithm. The previous state-of-art algorithm, the tuple merge, is the new state-of-art algorithm, which works faster in both lookup and update times than partition sort. And on top, you can see the smart split. So from this table, it's seen that its classification time is the fastest, but its update time can take seconds, so it's not actually a solution. So let's look more precisely at how hash-based algorithms work. I didn't implement and didn't try to implement the partition sort, the tree-based one, because lookup time is logarithmic versus constant, and also Tuple Merge white paper shows that it is slow by both lookup and update time. So let's look at hash-based algorithms. The tuple space search is the simplest one. So we have a set of rules. In this case, we will just filter by source address for simplicity, one field. And the tuple space search joins rules in tables by the length of the prefix. So here we have 2/16 rules, 1/8 rules, 2/24 rules, and we combine them into 3 tables, one with /16 prefix, another with /8, and another with /24. So when packet arrives, say 10.222, we need to look up every table, and first we go to the first table. The first table has a prefix 16. This means that to look up this packet, we apply a mask of 16 bits, and we get this value, and we see that it doesn't belong to this table. So we go to the next table. Here we have a prefix /8, so we apply a mask of only 8 bits. We got this value, it doesn't belong to this table. So we go to the next table. Here we applied mask of 24 bits, and voila, we found the packet inside this table. So this is a match. So what is the problem with tuple space search? So it's not a problem with tuple space search, it's for all this algorithm, but in tuple space search, it's pretty obvious. Like to do a successful lookup, we need to look up about half of tables. To do unsuccessful lookup, meaning that packet doesn't match, we need to look up and all the tables. And even in this case, with one prefix for IPv4, we can have something like 33 tables. If we go to 2 fields, here is an example for source and destination addresses. We can see that the number of tables grows too fast. So here on the horizontal axis, we have number of rules. And on the vertical, we have a number of tables. And we can see that even for 100 random rules, the number of tables is already like about 50, 60. And this means that even for 100 rules, we will do about like 30 hash lookups per packet. This is too slow. And for IPv6, it gets worse because we have more randomness, we have more and more different prefixes. And here, for example, at about 10,000 or 20,000 rules, we kept at 4,000 tables, which doesn't work in production at all. So the tuple merge algorithm solves this using several optimizations to tuple space search. So first idea is that if we have a particular table with particular prefix, we can put there rules which has greater prefix. For example, if we have table /16, we can put /16 rules there, we can put /17 rules there, we can put /24 rules. If another rule appears like /8, then we can't put it inside this table, we create a new table. And only this optimization dramatically reduces the number of tables. So this is the same experiment with the number of tables for tuple space search. And below you see the line, almost line for the tuple merge. For IPv6, it is really undistinguishable from straight line here. The second idea, which can reduce the number of tables, is that when we got a new rule, which doesn't belong to any table, we don't take a prefix as is, we just trim it a little bit. So for longer prefixes, we remove a little bit more rule bits. For shorter, we remove little less bits. But in general, if we have, like, for example, /16, we create table not /16, but /14. So /16 rules would fit there, /15 and /14 will fit there. If we see a /13 rule, then we will create a new table. This also reduces the number of table. This is the same example. So on top, you see the number of tables for untrimmed tuple merge version, and below you can see that if we trim tables, the number of tables reduce it like twice for IPv4 and even more for IPv6 because we had like more randomness here. So the third idea, which was used in tuple merge white paper, and it is not applicable to the generic implementation, unluckily. So if we have two fields which differ a lot, like example, we have 24 prefix and 8 prefix. So we can just omit the 8 prefix because it doesn't provide a lot of randomness in any way. So, but it is not applicable in generic case because in tuple merge white paper, they filtered 4 tuples, and we have source and destination IP addresses, so we can distinguish, like, choose between them. But in general case, we don't know in advance what field means at all, so we can't simply like compare them and decide which to omit and which provides more randomness in general case. So other problems with tuple merge, yes, there are some problems. Namely, we can't guarantee the number of tables in advance. This means, like, for example, that if we want to pre-allocate map, then we need to pre-allocate way more tables than is required, actually. And even in this case, we are not 100% guaranteed that we will have enough memory. But another thing is that the number of tables depends on the order in which rules appear. So here's a simple example. We first have /8 rule, then we create a table of prefix 7. Then we see /16 rule, and it fits inside this table. But if the /16 rule appears first, then we will create a /14 table. And then when /8 rule appears, we have to create a new table because it doesn't fit in the smallest one. So the order of rules in this small example means a lot. Like the second example will be twice slower than the first one. And when we have a lot of rules, it doesn't like scale exponentially, but it is random. So we can fix this by pre-allocating tables for a particular map. In this example, we have IPv6 4 tuples, and say we know that no rule will appear with prefix shorter than 32. Then we can just create a 32 table, and all the rules will fit inside this table. We still will have 64 bits of randomness, which is enough for hashing. And if we want, for example, to ignore source or destination, we can create not 1, but 3 tables. And most of rules will still be in the first one. So for lookups, it won't slow anything down. So a problem with this is that, it's cast in stone. So if we created a map for a huge system and said, there will be only 32 rules, but then 2 months later, we decided that we need to support 30/30 rules, then it doesn't work. We either need to break them or to reboot the thing. It is, of course, doable, but not very convenient. Another thing which is way more inconvenient is that if we provide API to do something, the users will find a way how to use it wrong, and we'll have more bug reports and maintenance burden. So which algorithm to use for this map? So first, the idea was to do all the things, like to support algorithm brute force and support algorithm tuple merge, and then provide a flag to do additional configuration for tuple merge to do to allocate static tables. And this is what I sent in the first RFC. But actually, this is not like too good. It's better to provide less API, and probably the next step will be to provide just a generic algorithm without this additional configuration. If there will appear a better algorithm, we will just replace implementation, so the API doesn't change. And another thing which Stanislav mentioned is that in future we will be able to implement such classifiers using Bpf itself. So it will be possible to just create a map, load the Bpf program, and then say that this map will be classified using this particular program, which provides like a lot of flexibility and reduces like maintenance burden from us, because all decisions are made by users. So let's look at an example. Again, the example is pretty simple. We will filter 4 tuples, source and IP destination addresses, IPv4 by prefix, and then we will have source and destination port ranges. So this is how we define a map. It has type Bpf type wildcard, and here we choose the particular algorithm, which can be omitted in future patches. So this is pretty simple. Like, this is map description, the field structure description, which we use here. We will review it shortly. And to use this map, it's also straightforward. Here we create a rule. So it's source address and its prefix, it's destination address and its prefix, it's port range and destination port range, and then we just do Bpf map update. To look up packets, it's even simpler. We need to copy less fields. So we just copy source address, destination address, we copy both ports, and we just look up element inside map. So let's look at how we define a particular rule structure. So for this map, we say we have 4 fields. The structure will be called Bpf4 wildcard, and we have like description of fields themselves. The first field is prefix, it's 4 bytes. The second is also prefix, it's also 4 bytes for the destination address. And we have 2 16-bit ranges for source and destination ports. This name is used to specify the structure names in map definitions. So the first one is struct key. It is defined by this macro. We don't need to define anything else. And the second one is a new field in the BTF map definition called wildcard descriptor. And it is required to tell kernel how to interpret the key, because kernel sees only void pointer and size. The key itself looks like this. So we have a structure, it has type, it is either rule or element. In case of rule, we use this part of union. In case of element or packet, its names are hard. We use the second part of structure, and they look like this. So for packet, it's pretty simple. It's source, destination address, port, and destination port. And for rule, we have more data. How they match, like this. So we have source address in a packet. We go to the rule, we have source address and prefix. We have destination address, we have destination address and prefix, so we can match them. For ranges, we have a name here and minimum and maximum value in the rule. Again, name here, minimum and maximum value here. So as I mentioned, kernel only sees void key and key size. So we need to tell kernel how to process the packets. And it is done by passing this structure in Bpf attributes. So we have number of rules, and for each individual rule, we have another structure which describes the rule. It's also pretty simple. It's just type and size. So prefix, range, and size. So for our 4-tuple case, we have 4 rules, and we have 4 field descriptors. The first one is prefix of size 4, 4 bytes. Another is prefix with also 4 bytes, and 2 ranges of 16 bits. So there is one problem. We can't specify the structure in BTF definition because BTF can't get the structures. So we need to actually macro defines another structure, which is parsable, which is understandable by BTF. And then libBPF takes the structure and translates it to the structure which kernel will understand. So we take number of rules here, we just convert it to integer. Then we take the first field called source address, and we convert it to prefix and size, and so on. So again, for users, like for users of this map, it doesn't matter all this machinery because we just define the simple structure. Then we just pass this name in the key and wildcard descriptor without like any problem. So what kernel changes required to do this, besides implementing the map? Another piece of data needs to be added to BPF attributes. So on map create, we copy another piece of data which contains this wildcard descriptor. And of course, libBPF needs to parse the BTF description to the description which understandable by kernel. And that's it. No extra changes. So let's look at numbers. Here we see 4-tuple IPv4 case, and rules. We have a number of rules like from 100 to 100,000. So the scale is logarithmic. And the blue one is the generic tuple merge. We see that it jumps up and down because we don't know in advance the number of tables. The orange one is a static tuple merge when we allocated 4 tables. And the green one is the static tuple merge when we allocated just 2 tables for IPv4. And we see that like if you have less tables, we have faster lookups. But even in generic case, again, this is the right side is for like 100,000 rules. So we still are under like or at like 120 nanoseconds, which is pretty good. For unsuccessful lookups, the numbers are more or less the same, but we see that like for unsuccessful lookup, we'll look up twice more tables, so numbers are twice bigger. And we see that penalty for having more tables is greater for unsuccessful lookups. This is the same numbers for IPv6 case. The only thing which differs here is that the static table below has only 1 table. So we actually do only 1 hash lookup for IPv6. And also one thing to mention, unluckily I don't have numbers here on this plot, but like the generic hash, if you just hash 2 IPv6 addresses, it looks like to be a little bit slower than this static tuple merge, because in tuple merge we only use 64 bits versus 256. This is unsuccessful lookups for IPv6. And another slide with numbers is that for simple case, when we just filter 1 prefix, this map, even if it's generic form without like static allocation, it works faster than LPM tree. And if we like grow number of rules, it seems that it also like tends to grow less because LPM is logarithmic, we are constant. So for Cilium cases, for example, we can just replace LPM with this new map and we'll just benefit from speed here. This is updates for the LPM and tuple merge. Again, we can see that there is a difference. So this is almost it, almost fit in time. So this is the picture from this tuple merge white paper, and you see this trade-off line and unfeasible region. So now it looks like this. The kernel implementation of Tuple Merge is in the unfeasible region. Of course, this means that we need to draw trade-off line in a different place, but still. And also, I want to mention, like, here is like half of microsecond for an update. Even for not pre-allocated maps, we have better numbers. I just didn't want to move it here. So for pre-allocated maps, we will have numbers like 100 nanoseconds for updates and 100 nanoseconds for lookups, which is actually pretty good. And for, again, this is for big number of rules. If we have thousands of rules, not 100,000, it's even faster. So that's it. Please send your use cases for packet filtering so we can refine the user API and do the minimum user API visible. And thanks for listening.
Many thanks for sharing. I have two questions about this solution. The first one question will be: is there any rules numbers up limit by this solution?
The limit on number of rules?
Yes, yes.
No, like you can define any number of rules. Of course, like it will slow down the lookups because you will have to process more like loop iterations. We have a generic match function. And another thing is that in this case, for example, for 4 tuples, we can just ignore port ranges. So the number of tables depends on like source and destination IP addresses, but the fields with port ranges do not like add any new tables. If you have 10 fields, each of fields is like important and you can't ignore this, then the possible number of tables can grow like exponentially by number of fields. So you need to refine which fields can be ignored in this case. So for port ranges, it's a general thing that in such algorithms, port ranges are ignored. And so if we have like hash collision, which brings us to like several port ranges, we just solve it as a usual hash map.
Thank you. The second question actually is for production environment. You know, it's not just about the latency for the rules, also about the memory usage, right? So if you have any data for the memory usage for this solution, for example, how many memory you will cost?
Yeah, so this costs exactly like a normal hash. So you just have a hash table. We use only one hash table per all tables. And we allocate buckets, of course, for a hash table. But otherwise, it is the same.
For one example, in your experiment, I saw that 400,000 rules. So given the LPM solution, so how many memory will cost roughly number?
I didn't remember. I didn't measure the memory like precisely, but for hash table, like if you have 100,000 rules, right? You will create a hash table with 100,000 buckets, as we do like for a hash. We can like right now it is done like this, and it is done like the hash map, like normal hash map. In my like early experiments, I did allocate less buckets than the number of rules, and of course, in this case, we have more collisions. But again, like we can allocate like 4-8 times less buckets than rules, but this will, of course, impact the collisions, the lookup time.
Okay, thank you.
Hello, my name is Lawrence. Can you go back to the slide where you talk about changes to BPF map create, please?
Yeah, sure.
Yeah, that's
Yep.
one more.
Yeah, that's one.
Yeah. So here the extra data is like a sized buffer. Can you tell me what's in there? Is that like BTF wire format?
Yeah, of course. So this buffer contains this second structure, struct well-covered desk, and it just contains here. Second, yeah, here it is. So in this case, we will pass this structure. So 4 rules, and then we have an array of rules here, an array of descriptors. So we have a generic match function. It goes to the first rule. It takes a look here and says, prefix, it's size 4, and etc. So this one.
Yeah, so my kind of follow-up question is, for other parts of the API where we specify types via BTF, we usually take a file descriptor for a BTF object and like an ID in that file descriptor. So here you've kind of gone with take a raw BTF buffer, I guess. Like, is there a specific reason you did it that way versus the file descriptor?
Yeah, I mean, it is possible to create a map without using BTF, right? So just use a BPF call. So in this case, like this is like less meaningful. But of course, yeah, we can just say we can just pass create BTF ourselves and pass the BTF object here.
Okay.
Yeah. So yeah. So instead of doing this, we can pass a BTF ID.
Cool. Thanks.
Hey, Anton. Not surprising to see you working on this. I know you've thought about it for a long time. Did you consider leveraging any of the routing layer implementation, since it's already doing an LPM type match? So it already has like optimized trees for insert, delete, lookups, that kind of stuff, and trying to reuse that for this.
No. So I didn't have like, sorry, I didn't have much time to work on this actually. So I just wanted to implement like Tuple Merge in form of BPF map, and only considered our Cilium use cases yet. So.
Okay. Because it has well-known, understood properties in terms of it's been highly optimized in terms of lookups and the insert. We know the memory aspects of it. So anyway, something to consider if it could be extended for this.
Absolutely. Thanks.
Yeah, I think to add.
Oh, sorry. Yeah, so my initial comment was I would just like to appreciate the fact that we just heard from Daniel how BPF is now no longer semantically a classifier. And now we have a talk about adding a classifier that can be used from BPF. And I'm sure we'll come full circle a couple of times. So in terms of the UAPI, when I saw the patch series, I was, it was a little bit inscrutable. This helped a lot to explain. I think it would be useful to separate out the BTF format for defining this and the actual UAPI to the kernel, as Lawrence was also saying. Also because we have user space libraries that are not C and BTF based. So having this defining and like documenting the struct format for actually passing the definition to the kernel separately would be useful for understanding how this works. And also I fear a little bit that this is like something that will lead to another e-inval hell when you're trying to debug why your definition is not working. And I'm not sure.
This is why I defined this like macro to provide such a descriptions. And so I don't know, if you look at the slides, like the user API is pretty simple, right? It's 5 lines, extra lines compared to a normal map definition. So users shouldn't think about this like at all.
Well, as long as they just want to do a normal 4-tuple match, yes, that's simple for a certain definition of simple. But once you want to do weird things with this and try to change it, the kernel is just either it's just going to accept it and your matches will be wrong, or it's going to give you back an enval if the format doesn't match. And this will, like, this is the kind of thing that confuses users of this, right? If you
Yeah, for this actually, while developing this map, I also was thinking about enval because I had, like, of course, during development some bugs, and I had a lot of envals. So I was actually like thinking about doing something like verifier does. Like if my map update failed, I would just pass another map update with a log buffer to do this. It will be slow, but I just, if I need to know the reason, then I can just use like a second, like maybe statically linked version of Bpf map update, which does the same but provides some insights of what's went wrong.
Yeah, so like we just heard about netlink and its exact and its pointers to which bits are wrong and something. I feel like we're on the way of reinventing that. But this is a general problem for the BPF syscroll, right? You just get back enval and you have to guess what's wrong. So
yeah, but for this particular case, I really like think that like this way of just passing a macro, which will be just copied by other users, is really simpler than creating your own BTFs. For library, it's probably the same, right? For particular users which just write like XDP or TC programs, it will be simpler to just copy 5 lines probably.
Yeah, but so what are the Go users and Rust users going to do?
Okay.
Going back to what David said, I think it would be interesting to compare this to I think you can implement this all with LPM right now. Even the port ranges, I think you can, if you do the like beat mask math, I think you can. So it will be more convincing if the next submission will have comparing this against LPM, array of LPMs, array of LPMs, array of LPMs.
Yeah, for one thing with LPM is that you can only do this with one field, right?
Yeah, you will have to have essentially like multiple array of LPMs going, I guess, like that. Maybe we can talk, I guess, on
Yeah, I mean, if you have like, I don't know, n fields, right, and each of them is implemented using LPM, you'll have n times logarithm lookup time, right? While here we just, like in many cases, we can just jump to like 1-2 hash lookups. It's way faster, even for like one prefix.
It should be pretty easy to show that it's way faster, I think.
Okay, yeah. The next thing for me is to like automate making these plots. It's like semi-automated right now. I will publish the test suite and self-tests and stuff like this.
Great.
Actually, historically speaking, this looks like the original fib hash route lookup algorithm that we used to have in the IPv.
So now we have a 19-minute break.
1, 2, 1, 2. All right, all right. Okay. Hello, everyone. Oh, people are still coming in. All right. Hello, everyone. Thank you for joining me for this talk about sharing IPv4 addresses by partitioning the port space. My name is Jacob. I'm an engineer at Cloudflare. I also help co-maintain the sock map code in the kernel, so you can sometimes see me on the mailing list. And this work has been done together with my colleague Marek, who couldn't be with us today, unfortunately. Yeah, and I'm hoping we can have some nice discussion about the API at the end. So let's get started. Before I jump into the problem and the solutions we have come up with, I need to give you a little bit of context, what our production looks like. So we all know that when we use the internet, we need a public IP address from which we can source the traffic and connect to various web services. But as it turns out, no two public IP addresses are the same. And I don't mean that they don't represent the same 32-bit value. So you see, public IP addresses on the internet have traits associated with them. And one such trait would be geographic location, which is tied to the address you're connecting from. Based on that location, the web services will actually tailor the content that you receive so that when you search for a pizza place, you will actually get results for pizza places that are hopefully nearby. Geographic location is not the only trait that we have out there. IP addresses also mapped to a reputation. If your public IP happens to have a bad reputation, then you might be penalized for that and be faced with CAPTCHAs that you have to solve before accessing a web service. So we run various proxies, but we also offer a VPN service that is based on WireGuard called Warp, where users establish tunnels to our data centers and we forward requests on their behalf. And we also run an Anycast network where every of our data centers announces the same IP prefixes. So we have a situation where users on the internet connect from various public IP addresses, and they can actually be attracted or land on any of these data centers. So what we have, if we have users connecting from, well, many possible locations to potentially every of our data centers, and us trying to mirror the traits of the IPs that the users are connecting from when we forward the request so that we can provide the best user experience. Like for instance, in this example, if a user would establish a VPN tunnel to Cloudflare from an IP that is associated with a location somewhere in Cork, Ireland, and it would happen to hit our data center in Dublin, then when forwarding user requests to the destination server, we'll try to choose an egress IP that has a location that is closest to the user location, so somewhere in Cork, Ireland, so that the user gets properly localized responses. All right, so what's the problem here? Well, we have users connecting from various locations and we have many data centers. So in order to facilitate it, we can imagine two extreme solutions. One where we would have an IP for every potential location, geographic location, on every of our data centers, for which we'll need lots of IP addresses. And that's totally doable for V6, and we've done that. but is prohibitively expensive for V4, unfortunately. But it has some nice features, like we are always able to egress locally. Whichever server receives the tunneled user request will be able to forward it to the destination. And we also get excellent reliability there, because if one server goes down, any other server can proxy the requests. On the other side of the spectrum, we have a very cheap solution where we could have just one IP provisioned for each geographic location that we need to support, and we assigned it to one of our servers somewhere. The problem there is that we'll almost never egress locally. We'll have to forward all the requests that need to use this particular location to this one server that has this IP assigned. And of course, we get very poor reliability. So somewhere in the middle, there is a compromise on price versus reliability, where we can imagine that we would have an IP for every possible location per data center, and that IP is shared by all the machines in the data center. Now for that, we still need some IPs, but we don't need any more millions of IPs. We also don't need to support all the locations in all the data centers to mostly be able to service requests locally. And we get pretty good reliability, right? Still, all the servers in the data center can handle all the requests, and sometimes we need to forward traffic. Why is it so important to strive for local egress for us? Well, if the user hits a server that is not able to directly forward its request to the destination, then it has a negative effect on the latency. We have to bounce the request from server to server before we can go to the destination. It also makes production management harder because you get uneven load. Some servers, in addition to handling requests coming in directly from the users, will also have to process forwarded traffic. If we can always directly egress from the server to the destination, then we get load that is proportional to requests per second coming in on egress. So how can we implement this? Well, the traditional solution for that would be to use SourceNet on the router. And that is actually the setup that is common in our home networks. We have a router that keeps track of all the egress flows and rewrites the source IP. It, however, has a major drawback that the router is a single point of failure here. So if we wanted to make it a little bit better, we could go for a distributed SNAT, which requires shared state between all the servers in the colo that needs to be kept up to date. It's a bit more reliable, but also complex to implement. The question is, can we make it simpler? And yeah, we can. And as you have probably guessed from the title of this presentation, we could also share the public IP address between the servers by partitioning the port space. In this example, each of the servers gets a slice of 512 ports from the ephemeral range that they can use to create outgoing connections. Now, we also have to route the return traffic to the right server. So an important thing to note is that the return traffic has to be routed not only by destination IP, but also by destination port. So we have servers which share an egress IP, a public egress IP, and they have port range assigned to them, and we have applications running on these servers that need to create connections, open connections from this egress IP, but only within that port range. How can we do that? Well, the naive and impractical solution would be to set the ephemeral port range to our port range assigned to the server, and also enable the local source port sharing so that we can reuse the local source port as long as the whole 4 tuple for the socket is unique, and let the kernel find a free port for us. This, of course, has a major downside that we are here changing the ephemeral port range for all the processes running on this server. And also we are assuming that the port range is the same for each egress IP that we'll be using here. So we have to work around that from user space, around this limitation. And we can do that by just sampling the port range that is assigned to our servers and trying each port one by one until we find a free one. In this case, we have to enable local address sharing with Rails address, or otherwise we'll get failures at bind time, and we will be able only to have as many outgoing flows as free local ports. That works great. We have it running in production, but unfortunately, it only works for TCP. So what about UDP? Well, UDP is harder because TCP and UDP semantics for connect differ. So if you are using Rails address on your sockets, then when you try to connect 2 sockets, bind and connect 2 sockets to the same 4 tuple, TCP will report a conflict when there already is an existing socket that uses their 4 tuple. However, UDP, on the other hand, will happily create 2 sockets that are bound and connected to the same 4 tuple. How can we work around that? Well, we have this beautiful hack that Marek came up with, and I really tried to prove that it is racy, but it doesn't seem so, where we resort to querying the bindings over netlink and abusing the Rails address socket option. If you're interested in it, I highly recommend his blog post that I linked to. So one of the major jobs that the operating system has is to provide useful abstractions of the available resources to the user API. And it seems like today, opening outgoing connections from a selected port range is hard. So can we do better? Well, again, this we have already seen, and this is ideally what we would like to have, but without these downsides that I mentioned. So what if we could actually define or set the local port range per socket, of course still while respecting the per netns global setting, just to narrow down the ephemeral port range. I've given it a shot, and it actually seems it's pretty easy to implement. So I've posted RFC patches. Of course, we need additional fields in the socket object to store the low and high bounds, which is the biggest downside of this solution. Apart from that, we need some glue code, but it's pretty simple because we can actually stuff 2 16-bit values into an integer. And once we have that, when we need to find out what the ephemeral port range is, either at bind time or at the connect time, we just look up the per netns ephemeral port range and clamp it down to the values set for the socket. So that works for TCP, but the question is it enough for UDP? Does it work for UDP as well? Well, it doesn't, unfortunately. UDP, once again, is on another difficulty level. Why doesn't it work for UDP today? Well, you can set the IP bind address no port option for UDP sockets, but it probably doesn't work as you would expect. So setting that option will not lead to source port sharing, even if the 4 tuple of your socket is unique. Setting UDP bind address no port today on a UDP socket means that you're delaying the moment of auto binding the socket from the bind time to the connect time. So can we make it work? The delayed auto bind happens today in the connect handler if we detect that the socket doesn't have a source port selected yet. And we're going to delegate that operation to the get port protocol operation. For UDP, that protocol operation is implemented by UDP lead get port, which is a pretty long function, but in general, it has an if statement that handles 2 cases. First one where we don't have a source port yet, and we want to find a free one, and that is what we're interested in. And the second one, which we're not going to be looking at today, if the user has specified the source port, and we just need to check if it's free. Both of them are followed by a common block that just publishes the binding. If we look at how UDP today looks for a free source port, we're going to see that, well, we're going to pick a number at random, generate a source port from it, and based on lower bits of the 16-bit value, we're going to find a slot in the UDP hash table and walk all the sockets in that hash table chain to find which ports are already busy. And we're going to build a bitmap that marks the busy ports. Then we're going to try our port picked at random and check if it's free. And if not, we're going to then check another port, but one that maps to the same hash slot table so that we can reuse the bitmap that we have just created. Only after that, we're going to move on to the other slots in the hash table. The function that is responsible for walking the chain of sockets in a hash slot is called UDP-lib lport-in-use. And what it will do, it will look at the various attributes of the existing sockets, like the network namespace they exist in, their local address, the device they are bound to, if source port sharing is enabled. And based on that, it's going to make a decision if that port number is actually free or can be shared maybe, or if it is already exclusively owned by an existing socket. So why am I telling you about all this? Well, it seems like we can use all this battle-tested code to make IP bind address no port work for UDP, because we are really trying to do the same thing. We just want to be a little bit stricter about detecting the conflicts. So instead of using UDP-lib lport-in-use, we need some new function. One that would be very similar to lport-in-use and would look at all the same attributes, but in addition to that, we also have to pay attention to the destination address and port of the existing sockets, connected UDP sockets. All right, seems like we have an idea what we want to do. The question is, how can we implement it? Well, we probably don't want to change the signature of get port because that has various users, and unfortunately it doesn't have access to the address that the connect handler gets from the user. So we probably need a new protocol operation, one that has access to the socket and the address passed to connect. Well, as it happens, there already is a protocol operation. I've just learned about it recently that we can reuse. It is currently only used by SCTP code, and it's called bind add. So how can we glue that into the connect handler if we put all that logic that I just described in a bind add implementation? Well, a reminder, this is what it looks like today. And we can imagine that we're going to extend that so that when we are doing a late auto bind at connect time, if some condition is met, we're going to delegate to the new handler, which is stricter about finding the source port. And if not, we're going to fall back to the behavior we have today and delegate to get port. What is that condition? Well, it has to be something that is backwards compatible, obviously. We can't make it the default. We can't break today's behavior. So what I would propose is to require a combination of reuse address and IP bind address no port set at the same time. And I'll explain why in a minute. Also, this would only make sense if the user has already selected the source IP address, because the connect handler gets called before the egress routing lookup. So we can't accept a wildcat address because we haven't selected a source address yet via routing. So why would it make sense to check for this combination of two flags? Well, that's because if you enable reuse address on the socket, setting bind address no port doesn't actually change anything for you. You'll still today get two conflicting sockets bound to the same 4 tuple. You won't get notified of the conflict. And if we change that behavior so that conflict is reported, you are very unlikely to hit that, because you would have to hit a conflict with an existing connected UDP sockets only run out of ephemeral ports. Yeah, one more thing I wanted to mention. I just posted patches for RFC patches for discussion for this morning. Yeah. So these are most promising solutions that we think, but they're definitely not perfect. So we've been thinking about some alternatives that I want to quickly mention. So if we don't want to fix IP bind address no port, we can go for a lighter option and just give users means of detecting conflict when we're creating a connected UDP socket. And for that, we could introduce yet another socket option. It would be kind of silly, but it would do the job, where the user creates a UDP socket, sets reuse address, which in UDP lingo means, hey, I'm about to create a multicast socket, but then kind of changes their mind and said, no, I actually want a unicast socket. Please tell me about any conflicts with other connected UDP sockets. Yet another direction we could go to is we could leave all the baggage that we have, API baggage that we have today behind, and perhaps prototype a new syscall and define semantics from scratch. It could be inspired by ConnectX syscall from Darwin, where we specify both the local address and the remote address. And of course, we also tried to solve it with Bpf, because if you have a hammer, everything looks like a nail, right? We can attach a BPF program to connect cgroup hook. And that program could actually take a look at the value, at the address the socket is bound to, and at the address the user passed to the connect syscall, make a socket lookup from the BPF context, well, and then check if there's a conflict and fail the connect syscall if that's the case. And that can be done, but we have found that this solution is racy because the BPF hook is actually pre-connect. So we have no control over processes trying to bind to the same address. We are not able to synchronize the publish step of this, which happens after the BPF hook. So for that to work, we would probably have to have another post-connect hook like we have to cgroup post-connect hook like we have today for bind, so that we can implement some synchronization via BPF maps and log a range of addresses for the duration of the connect and then log them once we're done. Right, so yeah, we have a couple ideas there. We have posted patches for what we think is the most promising direction. But the big question is how we can actually make the API support this use case better. And with that, I want to thank you for your attention, and I am all ears for your ideas, feedback, and questions. Thank you.
About post-connect, there is now a post-connect hook. I'll talk about it soon. So there is a LSM per cgroup post create, and there's might be something post-connect. So maybe that should be enough.
Yeah, I think we've chatted about this on the mailing list, yeah.
Yeah, but I like the API. I think if you can do it without all those BPF, it should be easy. I guess specifying the range seems natural.
I just have a question about the number of sockets you expect to use this 512 range for a particular server. Because at the lookup phase on the ingress path, we are going to scan a big linear list. So I was wondering about the performance of that.
Well, we haven't seen an increased load in the interrupt context with the flows we're having today. I mean, obviously the quick traffic is still on the rise. So as we see more and more quick traffic, perhaps that will become a problem on the ingress, but right now it has been working well enough for us.
But quick server are very different because they are using the connection identifier to do the demux.
Yeah.
You don't have one socket per flow because that wouldn't scale.
Yeah, that's true. The quick user can roam between source addresses, and that's why the connected UDP socket is not an exact match for the quick use case. But that is what we are using today because it allows us to not have a demultiplexer for UDP traffic in the user space, and the threads can have a socket that they just use. Well, all right, let me take a step back. So this is egress flow we're talking about, right? So we are the client connecting to the destination, so we don't expect to roam from one IP address to another. That's why connected UDP sockets in that case makes sense for us.
Yeah, I'm always worried about UDP needs. Because right now we don't have the full hash table, like 4-tuple hash table.
Right, yeah,
There is only a 2-tuple hash table. So we have to look up a potentially very long list. And so I'm thinking about maybe in the future we want a full 4-tuple hash. So maybe that's the next step. And then all these issues are
yeah, exactly.
Second order will just disappear because when you do full connect, you do full lookup and then find us. But
exactly, yeah, I was looking at introducing the 4-tuple hash table, like we have the e hash for TCP, for UDP as well, but that seems like pulling out the big guns. So for
Maybe
now,
not,
I
maybe
resorted
not.
to something simpler.
There's also another question I had. The changing the port range, ephemeral port range, is already available per namespace. So you also could use a different namespace
All right.
for your application. You don't need to change the default host setting. You can have a application one.
That's true, but that comes with a challenge of setting up routing outside to route traffic outside of a dedicated namespace and back into the namespace. That's the overhead there. And we try to, well, most of our services run in the initial network namespace. We don't have like a containerized workload on the edge.
I think that the whole ConnectX idea is a non-starter. It seems to have a severe case of argument diarrhea.
Right. Do we have any more questions? Anything on the chat? Well, you can reach me and Marek via email, we are on Twitter. So yeah, if you have any ideas or questions, we're happy to chat afterwards. Thank you.
Hello, my name is Stan. I work for Google in the host networking team, mostly working on the kernel in Bpf. Today I'm going to talk about Persigloop LSM and how and why we've decided to do it. I'll start from the beginning. We basically run a lot of containers. We run them on the same machine. They have multiple workloads. They have different policies and priorities. Think about like we can have some batch jobs sending some batch traffic, and we have some front-end jobs and serving some user traffic, and we want to have different policies for them. This is orthogonal to networking namespaces. This is about enforcing the policies. This is not about like isolating them. We have some tasks that run in the networking namespaces. We have some that run outside, and we basically want this enforcement for all of them. From this networking resource control, what we want to have is we want to have some unique identifier. I think for cgroup v2, it's like a cgroup ID, but unfortunately, we're a bit stuck in the v1 world, so we cannot directly use it. Another thing we want from this resource control is we want to enforce socket options. We want allow some socket options. We want to deny some socket options. And we also, for some legacy reasons, we want to some control over socket and bind syscalls. For example, can the application use v4 sockets, or can the application bind to this specific port? This policy is coming from some, I don't know, big database, let's say. So upon the startup, we create a C group. This container management system populates some C group. We currently use for this a Bpf C group local storage. So we write some policy in the C group storage. We want some of this policy to be applied by default. So for example, when the job creates a socket, we want to set a priority to some value. We also want some policy to be applied only when the user decides to exercise it, say, while calling some setsock option. And more details about what we want to control. First one is a socket priority. This is, again, legacy. We used to use HTB, so we used to do this like classless HTB thing. So we used to carry this unique container ID in this socket priority. So what we want to do is we want to prohibit the applications to call it, and we want to set it upon creation. Long term, we want to switch to C group ID, but this is not the case right now. Another thing we want to control is IP toss. So whenever a container wants to use some higher toss setting, it can choose to upgrade. And then at Bpf level, we want to, we basically know if this policy is allowed or not. So we want to allow or deny it. Bind port ranges, we also, this is again historical, this is pre-namespaces world, and we still have applications that do this. Basically, when the container creates a job, it asks the job to bind to this specific port, and now we want to enforce it. Another thing we want to enforce is no IPv4. We run IPv6 mostly, but again, sometimes we want to allow it. Right now, we currently hide it in our legacy kernel implementation. But with Bpf, we cannot hide it, but we only prohibit it. And again, last thing is we want to control some Google-only options. We have Google-only as we, for example, I think last year, Brian talked about DNN cap and Bpf. So we basically have a way for the jobs to say, like, for this socket, encap this traffic with this header. And this is purely Bpf. This is purely Bpf setsec option. So we want also to let some jobs do it and maybe others not do it. Yeah, so we also want a mode for the last item, sandboxing. So if the job decides to create a new networking namespaces and do some other stuff with it, we want to let it do it without enforcing all the controls, because we know that this networking namespace is isolated. The job doesn't usually have like netadmin capabilities, so we don't want to apply any of that. So historically, it has been done in a very ugly way. We still have this networking C group in our prod kernel. It's a mix of the upstream net class and net prio, because we carry class ID through the socket priority, but we actually use it as a class. So we tried to upstream it a while ago. It's obviously not gonna fly. That's why we've decided to redo it properly. Yeah, that's me again. Basically, we don't want to keep rebasing it. We don't want, because upstream keeps also breaking it. We choose to also carry our Bpf through it. So we don't use B2 for Bpf. We still use our B1 for Bpf with a bunch of like custom hacks. So yeah, we basically want to be closer to upstream. There's nothing secret about that. It's just pure legacy code that all it brings is the headaches. So yeah, we're trying to remove it, replace it with Bpf. The data I'm showing today, it's not widely deployed. We do the experiments with it. We have some promising results, and I'll just show you the examples of the functionality. So what we started initially with, I was hoping that we can just do it without any kernel work, right? Martin yesterday talked about how we have all the hooks in all the different places of the networking subsystem. So I was thinking how hard it could be just to write a bunch of Bpf programs to, let's say, for this IP toss, we have in the C group local storage, we have, let's say, an array with port ranges. Whenever there is a bind or there is a setsock option, we just compare against the list. And this is, again, just simple Bpf programs, setsock option hooks, look up local storage. If this is the option that I want, I just call a function that basically goes over a loop, verifies that everything's okay. It works. Same with bind ports. There's already a bind hook, right? I'm only care about lower 16 ports. I'm not caring about ephemeral port range. I'm not showing the program. It's essentially very simple. Next thing is Ipv4 hiding. We used to do real hiding, as in we had a C group knob where you start a C group and you can say just hide Ipv4. So it disappears from procfs, it disappears from netlink. It still appears if you just disable it or move out of the C group, but by default, the tasks wouldn't see it. You can also, it will also return you an error if you just try to create Ipv4 socket. With Bpf, we obviously cannot do it. We cannot just hide it. I mean, technically, we probably can, right, by adding a bunch of hooks and all this control, but we don't want to do it. For Bpf, we're just returning an error when the users create IFI net sockets. I thought it should be fine until I discovered that Java has a very interesting code. It tries to create IPv4 socket. From Bpf, I return eperm, and Java says, okay, I'm giving up. It has this last line says, it will basically try to upgrade to v6 only if the error number is one of those for some reason. The interesting thing, this code also has been added by Googler, probably because of our prod kernel. Again, so this is leaking into the kind of real world, but this all depends on our custom networking C group. So yeah, we had to get back with this a bit, do Bpf hooks to support our writing this, and so on. So yeah, this is how it looks right now. Basically, if it tries to create it, we just override the error number, and this should make Java happy. And then the last thing is this socket priority, this net class ID that kind of we use. I thought there is the C group sock hook, which gets triggered upon socket creation. That's what I did, and it all worked nicely until I've discovered passive opens don't work, and other things like AF packets also don't trigger this. And then yeah, that's how it basically looked. A bit simple thing, upon creation, I just want to write it down. And then, yeah, that's where I hit the wall, basically. There is this hook, it mostly works, but doesn't. And then we've talked a bunch on the mailing list, the obvious solution, like, do we want more hooks? But I guess you've seen Alexei's talk yesterday about how we don't really want to have any more hooks. We want to move into this way where you can hook technically everywhere. And that's basically why we've decided to do the LSM per C group stuff, because there's already a lot of LSM hooks throughout the kernel. They all have like different nice contexts, and there's already Bpf LSM. So we've decided let's just allow those LSM hooks, but to use them per C group. Yeah, so it looks basically like any other C group hook. You call like attached to C group LSM, and you also pass this extra BTF ID of the LSM hook you want to attach to. We also exposed Bpf set sock opt helper for those LSM hooks to mutate the socket state. And this basically addresses our issue with sock create not triggering. Yeah, so there's a bunch of hooks already, socket post create and inet socket clone. The first one is called after the socket has been created, the active socket has been created. The clone has been called after the passive socket has been allocated. And basically, yeah, it looks like that, and the same for the other one. Another thing we want to have is we also used to have it in our custom C group. It's not really related to LSM, but we also kind of leverage it. We used to have a net raw capability called net raw xmit, but it's a net raw, but it only lets you transmit net raw. This is used in our Plumbers, where we have some jobs that basically send some front-end traffic and cap, and they want to basically test it. Yeah, so instead of adding, again, all this new capability, what we're currently trying to do is we're giving task net raw, but we also use LSMC group to use two hooks. First one is create. We make sure we don't let them create sockets with protocol 0, which means I can read I can sniff all the traffic. If the protocol is non-zero, it's like a transmission only raw socket. And we also prohibit rebinding of those sockets. So this is creation, simple, same with rebinding. We just see what they're trying to rebind to, and if they try to rebind to protocol 0, we again return the error. There is a lot of challenges with this approach. In general, moving from V1 to V2, because with Bpf, and since our container system attaches all this Bpf, the tasks, sometimes they want to know their own maybe like settings. So what they used to do is they used to go to the cgroup fs and read all those knobs. They cannot obviously do it anymore because it's a BPF map. They should have permissions. Up until recently, I think there has been, we're still using, we're disabling unprivileged BPF everywhere, but it has been reworked recently where you can do some BPF syscalls if you have the BPF object to work on. And the first item is fixed now. The second thing, again, some of our containers, most of our containers, they run user namespaces. And if they want to create a sub networking C group, they cannot do it anymore because cap BPF is global. You cannot grant it to the user namespaces. And that's the third point as well. All right, there is no way to create unprivileged containers for us anymore. I hope it's not a problem because with the V2, we're also trying to do hierarchical C group. So there's probably no reason for the tasks to create even more narrow environment, but we'll see. Another big challenge for us is actually hierarchy. Suppose we have this socket priority set sock option, and we have a parent C group and we have a child C group. And the child C group is calling this, give me my SO priority. So what happens is the child program runs, it fills in the buffer with its own SO priority. And then the parent program runs and it fills its own SO priority, essentially overriding the child one. So there is currently no mechanism to kind of pass the state between programs saying like, oh, you know what, I've handled this request. You don't need, the parent doesn't need to do anything. Instead, we rely on the hacky way that, oh, this value is non-zero, then the parent doesn't need to do anything. But I think we should do something better. There is a way right now with our set ret val, get ret val. You can kind of, this error case, you can skip if you know this, oh, there's some custom error, then it means it might have come from some other BPF program, so you can maybe skip it. But for this successful get sock opt, there's basically no way currently to pass this information. Another point I discussed is the challenges that this was unexpected, that the user space actually do depend on the specific error, no? And why? I mean, like, why not just retry anyway? And the last one is, we will probably talk about this maybe on the mailing list more. All the set sock option, it kind of works and nice, but there's also like a big hole in the send message. You can call send message with cmessage and pass IP toss, you can pass whatever, and it all just basically goes out of the window. So maybe hopefully with the like dynamic pointers, key pointers, we can actually now have some cmessage BPF program that can nicely access this area and in some efficient way. Because currently we hopefully can, we have a mono repo, we can search for those users. We can find there's like 2 of them that do those kind of things. But it still would be nice to enforce this. Yeah, I think I have with summary, yeah, so going back to LSM, we were able to cover most of the functionality with this. We're still experimenting. This C group LSM, it still has a lot of limitations. It's only non-sleepable. We probably need to have sleepable, but for sleepable, there is a bunch of roadblocks, like C group storage depends on basically not being sleepable, and there's a bunch of other places. So we need to fix C group storage first to be sleepable as well. We also probably need to have for LSM, we probably need to have some annotations for the socket arguments, because some of the LSM hooks, they work on a locked socket. The other LSM hooks, they work on unlocked socket. And basically there is right now no way, we have a hard-coded list of hooks that can use getSockOpt because we know that those places have locked sockets, but we need something more flexible and more reliable. Yeah, and I've listed some of the commits. It's been a long road, right? We started with like getSockOpt, setSockOpt. I'm not sure we started even for this, maybe for something else, but then there was this global C group mode, error null overrides, LSM C group, and then the last one, it's not really related, but that's kind of lets us so control more. And yeah, I think I'm probably running early, but yeah, that's mostly it from me. Any questions?
Can you go to slide 22?
52.
22.
Say it again.
22.
22.
So about the point that there is no way to create unprivileged containers, you mean that there will be some trouble with loading LSM programs attached to sockets for unprivileged containers?
No, imagine like I'm just a regular job. I just want to create this netc group container and maybe limit some port ranges or do something else. With the C group E1, we used to do it, right? Where you just change mode of this whole directory. You basically let the users manage the kind of the subtree, and it all works nicely. But this way, you cannot attach BPF to enforce any of that, right? So you have to have some system daemon that you maybe delegate this whole thing to, right? So you maybe need to call some RPC, say like, you know what, I'm creating this C group. Can you please set it up for me in this way? So again, it needs a different model from the one that we have. The one that we have, it kind of all depends on the C group if it has been available and unprivileged.
Okay, so there will be need for like centralized daemon running as root attaching to unprivileged.
Yeah, I guess in the like non-Google places, probably like systemd is this management process. Again, we don't have that, so.
Right, okay, makes sense. Thank you.
All right, thank you.
Thank you.
All right, we have one more talk before we go for lunch from Dave.
All right, cool. So I'm Dave Taylor from Microsoft. So I am one of the members of the BPF steering committee in the eBPF Foundation, and I've been doing IETF RFCs for something over 25 years, and so I volunteered to help with the eBPF standardization effort. So when we first talk about, give a brief summary of some of the recent discussion, right? We had a meeting on the BPF office hours time slot, and here's some of the outcomes of that meeting. There's a goal that says we wanted to have, and this came up at LSFM on BPF, says we wanted to have a set of standards documented for around eBPF. We have multiple runtimes, we have multiple verifiers, we have multiple compilers, and so on. It says, well, it sure would be nice if we could actually write down what the standard is, so as we have different implementations of things, they can all adhere to the same standard, so that compilers can generate stuff that can be used by multiple runtimes, and so on. And so in that discussion, we said we'd like the documentation to be upstreamed into the Linux kernel tree, right, which is where it kind of is right now, among other places. But we wanted the eBPF Foundation to then publish a PDF with version numbers, so like a snapshot of stuff with different version numbers that says this is the standard as published by the eBPF Foundation. Okay, so there's the source code that's in the source of the documents that's in the Linux kernel tree, and then the PDFs being the actual published standard, if you will, by the eBPF Foundation. We said the eBPF Foundation would kind of host this effort to document things, but that we would continue to use the BPF mailing list for communication. So we said, well, what would we actually standardize? What would we actually document? And so there's a bunch of different things that came up, and we said we were going to start kind of bottom up. So the things we were going to do first would be the instruction set architecture, the ELF format, BTF, some of the verifier expectations in terms of what does the ISA cover versus what does the ISA not cover and their verifier is responsible for. And similarly, compiler expectations. Okay, so we're going to start from the ISA first and kind of move up the stack, and then eventually we get to other things, maybe like program types and map types, and so on, that a number of the people in the community are actually arguing for. From a user perspective, they actually want the bottom ones, but we said we're going to kind of start from the bottom and work our way up. Okay, so that was the recent discussion that we had. So now moving on to since then, since we had the meeting, a little over a month ago now, there's work in progress. I tried to post to the Bpf mailing list, but it ate my mail back last Friday, so I reposted again this morning, and hopefully it all made it through, and you can find it here. But instructionset.rst is the file that's in the Linux kernel source tree that had an ISA which was had maybe, I don't know if it's errors, but it certainly was incomplete. And so we've had many other sites that have been shown up that have had various variations of the instruction set documentation. We're trying to go through all of those and collect the information and then update the original one. Because we want this to be a cross-platform standard and published in PDF, right? My goal was that the RST should be renderable in as many different RST viewers as possible. Okay, and so one of those being GitHub. And so I did a copy over into a GitHub repository that I have this my personal repository there, so I could see how GitHub would render things. And so that's the copy that I've been iterating on to make sure that it would render right under various RST viewers. And so I posted the mailing list. There's a GitHub diff that's like the diffs in the current version against the latest one, but then there's also the Git format patch that was sent to the Bpf list. So whichever way you like to see it, you can see the rendered copy. You can see the diffs in GitHub version if you like that. You can see the diffs in the format stuff if you just look on the mailing list. So my proposal is that once the stuff is eventually upstreamed into the Linux kernel, right, that the docs themselves be mirrored into a GitHub repository. Right? We do this for libBPF, we do this for Bpf tool. This then helps other consumers that aren't Linux to be able to consume those same sorts of documents and use different tools. So the eventual goal is that I mentioned that the Bpf Foundation would then publish the PDF, right? And so how do you generate the PDF in the RST? Well, you put the generation tool over in the GitHub mirror, okay? Similar as how we do with libBPF and Bpf tool right now, with a mirror repository just contains things specific to the mirror repository, not the authoritative sources, right? So that's the eventual goal in the proposal here, is to say we're going to create this GitHub repository under eBPF Foundation, and that's where we'll have the Bpf generation, or the PDF generation, and the published PDFs. Okay, but the point is you can actually see a rendered copy right now that I'm going to show you a couple things from. All right. So this is the current, so far all that's in there is the ISA, right? It's just the modifications to instruction set.rst. This is the current table of contents as snapshotted in the rendered version, okay? You can see a lot of those are in the one that's in the Linux kernel repository, which does not have the table of contents in it. We just added this to the RST. And there's a couple of additional sections here that we're missing in there that were copied in from various other sources, right? You remember yesterday there was a presentation that referred to the instruction set, but it actually linked to the Pchango version of the GitHub docs elsewhere, not the Linux kernel one. That's one of the many sources we use to pull together from this one. I say we thank you to Quentin and Jim for generating actual reviews and code, and for people like Christoph and Dave Tucker for generating mailing list discussions in the past that we used as sources. So. And by the way, part of the point of this is to call for additional volunteers. If you want to help with this, whether it's for ISA or for any of those other categories, please just contact me. We'll get you set up. All right, so let me talk about a couple things that are already in the diffs, okay? And then there's a couple of open questions that I would love feedback on, or reach out to me afterwards, okay? So the first thing, this one came up at LSFM and Bpf, which is pointed out that it said nothing about overflow, underflow, or divide by zero, and that's probably the lowest hanging fruit to go and fix. And so the text in green there is what it says right now. If you think it's incorrect, just tell me what it should say, right? But it's better to put something, right? That's the trick in standards documentation, is you put something down. And if it's wrong, people will tell you, and then you can fix it. So that's put in there. So you see, program execution must be gracefully aborted. That's what it currently says on divide by zero, okay? But it doesn't actually yet, one of the gaps is, it doesn't say what gracefully aborted means, okay? The previous doc, if you look in the Linux kernel repository right now, there's a similar statement talking about the legacy packet instructions where it says, If the eBPF program tries to access the data beyond the packet boundary, the program execution will be aborted. It doesn't actually say what will be aborted actually means, right? Does that mean you return back to the caller? What's the return code? It doesn't say, it doesn't cover that, okay? And so the point is that's another gap that we need to figure out what's the right thing to say there. So if you have thoughts on that, text contributions gratefully accepted, explanations on mailing list welcome too. So that's what it says right now. So that's one step that's improvement. One of the other things that people were asking for popularly was to have a table of all the opcodes, because you can kind of derive it from other information, but having a quick lookup table. This is in the appendix because this is not what's authoritative. What's authoritative is the text in the body of the document. This is the summary at the end. It says, if you just want to know what opcode hex 15 means, here's the simple place to find it. And you can then have the link that jumps back into the document that contains the formal definition of it. Okay. And so if you're just trying to say, what is that bytecode right there? Well, look it up in here, and then you can jump to the correct section of the document. So it's all the ones in here. I just snapshotted just what would fit on the screen here, but it continues on all through the rest of the opcode space. All right, so now I'm going to go through a number of open questions, and I'm hoping we can have some discussion, because otherwise this will be real short. So, all right, so here's some open questions. Now you'll notice, I thought there was another slide in here. Well, I'll just talk about it then. I think on when I thought there was a different slide. Okay, all right. So in the document right now, because it's a standard that's intended to be cross-platform, okay, right now it uses the standard types uint32t, etc., not u32. Okay. Now, of course, in the Linux kernel, we always use u32 and so on. Okay. So here we have a Linux implementation note that says in the Linux kernel, uint32t is expressed as u32 and so on. Okay. And explains that since this is a standard document, that's just what Linux does. Other platforms could have different variations of that. Okay. The point is, we put in a Linux implementation note here. So the question is, in a standard here, do we want to include Linux implementation notes and CLang implementation notes? Okay. Right now, the answer is yes, it does, specifically for things like this, in order to translate between what was in instruction set RST before and what would be in a cross-platform standard. You can say, okay, if you have a Linux document and you have the eBPF standard, right, should that be the same document or two different documents? Right now, the proposal is it's the same document with just Linux implementation notes in it. Okay. You don't have to have one that refers to the other, but you could argue the other one too. But right now our approach is anything that was in there that was really specific to Linux is now in a Linux implementation note that looks like that. And also across the different other instruction set documents that were out there, there was a number of CLang implementation notes. And so we put those into notes that look like that. So for example, how you determine whether you have the 32-bit ALU operations, here's the Clang implementation note as to how to do that. Okay. We could have dropped that. We chose to put it in there because it was popularly referenced in their documents. So if you have feedback on that, but right now the proposal is yes, and it will look like that. Different question would be, so what happens if we wanted to have, GCC implementation notes or Windows implementation notes? Do we add that into there, or is that out? Open question, if you have thoughts on how to do that. Right now, the straw man is Linux and CLang is in there, and other ones are kind of open as to whether we keep those in or out. I'm going to keep going, but these are things that I would love feedback on, because otherwise I'm just going to make some arbitrary choice and hope that Joel can live with it. So by anybody else is contributing and generating pull requests and things. So, all right, so the next interesting question is, how do we deal with input arguments to eBPF programs? Okay, so on Linux, right, you just have one register used as the input argument, but that's a convention, right? That does not necessarily apply to other runtimes. Windows follows that same convention if there's only one, but if you look at like eBPF, right, because one of the people that's reviewing and stuff is one of the eBPF maintainers, eBPF actually differs, we learned, this was surprising to me, between the JIT compiler and the interpreter in eBPF. One of them uses one argument, and the other one uses two arguments, okay, which is the second argument is the size of the context field, right? So the first argument is always the same, but it also has R2 that's filled in with what's the size of the point of the structure pointed to by R1. Okay. And so right now the straw man is to say, what if we say that it looks very similar to how helper functions work, okay, where the helper function can vary by platform, but the details of how many different arguments there are in this meaning is up to the helper function. Okay? We could say, well, it's actually up to the program type. And by just so happens that all the program types on Linux and technically on Windows all have a single argument. But some runtime could define program types where the number of arguments vary by program type, just like they vary by helper. That's the straw man that's in here right now that says this seems to be fairly flexible without actually making anything invalid, and probably would even cover cases like eBPF and any other, I don't know what HBPF does, the one on offload cards and so on. So previously in the document it talked about the Linux part about there's only R1 was just in the body, and we moved that into a Linux implementation note because we found cases like eBPF that I mentioned, which actually did not follow that convention. Okay, so we said, well, the standard is kind of the lowest common denominator, and the note about only using the one is kind of a convention used by Linux that not everybody apparently uses. So that was news to me. Yeah, so you can see the actual number of registers used and their meaning is defined by the program type. This is the straw man. A networking program might have an argument that includes network packet data and or metadata. We tried to copy language as close as possible out of the other documents if it wasn't already in instruction set RST, then one of the other things that was listed as a reference. Now I get to the two most difficult ones. Okay, so here's one, legacy packet instructions. There is text that's in there right now, and I'm not sure that it's right because there was discussions on the list over the last year about what to do with this. So right now, what the document does is it says, well, let's try to abstract it from Linux and see if people like it, right? Because we could just remove it or whatever else. So what it says right now, okay, and the red parts is the most interesting parts here. So I'm just gonna look at that. So legacy packet instructions are ones that actually, the instruction set architecture knows that there's a packet that's there, okay? It says when the program context contains a pointer to a networking packet. So what the original doc said is it had an skbuf, right? Well, skbuf is inherently Linux specific, right? But basically anything with a networking stack has a networking packet and something that actually contains a pointer to it, okay? So if you said, well, what would another runtime do with that instruction if it ever saw it? It wouldn't have an skbuf, but it could still do something? Absolutely. We just have a different offset or a different structure, but it could actually find a data structure that's in there if it was during the instruction set architecture, okay? So it says, okay, if you can tell that the program context contains a pointer to a networking packet, then the legacy packet instructions could, in theory, make sense. You see, R6 is what has the context. It says a pointer to a context structure with a packet data pointer. Okay. Now, in previous documents that said contained a pointer to an skbuf or whatever. This is an attempt to abstract it from saying skbuf to something where skbuf is the Linux instantiation of the packet data structure. So you can see the Linux implementation note that says, on Linux, that thing is an skbuf. Other proposals that came up on the mailing list was, well, should we just remove the stuff and say these are deprecated and they don't mean anything, or they're up to the implementation, up to the runtime. You can do whatever you want with these things, right? Which probably is less interoperable than actually the approach I tried to take here. Another variation where this was the posting on the mailing list between, I think it was Jim Harris and Christoph, where maybe you do it as an extension or something like that. And you can have different things that claim to support an extension. Okay. So far in the ISA document, I don't have anything that's the concept of an extension. If we could. And so whether you think it should be moved to an extension, whether you think it should be deprecated, whether you think it should be implementation defined, or whether you like this approach that says, well, it's just kind of generified, even though it's deprecated, right? Such that the instructions could be used on some other runtime. This one, I guess, is my preferred approach, but I don't feel strongly. So if somebody has a strong opinion or a good reason to not do it this way, just if there's something broken here, let me know. But this is one of the things that is kind of a big open question because there was this discussion on the list that hasn't really been resolved. Right? So I'd love some people have strong opinions on this one. Yeah.
So I was wondering, so with the skbuf, I think there's not always a guarantee that the network packet data is going to be linear in that buffer. So I'm kind of wondering if there's an implication that we're adding here by saying this is a networking packet. Like, are we saying it's a linear set of bytes and so on? Like,
So it actually looks at the offset, and then it also can copy stuff from the non-linear data section. But I don't know. Do you think, like, if we don't even mention it, that we would still comply, like comply to the standard, or would we have to, when we want to create a standard, make an exception and say there are some, deprecated implementation specific exceptions, like, like this one here that you just show?
Yeah, you can see, the state, I don't remember if this one was Jim or Christoph, it might have been Christoph that said, the standard might say implementation defined, meaning that different runtimes don't have to support them. But if it's implementation defined, that means that your compiler can't actually generate something unless you have implementation stuff in the compiler, right? And so, not sure what to do there. Especially so you start having other compilers besides Rust.
This part, like, yeah, I would leave it, like, I wouldn't put this kind of stuff into common document. I would just say, yeah, implementation defined without going to the details. Because it's then like, yeah, what is this KB? Whether it's linear or not, it's like way too many questions. Plus, we don't really abort. So same for the divide earlier, which is already a bug in a document. Like divide doesn't do any abortion, it just like returns 0.
So what are we arguing for here? Are we saying to make them be implementation defined, deprecated?
Yeah, like just implementation defined. Like, because just saying it's undefined would also be not quite correct. Like we are, like on Linux, at least it will stay this way, this Bpf int and apps ugliness. So yeah, just say implementation defined, but don't like, it's just like, I don't see the value of defining them in a standard.
2 other hands up, so, okay. Thank you for having actually discussion. This is what I wanted. So yeah, I have one other big question too, but let's get to this. Feedback on this one is like super valuable. And then I have one more after this one that I would like to have discussion on too. So yeah, please.
Yeah, so if we make this implementation defined, does that mean implementation could come along and reuse the opcodes for something else? Or would we want to say,
yep,
this class is actually reserved, you shouldn't use it for anything? And like, I guess it kind of goes to the question of, do we specify the full ISA and say you're not allowed to add your own opcodes to it? Or can an implementation say, how? I kind of want this nifty thing here. But I mean, my personal, I would prefer if we said, don't put any of this in and just say these classes are not to be used and other things will have to be documented later or specified later.
Yeah, I think that would be consistent with saying they're implementation defined and deprecated, meaning nobody should use these for anything, right? Some implementations did, but compilers should never generate these in the future, right? And you get what you get if you try to use them. You can't rely on it being interoperable or whatever, so please don't use them. But some things did.
Yeah, so we can say like reserved, I guess.
Yeah. Well,
so that means like you shouldn't implement because it's not specified what it is.
Reserved still encourages people to squat on them, and so I would say deprecated, please don't use, kind of thing.
I mean, like we can leave the note that like Linux historically supported it, but like that's definitely a legacy that like we wouldn't implement if we were like implementing from scratch.
Okay, so I'm gonna come back to that, but I can go here.
So I came in a little late, so I probably missed something. So my question is like, is this program type part of the standard? I'm asking because this is kind of, well, to me, it's like you get a program type, you get a context like this. It's kind of tied together, right?
I'm going to ask you to hold that question until the next slide, okay? Because I said there's a second thing. I'm going to come back to that, and it's going to be very relevant to the next slide. So I did want to answer one point on Andre's thing, which is if this gets removed from this document, okay? So if I go back to the slide that talked about this one, okay? Today, this is being done as a replacement for instruction set RST. In other words, these are patches that would actually modify that file. Okay. Now, if we remove it, that means that there is no file that actually documents this stuff. Okay. So that means maybe we do want to have a separate file that contains Linux-specific, extensions. Just to use, I think it was Christoph's term, right? It says, okay, maybe the legacy ones move into a separate file. This Linux deprecated extension, something like that. So the instruction set becomes the generic stuff, and then a separate one has deprecated stuff that's Linux specific.
I'm a bit worried about like extensions, because that sort of will encourage other implementations to start creating their own extensions, and like that's probably what we don't want. So it's like maybe Linux specific, historical, whatever, but like not an extension.
Yes, I agree.
Baggage, yeah.
Okay, okay.
I have one more question regarding the division by zero. Can we just standardize the way what we currently have from Linux? Does there speak anything against that? I mean,
if somebody wants to write up text and submit it to me, then chances are yes.
all right.
It's what? Meaning set the return code to 0 and return, or what? Oh, just set the value to 0. Gotcha. Okay. Yeah. See, I didn't know the answer to that one. So if you tell me what it is, I'm happy to put it in. Yeah. If you said divide by 0 equals 0 and then continue on instead of gracefully aborting, then yeah, happy to change it to that.
Yeah. I mean, for the case where we cannot verify it at load time, then we adopted the same thing like ARM64 did. So to not throw an exception, because when you have BPF to BPF calls, there's a certain return type expected. Now, when you have like some kind of abortion, then this conflicts with the verifier, for example. That's why we did that.
Yeah, so my preference is to, yes, let's have the same behavior across runtimes and standardize it. And if that's what the answer is, then let's just make sure that eBPF and other runtimes do the same thing. So we got a eBPF maintainer on the list of stuff here, so we can get those changed.
So what happens with the second part, packet boundary? Like when has data beyond the packet boundary? Isn't that like the statically verified?
I'm telling you what the document says right now. What happens, I can't comment on what the document says right now.
You don't have abortion, right?
Is that you gracefully abort, and I think in somebody's presentation, maybe it was yours, talked about like detaching yesterday. If you see something weird happen.
Yeah, we don't have graceful abort
yet.
Like as what Daniel explained, like there's no way to, well, that's why like we changed divide to do this, like it just like return 0 and continues, because we cannot just like exit.
Okay, so the sentence at the bottom is the one you're talking about, and that sentence is actually in the legacy packet section. So if we take that out, then that part gets resolved too, right? By just moving into the legacy section, although the legacy historical note or whatever we call it, however, we'll have to fix that sentence, right? Just won't be in this.
Yeah, even if you move, it's probably better to like specify what actually happens.
All right, so I want to get onto my last slide, and so this will get to your question about program types. Okay. The other big question is, here we go, other wide instructions. Okay. So Quentin nicely posted a pull request to the IOVisor eBPF docs that had a bunch of great reference information in there. And so there's other 128-bit instructions or wide instructions that use additional information. And you can see a little snippet here from what's in Quentin's pull request. And so all of these, the definitions of that now use the source register field in addition to the immediate or whatever fields. To distinguish what that instruction does. You can see the definitions, at least in his write-up, it uses things like, mapfd, uses BTF ID of variable, map index, BPF callback, and so on. None of those terms are mentioned or defined in the instruction set. Okay. So here's an opcode, or at least an instruction type that has a particular meaning that is specific to BTF or maps or so on, where the instruction set does not define the concept of a map. Right? That's at a higher layer. Okay. So here are we polluting the instruction set with these higher ones. How do we deal with this issue? Right? Where you have sort of upwards dependencies in the layer that says the instruction is defined to mean something about a map that has no notion in the instruction set. Okay. This is the one that I'm really scratching my head. Just says, okay, what do we do with this? Okay. Because these things will be defined in other documents, right? But do we have sort of upwards references or what? So I'm looking for ideas on this one, because your point about does it define program types? No, there's no definition of program type in the instruction set. Okay, that's a higher layer on top of the instruction set. Should there be? Well, you tell me. It's the same as the answer to these. Should there be a concept of a map FD in the instruction set? Okay, or is that a layer on top of the instruction set? Right? I would have previously. I didn't know about these instructions. They're not in the instruction set RST right now, right? That's why Quentin sent the pull request, right? Is none of these things are mentioned there. Do they need to be?
Well, it's because instruction set by itself is not sufficient, right? So like you'll need to define like the environment.
Yeah. So, but here there's specific opcodes or semantics of opcodes that actually depend on these other concepts. That's what's weird in these wide instructions. This doesn't exist any place else in the opcode set other than right here.
Like we do expect to document the like environment, sort of like the higher level concepts as well, right? So
yeah.
If there is some reference to an existing higher level concepts as a temporary solution, that probably is fine, no?
Yeah, I mean, a couple of these, there might be a way around, sort of. Like if you look at, let's say, the top two, right? You can just say destination equals the immediate and destination equals the immediate, but it means that the immediate is a map FD. Okay. Well, if the instruction set, interpreter or runtime doesn't know the difference between an integer and a map FD, that's at a higher level. You could collapse the instruction set definitions of those first two into the same meaning. They mean stuff different to the verifier and the JIT compiler and so on, but the instruction set architecture, they mean the same thing. You're going to do the same thing with the registers themselves, right? With the top two. So maybe there's a way of trying to splitting that to say there's things that are maybe verifier and set expectations versus things that's just what do I do with the registers? That's my only thought off the top of my head. But other than that, I'm looking for ideas on this one. So, okay. So let's go back to your question. So I was kind of come back to you because you want to talk about program types, which is kind of in the same category as all these other things down here, like mapFD.
So I kind of think they're different. Well, like maybe just my understanding may not be the same as others, but I think like map ID, BTF ID, like a program ID, or index or ID, or like a callback. I think there's going to be a BPF program ID. I think that should be part of the instruction set. Well, program type is kind of something we can take out.
Yeah, you can argue that the program type is a lot easier to deal with at the instruction set definition level.
Yeah, I mean, these ideas, I don't see a way to take them out. We want the ID in the instruction.
I think that's right. I think there's a good argument that you're making that the program type is more like a helper ID in the sense it defines a prototype and some semantics to go along with it. Just one is calling in, one's calling out, or whatever. And it does talk about helper IDs because there's the call instruction, right? And so you have to document that. And so I think the notion around like back here when we talked about how many different input arguments here, where we have program type. So I think we could deal with program type fairly naturally. It's the other ones that's like map FDs and so on. Does that have any impact at the ISA level? So yeah, I think you're right.
So we have a comment from the chat. Max Tottenham says, is this not similar to how the x86 ISA defines a GDT for the load GDT instruction? And I take that to mean maybe say these other bits, if source is not 0, then to be defined later, I guess.
Okay.
What do you think?
I don't know the specific example he's talking about, so but suggestions appreciated. So if that translates into a particular way to word this, that's fine. I just don't know that specific example.
So one of my concerns and the reason why I put in these instructions to Dave is that the document otherwise specifies that the fields that are unused by the instructions, so the source and destination and offset fields in the encoding of the instruction are to be set to 0 if we are not using them. So if we keep that constraint on the ISA in that Linux uses some source field, for example, for this instruction in particular, then in that case, we're not strictly compliant with the specification.
Yep, that's right. And just to repeat that, these wide instructions are not currently compliant with instruction set RST. Instruction set RST right now disallows these wide instructions that have been implemented, okay? Meaning we got to fix the instruction set RST, right? That's the point here.
Couldn't we say, like, for the specification, I mean, to abstract this, concept of FD away and saying it's like a non-zero identifier, and whatever that means is like platform specific. I don't know like how it looks in Windows actually. Do you also have like file descriptor that you pass down in there or something else, or?
To answer your question about Windows in particular, in Windows there are IDs, so like a map ID is the same, but the FD, whether it's maps or anything else, FD has no concept in the kernel. It uses a handle. In other words, it's a 32 or 64, depending on the architecture, bit number, rather than an integer, right? And so it's up in user space is where you have a mapping from an FD as used by clibs into a handle, and then the handle is what's used to transition across the user kernel boundary. And so in the kernel, it's all handles only. And so the FD doesn't actually have any existence in the kernel, right? IDs do, and so IDs is what's actually stored just like in Linux.
So in this case, we have like a non-zero ID for an object of a map.
But here we'd have to define a map object at the ISA level, as opposed to defining it over in a different document that sits on top, that map types and program types.
There is also very strong assumption that this whatever FD or ID will fit in 4 bytes. So that probably should be part of the specification, and that will cause troubles to Windows, but that's life.
Okay, so we're about, let's see, we've got about 2 minutes, I think, left in our usual time. So if we still have another question or comment, we can go for more, because this is really my last slide, right? So if there's any other comments on this one. So I guess right now I like the suggestions, maybe if there's a way to say, the ones that introduce these other concepts, if there's a way to say that they're maybe up to the implementation, maybe we could do something similar to the legacy ones, but that says it's more like legacy and varies. So if you have a compiler that tries to generate, source equals, I don't know, let's pick 4 this time, right? Where Bpf func in the instruction offset of Bpf callback, right? Well, what does that mean? Can we write that up in some generic fashion? Or is that something that says, well, if you generate that, it's going to be inherently runtime specific, right? It's going to only work on Linux and not eBPF or HBPF or Windows or whatever, right? Or is there a way to abstract that encourages it to be implemented the same way by multiple runtimes, right? Which then makes it much easier to do compilers, because now you can write it once, and it doesn't matter, that you have more portability. So if somebody's familiar with those and wants to take a shot at saying, well, here's what the generic version would be, then we can maybe figure out what document it would go in, whether it's this document or whether this is create some slots that may be plugged in by higher level things that says, here's the map specification, and the map specification uses, the source equals 2 here and source equals 5 and 6 with the following meanings.
So maybe just like worded generically that like LD IM64 with like non-zero source is used to refer to some entities defined by the environment, like, and just refer to it and like get something about it, and then like that will be specified by the environment specification.
Sure, I'm saying you can do that. I'm saying the only disadvantage is now if it's specified by the environment, that means if you're writing a compiler, then you can't generate these instructions unless you know specifically which environment it is, right? You have to turn on an option that says, I'm generating it for Linux, so please allow to include these instructions.
I don't think Clang right now generates anything. Like it generates zeros, and then we have relocation, and then it's up to like eBPF, for example, to fill it in. So compiler doesn't know about any of that, I think. Maybe about like function of set.
I would love to have the compiler person tell me what Clang does. I mean, because this is generating the source value, right? The value in the source field of the instruction. So similarly, if there's a way to turn on and turn this off in say LLVM to say generate or don't generate, sort of like the plus ALU32, if there's a way to do that, it might be useful. So I'd love to hear about that. So.
But I also wanted to check about the input arguments. Like, should we specify actually that it's only one R1 for the context and that's it? Because otherwise, similar as with extensions, right? Like some custom implementation will go crazy and like specify up to 5 input arguments.
This one I do have an opinion on, only because, first, that was my original thought, and I actually wrote it that way the first time when I was updating this section. And then the different reviewer said, this is actually not right. Did you know that that's just a convention? So I learned, because I thought that this was kind of baked in and everybody did just one, and that was just how it was. And what I learned is that's not the case. People don't do it that way. And in fact, there's no real reason for that other than convention, right? And so that's why I specified it this way. It says, okay, if somebody wanted to define, program types on some platform, and maybe we won't have new program types on Linux, but somebody else could have program types, right? That's not part of the ISA. And they wanted to say it's going to vary by program type, just like the number of arguments varies by helper function ID, right? They could do that. It would actually work. So I didn't see
Yeah,
a
but
reason.
do we want to create this divergence? That's the question. And like that's the point of the standard, to actually keep it like uniform and simple instead of like, because you know, like it will go into the area where like, oh, it's implementation defined and like it's unspecified, like with C undefined behaviors, and that is crazy.
So because I was arguing exactly what you were arguing before, now I'm trying to channel others, right? So keep that in mind. But I think one of the arguments that I heard was, if you think about the eBPF example, that says if they use R2 for the size of the structure pointed to by R1, okay, that actually makes a number of things be a lot easier, right? And so I say, no, you can't actually use R2 that way, then it may prevent some implementations on some types of platforms or compilers or something. So again, that's I'm not authoritative on that part. I'm just kind of relaying what the feedback that I heard was. So something to think about. So I don't have a strong feeling on this one. Like I said, I originally wrote it exactly as you're saying, and then I had to change it. So, all right, I think we're about out of time. But anybody else that wants to participate in this effort, either post a list, send me email, comment on the private or my personal GitHub repository right now. I thank you for all the feedback. Great stuff. So.
All right, thank you. So now we have a lunch break and we'll come back at 3.
We'll have multiple copies. It's just like number 1 out of a set of
All right, so let's start with the next session. It's held by Toki about adding packet queuing to XTP.
Thank you. Hello, everyone. Before I start, a show of hands, how many people of you regularly think about queuing? That's pretty good, because otherwise it would have been this situation. So I'm going to talk a little bit about XTP and how to add the capability of queuing packets in the XTP forwarding path. And I already got a question before this talk, which I'm actually going to address as the first thing. Why? Why would we do this? Why does XTP need to queue packets? So I'm going to come back to in more detail how the XTP forwarding path works, but this is sort of a bit of a contrived example. We set up an experiment where you redirect from 100 gigabits into 10 gigabits using on the green line the regular Linux path, and the dotted line is XTP forwarding. And as you can see, a single TCP flow cannot fill the pipe here at all, because there's no buffers. Like basically forwarding with XTP is today kind of similar to a very shallow buffered switch, where you have no way to store packets, you just send out, and this works as long as ingress and egress has the same speed and you can keep up. But as soon as you have a rate transition or anything other than that, you start dropping packets, and this does not work very well for TCP. Also, there are some other use cases where we can get new things when we can queue packets. So anything related to packet scheduling policies like flash queuing, QoS, reordering packets of any kind requires the ability to queue packets somehow. Bandwidth shaping is another thing, where if you have either a very small box like a home router that you probably have at home, everyone, and probably runs Linux, and you probably can't keep up with the internet speed these days because those go up. So we can accelerate forwarding on the edge with XTP, or you can have a big box in a data center that shapes 1,000 customers and an ISP, and you want to do policy shaping here. You can also do things like network emulation, reordering, delaying packets, all the stuff that QDish do in the regular stack, right? But accelerated with XTP. And then there's also like the last one is a bit more speculative. You can do custom buffering schemes where, say, you have a CNI plugin like Cilium, and you want to support something where you spin up containers when a packet comes into a particular service with a buffering scheme in XTP. You can do this there and then just hold on to the packet a little while, wait for the container to come up and send them in. But that sort of, those kind of use cases I'm sure will appear once we add this. At least I'm hoping so. So just to review in detail, how does the XTP redirect path actually work? We start up here in the top left corner, where in the driver, packet comes in, those are the solid lines, goes into the XTP program. XTP program uses the Bpf redirect map helper here, which all this really does is it populates this Bpf redirect info struct, which is a per CPU struct, and then it just returns, and it returns XTP redirect if this worked. And then once the XTP program has exited, the driver will call XTP do redirect, which does the actual work of redirecting the packet. And then for the forwarding case, like XTP do redirect is really a demuxer on all the different types of redirect you can do, which is pretty neat because then we can add new types of redirects without changing anything in the driver. And devmap and queue is the thing it does when we are forwarding packets. So what devmap and queue does, it actually just buffers the packet a little bit. It puts it into a bulk queue that can hold up to 16 packets. So this is the very shallow buffered thing. And this thing, like the gray area here, is then repeated for the whole NAPI loop. So we actually just put it on a bulk queue, and we wait down here until the driver is done with the loop, and then it does flush. And as soon as we do flush, we go into the XMIT part of the devmap thing, and that will just call NDO XTP XMIT and put the packets on the wire. And as you can see on the outer dotted line here,
this all happens inside a single MAPI cycle in a single soft IRQ. So it's all pushed through. And if at any point during this time, for example, if the TX side buffers are full, if we can't transmit the packet, it just gets dropped. And this is also like, there's trace points where you can see packets getting dropped, but one of the pitfalls of XDP redirect is that you get some really nice numbers for how many times you can do this bit. But once you actually get down to transmitting the packets, they're not going anywhere, and you don't necessarily realize this unless you look at those trace points. Contrast this with the networking stack regular forwarding flow. And similar to Jakob's talk later, this contains simplifications, omissions, and lies. But very simply, the driver will build an HKB. It will go up the stack. We're just hand-waving away all the protocol handling. We're just forwarding here, so it gets routed. And then it goes down to defq xmit, which enqueues it into a qdisk. And then the packet just goes here and sits in the qdisk for a little while. And then it does netirf schedule through the qdisk start bit, and that actually raises a soft IRQ. The qdisk watchdog also does the same thing, which can be timer-based for packet shaping. And then a whole new TX action over here in the TX of the IRQ starts, and that will put the packets back out of the qdisk and push them into the driver, similar to what we had with XDP. So in order to be able to queue packets in XDP, we sort of need to replicate this bit here on the right to have somewhere to store the packets and to somehow a way to push them out of the interface. So these are the ingredients we need. Somewhere to store the packets, a way to schedule DQ and transmission. And let's look at these two separately. So if we look at the prior art, we have, in my count, 38 different files in NetShed representing different qdisks. So how many different data structures do these different qdisks actually use? Well, there's a hint if we look at the start of the skbuf, which is where the pointer is used to store the packets inside of certain data structure. And like this is next and previous pointers for a linked list. This is irrelevant. This is an RB node for an RB tree. And these are also linked lists. So all of these really fundamentally only use two different data structures, an RB tree for a sorted list or a simple linked list for just a FIFO buffer. And a linked list, so an RB tree or a priority queue can also be used as a FIFO. So we can actually narrow this down to we just need a single data structure, some kind of priority queue to store packets in. And then we can use that for anything. And obviously for BPF, the data structure is a map. So my proposal for what we need for XDP to just store packets is some kind of priority queue. So that we can also use it as a FIFO. We only need this one type. It's only a matter of performance, and we can try to optimize that so that if you just use it as a FIFO, you get reasonable performance anyway. And we want to reuse the BPF redirect map functionality, as I showed on the previous slide. This allows us to demux without changing anything in the driver. So if we just say, okay, we have a queue type map, and we already have a parameter to the BPF redirect map, which is used to specify the map index. So this can just be used to store the priority. And then we have a mechanism where a BPF program can quite straightforwardly just queue a packet onto a map. And then to get the packets back out, my proposal here is to have a new map helper that dequeues the packets, and which will return a pointer to BTF ID, which is a reference to the struct XDP MD, which is the context object for XDP. So that means that when we pull the packets back out, we can use BTF to look at the packet content, and we can get direct packet access just like the regular BPF program. There's some example code on a later slide on how this actually looks in a very simple case, but this is sort of the map structure that I've implemented to deal with this. So what's the overhead of doing this in terms of redirecting? I'm doing nanoseconds per packet instead of packets per second, because that sort of looks more directly at the overhead. And this here, 36 nanoseconds, is the minimum delay for just a FIFO queue that's very dumb, does nothing. It just puts the packets in and pulls them back out again straight after. This is the RB3 based. I'll come back to what the PIFO is. But so the overhead from just FIFO is basically the overhead of, instead of just pushing through the packets immediately, we put them on a buffer. We spin up a separate soft IRQ thread to push them back out. I'll come back to how we do that. And most of this, as far as perf is concerned, is actually the cache misses, because we no longer, it's a different packet, so it's gone out of cache by the time we come back to dequeuing, as far as I could tell from perf. And so the RB3 overhead here is because RB3 does this. You're not supposed to be able to read it. It's just to point out that there's a lot of tree. Like the RB3 implementation is highly optimized, but it does do a lot of tree rebalancing. It doesn't run all this code every time you remove something from the RB3, but it does it enough that this has a significant overhead, which for XDP turns into, it basically doubles the overhead of the queuing operation just from using the RB3. So we had this thing in the middle that was called a PIFO queue, which is a data structure that actually comes from the literature. So I'll do a slight detour and talk a little bit about PIFO queues. So a PIFO queue is this push in first out data structure, which appeared in the literature 5 years ago. And it's actually targeted at Silicon implementation. So this is a data structure that's implementable in hardware. It's a limited priority queue where you can push in at any time, hence the name, but you can only dequeue from the head. And that's lends itself well, as it turns out, to be implemented in Silicon. Now, we're not doing Silicon, we're doing software. So we don't really need to limit ourselves to the PIFO data structure. Like we can do arbitrary dequeue at another position if we want. But the nice thing that appeared when we were looking at this is that there's an optimized algorithm in software in a different paper called Eiffel, which does this bitmap-based index into a list of buckets. So you have different queues, which is your priority. And at each priority, you just have a FIFO of packets. So if you in queue multiple packets with the same priority, you just put them into a FIFO. And then you have this hierarchical bitmap where on this figure, it's only 2 bits, but these will be words. So you have 64 bits at each level. And then if this bit is set, that means the next level has a packet in it, and you go through all the way, and then you have a very efficient index into where is a packet in queue. So if you have to find the lowest priority packet, you can do that really efficiently with just a few find first set bits. And of course, this is just an array of queues. So if you want to do out of order, find something at like dequeue at a particular priority, you just index into the array. Now, the drawback of this is that it's fixed. So like the RB data structure, you can put any priority in there and it just sorts them, basically. Whereas this, you have to ahead of time decide how many buckets do you have, and these are the only priority levels that you can do. That is, for some applications, that's totally fine. If you just want to do a priority queue with fixed priorities, you just create this and do it. But if you want to do things like calendar queues, where you're pacing out packets and doing time-based things, then this becomes a bit of a problem, because you want to actually advance the priorities as you use them up, as time passes, right? And so they do have a solution for this, where you create, behind the scenes, you create 2 different sets of the same number of queues, and then you rotate them. So here we are sort of in the middle, where there's packets in the top priorities of the primary, and the bottom priorities of the second. So as you advance the window of priorities you're using, you will sort of switch from the primary to the secondary, and then at some point you will come all the way over here, where this one gets completely empty, and then you rotate them. And then you have the second like you do the whole thing over again once you've passed through the second. So this requires you to know ahead of time roughly what's the window of priority values that you're going to do. But as long as you just keep advancing, for example, when you are using time-based priorities to do something like EDT or what ShedFQ is doing, you can use this data structure and you still get the efficient lookup for finding the next bit in it. So that was the thing here in the middle. And you can see this performs significantly better than the RB3 in terms of overhead. And I think this added 22 nanoseconds is not actually so much the bit operations. It's more about, again, the bitmap itself being held in cache, so you get cache meshes when you put it in. But it's about half the overhead of the RB3-based one. So the question then, in terms of the data structure, is this API limit acceptable? It seems like the performance benefit is worth actually using this optimized data structure. But we can discuss that. If anyone has any ideas for other data structures, we can discuss that as well. And then as far as the API is concerned, what we're proposing here is the reuse BPF redirect maps. We don't have to change the drivers and then have a separate helper to push the packets back out. Which brings us to the other ingredient that we need. How are we actually going to schedule and dequeue this package? Now we have packets in a map. They're sitting there and they'll stay around forever until we clear the map, which is obviously not so useful. So what could we do instead? We want a TX hook. And we had the first attempt, which has submitted as an RFC back in July, is to add a new program type, which can be attached to an interface like an XDP program. And then the stack will call this program, ask, do you have a packet for me? This program then goes and looks in its PyFo map and says, yes, I have this packet, and it just returns the packet as the result of the BPF program execution. And then the stack will do NDO, XDP, XMIT, and transmit and batch up packets the same way as XDP is doing on RX. So if we go back to the diagram of the networking stack here, so this one becomes a new helper, the scheduling bit, where you can tell the stack, please schedule transmission on this interface. The queue is to actually store the packets. We cover it. That's a new map type. And then over here, we do a new program hook. And that was the first attempt. The diagram with the performance bits I showed before, that was actually queuing this. In terms of code, it becomes really simple. This is a terrible queuing program. It just does FIFO queuing. So it just enqueues into this PyFo map type, which you specify the range as the map extra field, and then you just redirect map into the PyFo. Here we always do priority 0, so it's basically a FIFO in terms of behavior. And then if the redirect works, we will call this schedule iphase, which will kick off the TX soft IQ, and we will get a dequeue program transmitted over here, which will pull the packet back out of the PyFo and just return that. So this works. Problem. We don't do new program types anymore, as we heard yesterday morning. And Alexei suggested that we can do it without doing any of these hooks. And much as I hate to admit it, he was right. So back to the drawing board. We want a callback. Do we have something in BPF already that can do callbacks? Yes, we actually do. We have BPF timers. So how about we try using those? We keep the new map type. We have a helper that is just the send this packet helper, and then we do a timer callback to do this bit over in the soft IQ. So that means that the code starts looking like this. In the XDP program on RX here, we look up the timer, arm it if it's not already. This is a one-time thing. And then we do the redirect map as we did before, but instead of calling the helper to schedule, we just start the timer with a timeout of 0, which is a way to sort of abuse the timer API to just get a callback as soon as we can. And then over here, we have the timer callback, which is a function defined in the same XDP program. It's no longer a new program type. It's just a function in XDP. And this will get the the Bpf timer, we can reference the map, and then we just do a loop here. So all the batching that the stack was doing for us before, we just do in XDP, and this Bpf packet send is then an interface to just call the NDO XDP XMIT function like the stack was doing before, with the batching so that we call flush when we're done, and that will actually flush the packets into the code. And like this helper is now 4 lines of code because it's just reusing all the bits of the dev map. And then we keep track, and if we've done a batch and we want to come back, we do a queuing thing as well. So this callback is, because Bpf timers are using the HR timer APIs, this will be called in a different software queue, which is the timer software queue. So it's sort of similar to what we want. It's just not the TX IRQ. I'll come back to that as well. So one problem with this is that compared to what we had before, we're now suddenly at 114 nanoseconds from the callback. So this is due to the overhead of the HR timer. We're sort of abusing the timer mechanism a little bit by saying we want an immediate callback. We do want to do the timer thing with actual timeouts. If we want to shape out, like if you want to pace out packets, you want actual timeouts. But if we just want to send packets as fast as we can, we need this immediate callback. And because timers, the HR timer code takes a couple of locks, and that's a bit of overhead in sort of scheduling a timer, this adds up to quite a bit. So I think the approach of using the callback thing seems promising. I do actually agree that it's a better API. We can all the batching can be decided by the Bpf program instead of having the stack impose a particular way of doing it. So how do we deal with this overhead? There's also the risk of doing so much work in the HR timer soft IRQ. I'm a little worried about blocking other timer work. So there was some discussion on the list about a generic callback feature, which might be a way around it. We can also have a bit of a hybrid approach where we still expose a helper to Bpf to schedule a callback in the TX soft IRQ, but instead of a new program type, it will just be another way of executing the timer callbacks. So if anyone has any thoughts on what would be a good way of dealing with this, or in general, please let me know. Another thing we have to solve that I'm not quite sure how to do is that we need pushback from the driver. So we need to know, we don't want the driver to just drop packets on the floor if it can't keep up. So what the new program type hook was doing was to use the same mechanism, and then the driver will will come back and say, I couldn't transmit all the packets. And then the stack can just keep the package queued on this small bulking queue and try again the next time it's called. But for Bpf, we can't really return the programs immediately to the Bpf program. That the Bpf program really needs to decide, okay, I tried transmitting 8 packets, I can only send 4. What am I going to do with the other 4? And I'd rather not add another hook in the driver to sort of get this information ahead of time. But and the reason we can't just do the same thing we're doing in the stack is that if we do that, then we have to teach the verifier to ensure that the Bpf program will either release or requeue all the packets that couldn't be transmitted. And this seems non-trivial. So any ideas for how to do that would be welcome as well. But other than that, that is basically it. So this is sort of another diagram to summarize what is the proposal here for how to do this. With this, we will have the XDP program starting a timer, still doing the redirect thing into a map, get stored in the Python map, and the timer callback will then do the same thing, still in the context of the XDP program, but in a different software queue, and the batching is done by Bpf, and that still sends it out to the driver. So yeah, thoughts, comments? This is also a PhD project, by the way. I have a PhD student working on implementing different queuing algorithms to show that this can be done in this API. And many thanks to Jesper and Katikaya and Anna and Per, who are advisors in this.
I have a question about the timer part.
Yeah.
Most of the time, you queue a packet on an empty P5 FIFO. So why should you start a timer? You could send the packet right away without the timer override.
Yeah. So this was like, you mean this bit? Like instead of queuing it and scheduling the timer, I could just send the packet. I mean, yes, that's because this is a bit of a contrived example to just show the overhead of transmitting. So actually this, what this gets you, apart from a lot of overhead, is that you get a bigger buffer. So you can buffer, depending on how you size the map, you can, if you can't keep up, you can, you get a buffer of however many packets you size the map for. So if you have a bursty thing, so this is not a real queuing algorithm, obviously.
My second question is about BQL or XOF state. So QDisk normally doesn't attempt to send a packet to the driver if the driver already say XOF, right? So
yes, that's this bit. Basically we want to be able to do something like BQL. And one way of doing that is to have a hook in the driver, but then we need to implement that in the driver. Bpf could also do the same logic, but we're not hooking into the packets that come from the stack. So what I was doing in the initial implementation is sort of reacting to the fact that the driver says, I can't transmit any more packets, and then I just back off. But having something like being able to do something like BQL is definitely a goal.
Also, I want to comment on your slide number 6, because you said that when you do the unqueue, then we fire the soft interrupt, takes soft interrupt, but we don't. It's the QDisk. When we do the unqueue, then we just do the dequeue right after that. We don't rely on the soft interrupt by default. So if you queue a packet right now on QDisk, there is no soft interrupt triggered unless the watchdog needs to be set up.
Right. Okay. Yeah.
So have you looked at, and I think I know the answer to this from past discussions, what kind of changes would be needed to allow XTP frames to go through the existing QDisk? So that way the SKBs and the XTP frames, you don't have to have separate paths and separate handling, but instead you're going through the same QDisk mechanism. And like kind of like the ton driver, there's a flag at the lowest bit that says I'm an XTP frame or I'm an SKB, and then somehow figure out how to allow the same infrastructure to exist for both.
Yeah, but QDisks tend to rely on details of the SKB, right?
Right, that's what I mean by how much work is needed to get this code, the enqueue and dequeue and scheduling aspects to handle both. Is it just beyond the realm of possibility, or could something be done to kind of carve it out? It avoids the need, it allows both paths to interface with the driver in a nicer way. You don't have to reinvent a lot of the infrastructure that QDisk already has.
So the reason I went with this approach was that my thought was that the answer to that is a lot, and like more than that's what's feasible.
I'm not sure it's possible. I think we use the CP field in the SKB, right, to store the length and the different information. So that's hard to get around the SKB.
Part of a potential path to do that would be to finish the list head conversion for SKB.
Sorry?
If we finish the list head conversion of SKB, get rid of that next and previous pointer and replace it with a true list head, then the structure is generic enough that we could place that at the beginning of the XTP buffer or something like that. Then we have this generic object we can push around either through scheduler or through paths.
Yeah, that would imply basically making the whole forwarding stack agnostic to whether or not it's an HTTP.
That would be the most ideal situation.
Yeah.
Slightly related to what David and Jesper was saying,
it's very dumb, but have you considered instead, for example, introducing a XDP different return code that will redirect the frame, translating it to an SKB?
That's sort of what CPU map does. That will redirect to a different CPU, and then on that CPU you will build an FKB, and that will go into the stack.
And
it's also
through QDisk.
Yeah, okay. So you mean redirect it to an egress interface and build an FKB at the last minute and queue it on the queue disk?
Yes.
But then we lose all the performance, right?
We lose some performance. I did something like that many years ago with something that resembled vaguely XDP, and on very small size hardware, the loss was not so tragic. It was very simple, and it fits the normal traffic. Like normal traffic will be shaped like the XDP traffic or partial XDP traffic. So,
yeah, but like if you look at, for example, the difference between generic and driver XDP, that also shows that performance goes really much out the window as soon as you're allocating FKBs. Like if you had something where you can build a bare bones FKB without allocating any new pages or anything, that might change, but that's...
But it's just to save like implementing a new transmit, right? So you can use the existing. So the speed up, we could have allocating the SKB, just not initializing the cache lines, and then making sure we only have to touch, like that we know in the transmit path of the normal drivers, we only touch these things of the SKB, so we only need to initialize those. If we can do that, so we only need the first cache line in the SKB, then we might actually have to speed. Yeah.
I have a question slightly unrelated, but you mentioned BQL. Do you have any information or experience running BQL on multi-queue devices, and experience to tell us whether it's still relevant?
Whether BQL is relevant?
Is it? We have multi-queue devices, right? BQL kind of counts as per queue. So I don't know how relevant it is.
Well, so depends on the hardware, but BQL helps a lot in general from like keeping the hardware from queuing up too many frames.
No, but that's a good question, because if you have a lot of receive queue than transmit queue, then BQL is less effective. But I guess if you are using XDP, that's maybe because you are using less queues, like 1, 2 queues, and there BQL is relevant.
Yeah, so I had a bonus slide actually about CPU steering, which also is like receive queue steering, that it's sort of like transmit queues and CPUs and everything. And any synchronization you do between queues or between
you can use this command with Bpf tool to dump it and see the output. You can also get it formatted as C code, which is more practical. But to see the raw output, you can see all the numbers referring to each other. Today it's exported via syskernel Bpf, BTF, and modules since 5.11. We have the main file, VM Linux. We have IDE 1, and the modules are sort of they use the last IDE in the VM Linux and build on top of that, because that means that the modules can save space by referring to the IDs used in VM Linux, so they don't have to define the type U64. And then user space can also have BTF sections, and this is known as local BTF. And there's another helper function that you can use to extract the local ID, and the numbering will start from 1. So the question is if we can use these IDs to identify the layout of the BTF. So I explained before the type IDs I could look up. They're actually not unique because they will repeat again in different kernel modules and basically in different BTF objects. And I think you can also, from user space, load these local BTF or load other BTF that will also get an ID. Vmlinux gets ID 1, and the modules get assigned dynamically when loading. And the same for user objects. So the idea is that we discussed on the mailing list was to have this full BTF ID, the 64 bits, which is a combination of the object and the type ID, and the lower and the higher 32 bits. So back to XDP hints and this metadata area. So the metadata area has some funny properties, which is that it grows backwards from where the packet starts. It must be 4-byte aligned, and we have a limited size. And the Bpf programs can play with this area also, so they can do the adjust meta that works today. We have the verify binary checks and all this kind of stuff. There's a gotcha here, but let's just move on. So let's look at the expected users of these XDP hints. The obvious user is Bpf programs themselves, XDP and CC hooks, and they can use these helpers to get adjusted the layout. It's great, but I also have a use case where I want to go from XDP to SKB conversions. We already had that today in VHH and CPU map. I want them to be able to have these traditional hardware offloads transferred in, because we're losing that today when we are redirecting into CPU map or VHH. We're losing the traditional hardware offloads, and that's kind of sad. We want that back. And then you can also chain Bpf programs that could communicate with this state. And the last user is AFXDP that wants to consume this. We have users at Intel, and we have users in wind turbines that wants to use this. That means that the user space have to decode the BTF information themselves to understand the metadata area. People have complained a little bit about this, so I'm just coding it up for people. I have examples so they can do that. So the motivation for XDP to SKB conversion is my moonshot idea with NIC drivers without SKB knowledge. But this, for the sake of time, let's just skip that. So the other motivation is that at some point, we do it in software first, but at some point I want hardware to produce these XDP hints. And we know it's possible for the hardware because it's just next to the DMA area. It just needs to shift the DMA area a little bit and then put the metadata there. On the mailing list, there were some other proposals that wanted to take care of engineness. I'm saying BTF is flexible. Let's add this later when the hardware appears. So let's explore the solutions with the queuing approach. Yeah, so I want to decouple things with the BTF ID and put the BTF ID in the metadata. So this will be this full BTF ID value as the last member of the metadata area. And we want that, so I think it was Björn, the AFXDP maintainer, that came up with this idea, that we can then, AFXDP can just do a negative offset on the packet header, and then look at this ID, and then multiplex on that ID, and then it basically becomes at a known offset, and then AFXDP can decode and knows the layout of the metadata and how big it is, also from this ID. Then I extend the flags in XDP-buff and XDP frame, and we also need some flag on AFXDP. Just say this is enabled, and because we have the full ID, we identify what module it is. We need this when we are redirecting into VHH, because it can come from different modules, so we don't know, because it would be easy if I'm just running XDP on the same receiving interface, then I know it will be from the same module, right? Because I'm running on the driver. So this decoupling, I call it decoupling because I don't have to have a fixed XDP structure, lock it down or somehow. It's nice because I can just change layout per packet. I just need to update this ID to tell what the layout is. It makes XDP to SKB conversion harder because I would need a sort of a lookup table to see if it's compatible and contains the existing hardware floats the SKB knows about and update that. So step 2 is I extended with a common struct that the net stack knows about the existing hints we already know and I described. We still place the full BTF ID inside the metadata as the last member, and then I extend with one more flag that says this is compatible with the common layout, and that this helps the XDP to SKB use case quite a lot. Then I can just code it in standard C. But for example, AFXDP must not, and user space must not consider this like the UAPI. It's only described via BTF, and they must decode the BTF information with this. And this is what's in my patch sets. So this is an example of the layout that is described via BTF, and the last member is the BTF full ID. So we also have some flags, which are very important for understanding what's in the structure and what's enabled and not or activated, right? But I also want to use BTF for the flags. So the next is the flags dumped from BTF. So people should also use these, and they're still not UAPI. You have to decode it and use BTF to get resolution on what they mean. And there's the checksums, which are the first two bits. I map those directly to what the SKB has of information, like the checksums, none, unnecessary, complete, and partial. And so I can just map it directly and use that in the SKB, and I'll refer in the comment to the documentation for the SKB. So this is how a driver-specific struct looks like. So in the bottom of the struct, because it goes backwards, we have the XDP hints common, and in this case it's I40E that has extra the hash protocol type, information. So it would actually tell you when you're on this driver, it's specific for this driver, you can check if it's UDP, TCP, SCTP, and there was, I think there was one more protocol you could see, and you know if it is encapsulated, and you know if it's IPv4 or IPv6, you can get that information out of it. While this thing that you get down in the SKP is only if it's layer 4 or layer 3 headers. You don't know anything more about that. This way we expose that in an easy way. So that's how the layout can do. But how do we export this to user space? And do we really need a new UAPI to export it? I'm saying no, just use BTF. So the proposal is basically naming convention. So like I think you saw here, I named this struct XTP hints underscore I40E, right? So I can just to figure out what this driver supports, I can go in and pass the BTF information and then search for stuff called XTP underscore hints to understand what this driver can provide in the different packet layouts. That's the one in my user space program. In AFXDP, I have to decode and be able to identify and handle those I care about. So that's the way drivers can figure out that. So an extension of this is, I'm not sure it's a good idea or not, is that each NIC driver simply defines a union called XTP hints underscore union, which contains these. This means that my BTF parser just have to find this union and then decode that union and find the IDs that this union points to. And then I know what this driver supports. One complication is that the metadata goes backwards, so you have to have this padding of the union, which can kind of look ugly. But it could be easier for the driver because it actually has a type for all the different metadata areas. And this is how it ended up looking, my proposal. So in the I40E driver, I also have an XTP hints that contains the timestamp. And I have the normal hints. And I also show here I can have the common hints. I don't know if it's too bad, or I don't think it's too bad with the padding. But that would be a way to export it without introducing any UAPI. It's just naming conventions, just a convention that every driver will have a struct with this name. You have to pass that, figure it out. So the future work, so I think I covered the receive side. Future work is that Magnus, he promised he will look at the transmit side, the AFXDP maintainer. So TXI is basically asking the hardware to perform an action for us, like do the checksum offloading. We also want to do that. I'm not quite sure where we have to put some hook in the driver. We have to do some driver changes, which is annoying, but basically the drivers are already doing this today, taking the information from the SKB and put it into the transmit descriptor. So it's it's doable, it just requires some work. And then we have and one thing to remember is I also want to have on the transmit completion events, I also need something there, like because the hardware also return hints when it's done transmitting the packet, which is like the transmit timestamp. We also support that today with SKBs. And then I'll help user space developers write some code up to decode the BTF, and maybe we should create a library with this somehow. to make it a little bit easier. Another thing is we could extend BTF tool to list these available XDP hints to we adopt the naming convention and say this is how we export it, and BTF tool can, for drivers, list it to make it more consumable by people, but we basically didn't introduce any new API. So I tried to keep time. I spoke a little quick because we lost some time on Toge's session. So questions?
So my question is with using kind of BTF IDs, type IDs together. How do you manage the lifetime of these BTF objects? Because you kind of use the BTF ID from user space, you get a file descriptor, you take a ref count on the in-kernel object, and that kind of makes sure that everything stays around for you to use. But imagine from AFXDP, you can kind of get a random packet with a random ID, and then you're going to have to look that up. What happens if the BTF is removed from the kernel?
What I did in my patch is that I took on the BTF object in the module itself, allowed it to take a reference count, or I incremented the reference count for the entire BTF that the module provides. So it will stay there until the module unloads. But you could still have the user space like trying to identify and looking for these IDs, right? That comes in while the driver has been unloaded, but it doesn't matter because it's just the ID. That's what I mean. That's sort of decoupled from the user space. Have to have a reference count to make it sure it's there. That's what I mean by decoupling through the ID.
As in the user space. Sorry, what would user space do?
So user space will have when the driver was loaded, it would have a table that it knows this I like this ID. I want this ID, but once the driver is unloaded, it still looks for the ID, but the ID will never come, right?
Oh, right, okay. But I think we can reuse IDs for BTF objects.
Like the IDs for kernel objects are not reused immediately, right?
It should be very, very, very unlikely. You have to wrap.
I guess like the expected use case would be that while driver is up, you can download the contents of the BTF object, right? Like parse all the types, then attach program. And if after that kernel is unloaded, module is unloaded, it doesn't matter. Like it's just IDs, right? So memory access.
Yeah, and so the use case where it could happen, like because if it's loaded on the driver that XDP hints are coming from, it will obviously be taken down because the driver is unloaded, so it cannot. But we could have it in the VHH that we are redirecting into, that all of a sudden gets an ID, or is looking for an ID that cannot appear anymore. That program Bpf program will still be loaded, right? But I don't.
Yeah, so like if you're talking about like whether eBPF will do all the relocations when you load the program. So like if your program already got the packet, then like you have all the core relocations happen, right?
Yeah.
If it's AFXDP, presumably like the AFXDP application will parse the BTF just when like they set up everything initially. So like by the time that it gets packets, it also has all the.
Yes, that's how I implemented, and I made a very strong point of for the AFXDP people, don't look it up on every packet. Like don't pass the BTF information on every packet. Do it at setup time, right? And I coded it up for those users that used it.
So just one remark, I wouldn't put this BTF full ID into the struct itself. Well, first of all, it's like misaligned right now with your data structure. It's not U64, it's actually two U32s. But like also why you're demanding everyone to put it as a last member if you just know that it's there in the memory and just dictate that it's there and that's it. So the hint itself should declare like the useful new information, not the one that like you know that is there, right?
I do hate that I'm spending that many bytes on the BTF ID, but I'm doing it for the AFXDP user, so they have it.
No, I understand. I'm saying like don't include it into the struct definition itself. Just dictate that like last 8 bytes of the XDP metadata is the BTF full ID.
Yeah, you could do that. Yeah, so we don't actually define it. But yeah, so it's just mandatory that it moves. Will just be there. That's what you're saying.
So, quick comment. So, like this whole storing ID in the packet, in every packet because of XDP, I really don't see how like user space would deal with it. Like imagine doing like switch statement per packet and then do different things potentially with this every ID. Feels like any kind of performance benefits from hints that come with the driver will be completely destroyed by this, like, let's do switch statements for every packet and check the ID whether it matches and so on and so forth. So just like doesn't seem worth it. It's like you're trying to improve performance on one side, but then like it gets down the drain in another.
It's not only improving performance. The use case I have is in a wind turbine, we get the hardware receive timestamping on only some of the packets. It's only a 1 gig interface. It's not for speed.
Sure, but still, like for FXDP, you don't need to pass all of the stuff all the way to user space because FXDP also has can have BPF programs attached. And if they want to read the timestamp, let them read the timestamp before like user space does start to run, and then it can like convert it to whatever flags and necessary. So I would keep the packet only with the data that is there, that is like provided by the driver, and that's basically it. And let VPF side, in both cases, in XDP and FXDP, like decide what to do with it.
So you want to let a BPF program restructure it before it goes to AFXDP, or? Yeah,
before user space, like user space like receives it, right? But there is still like BPF program can be run, right? We typically optimize it into knob when it's not there, but it can be there just as well. It doesn't cost us anything. Like it's.
But then, yeah, sure. But then you have to invent a new scheme for that.
No, it's like, but it's there already. Like the BPF has an ability to run in the FXDP case. Anyway, probably should take.
Yeah, but then I need to store the information for when I redirect into VHH. I need to store the information somewhere, and then I need the BTF ID maybe in the in XDP buff.
So one thing metadata can help with is that you can delay the populating the cache with the headers. For example, if you're looking at the hash to know where to queue the packet, you can avoid touching the data before it's populated in the hash, getting some more performance. So that's one thing metadata can help with. It has some use cases.
I think this would come down to benchmarking it, right? Because if the BPF program is demarking, and then you have to copy the data somewhere where the user space knows where it is. That may or may not be faster, and then switching on it depends on how many different IDs you're handling. It could also potentially be things. Yeah. Yeah.
And the reason I place it in there, the ID is in the same cache line that I have to. I get the metadata down as a hint, and I need to touch this cache line anyhow. So it won't cost me much more to read the ID. It won't.
I have one last question. Did you look at the different XDP projects and analyze, like what metadata they would be able to make use of first in order to accelerate them, and what would be the most useful? Because I think like the Weave XDP support so that you can then populate the SKB is probably, I don't know, I wouldn't call it the primary use case, right? But I would probably go and look at the different projects that exist and how can we optimize them so that they can make reasonable use of the infrastructure here?
Yes. So the request has most primarily been about the receive checksum and the receive hash. And there's a project called CNDP from Intel, and that wants this, and there's another project called IPDK that wants this, which are both AFXDP based. And then I have to have the wind turbine user that wants the timestamping from the hardware. And they also want the transmit launch time to send very specific point in time from AFXDP to send the launch time at these time windows.
Okay, thanks. I'll close the session. Thanks.
Yeah, thank you.
All right. So the next session is the next session is by Said about firmware-centric devices and NIC customizations.
Okay. Oh, yeah. Okay. So hi, I think we get 20 minutes. I'll try to quickly go through my slides. The point I'm trying to get across is very straightforward, so no need to go into details. Today I'm going to be talking about firmware-centric devices, and I'm going to explain what I mean by that. We'll talk about NIC customizations, configurability demands, and the complexity come with such firmware-centric devices, and what is missing today in terms of mainstream tools to poke around these devices and configuring them according to the user needs. So what are firmware-centric devices? Basically, these are the modern device you use in every day. They offer more functionality, which means they have more hardware units, accelerators, and engines inside of them. They have more processing power, more capabilities for the user to use, and they have more capacity in terms of internal storage, which means they are more configurable. There are more options to tweak and tune. So these are modern devices, and some of these modern devices, they have ARM cores inside of them. They're not running full Linux OSs, which is just an example of how powerful and how configurable these devices are. And if we look at the early Linux, some of them actually ran Linux OSs, and they have MIPS cores in them, which could easily run a full Linux OS. So complex devices will eventually lead to customization nightmares for system administration or anyone who's interacting with these devices. And they offer basically tons of features and layers to set up and customize, tweak and tune. And users basically needs to know exactly what combinations of this feature they need and how they can fit the use case and what is the exact tuning they need for these features to work in harmony with each other. And most of the time, these features, they don't magically just work with each other out of the box. For example, if you take a NIC and has like an offload crypto engine, I'm very sure they will have lots of limitation running all of the crypto engines all at once, like TLS, IPsec, MACsec. they're going to have some limitations. And the user needs to pick and choose what exact configuration they will eventually need to run with. And the average user basically uses 20% out of what the NIC provides, what the NIC can offer, which means customizability and configurability is required from the user. So I'll give here an example, some code statistics for our ConnectX devices. Firmware code, basically, it's today the core firmware code. I'm not talking about the whole thing. This is the core code that runs basically on every ConnectX device. It's around 500,000 lines of code, and it has north of 600 configurable knobs, which is crazy, but we need that. It's a big device, has lots to offer, and it has a lot of tunability and customizability. So these devices grow about 25% in terms of code and configuration knobs each year. So just to get an idea how much this thing is growing and getting more complex every year. So yeah, we get the point. These devices are highly configurable. They have lots of knobs, lots of settings to work with. But don't get me wrong. Yeah, they're highly configurable. They're not as smart as you want them to be. Eventually, a human interaction is required. The user needs to know how to configure and set up this device for his own demand. So that's highly recommended. The user knows what exactly to set up and how to configure the device, what exact combination of features to boot with. You don't need everything, so pick wisely what you are going to need. And user needs to know the most efficient configuration for his use case. So finding the most efficient configuration is a trial and error process. And usually we are testing a full stack. It's not just testing this specific hardware. We're testing the hardware with a full stack, and the NIC is only one single piece of the whole puzzle. Standardization can only go so far. By standardization, I mean ETH2. It can do everything that a user want to do. And for example, system control and ETH2 can help with tuning some TCP parameters that are software oriented. But the question is, how can I tune the hardware TCP engines and accelerators? And can I experiment with those? What the specific vendor has to offer in terms of optimizing TCP or any other offload in this case. And this is the big question. Can I tune and tweak the hardware I'm working with for whatever use case I'm trying to explore? So the current solution the vendors has to offer is just download the specific vendor-specific toolbox and gain the access for the NIC, the device internals. And the problem is that these tools, they come with lots of issues, and they're not easy to use, obviously. And most of the time, they will require user space access to the PCI. They will need some proprietary drivers, kernel modules, and long list of tool chain tools just to set up one single flag or one single mode of operation that the user is interested in. Mostly these tools, proprietary tools, not welcome in production. They have long turnaround cycles. If you're debugging an issue, it will take days until you have some sort of environment that is usable, workable. And they just don't work with secure boot and secure kernels. So there's no solution there. You have, from my experience, some people, they just boot into different OSs just to set up some flags and boot back to the production or testing environment just to test some single flag. There are lots of horror stories. I'm not going to go through all of them. So the whole idea here is to set up a single flag or to experiment with something. You don't need a tool chain from the vendor, which is the whole point of this discussion. So let's discuss quickly the types and knobs we need to have full access to configure a device. Basically, there are three types: functionality, enable, disable, select a specific mode of operation from a list of well-defined values. Performance tuning, performance values to set up all kinds of algorithm limits and ranges that you might need and experiment with. And verbosity and debuggability. Trigger some sort of monitor trace inside of the hardware, monitor that tracer, capture log, report it, and turn off that feature once you're done. Some of these features exist today, some of these features do not, so we'll explore all of that in the next slides. You would categorize these parameters into 4 categories. The first one is non-volatile, which is the usual NV config that you have inside the firmware. These are static parameters that are preserved across reboots. Volatile device global firmware parameters. These are runtime parameters that you set up once and you reload the driver. Sometimes you don't need to even reload the driver for them to take effect, but you will lose them across reboots. The third one is interesting one. I'm not going to go into much details today, but it's interesting, and it's mainly needed for SRV and virtualization environments where you need to set up configuration, specific configuration per function. And mostly these are going to be runtime configuration. And the fourth one is RAS types of feature for firmware to capture and debug and have some sort of access to the hardware internals to have some visibility and to get some to have some gateway to view the internals of the device. So the upstream API today, we have something that we can work with that can provide the needed mechanisms and methods to allow all the stuff that to allow all the parameters needed in all the categories. Basically, it's DevLink. DevLink has many subsystems that we can utilize for the requirement, and we already today have something. So it's basically going to be DevLink params, DevLink health, DevLink resource, and port functions. I'm going to go into details in the next slide. So let me quickly run through all the categories and what kind of utilities we have today. So for the first 2 categories, the non-volatile and the volatile NIC customization, we already have DevLink params. DevLink params, they have flags for each param that can describe the parameters to be permanent, which is non-volatile, or volatile, which is driver init or runtime. Driver init means you have to restart the driver for this parameter to take effect. And if it's runtime, the parameter will take effect immediately. There are ways to show the parameters, and there are ways combined with DevLink reload, it will give you the full requirement for setting up a specific configuration. Also, DevLink has a driver-specific parameter mode where you can register parameter that driver-specific, which is great for vendor-specific optimizations. The big problem here is that it's hard to agree first of all, what belongs to DevLink and what is driver-specific, what is not. So this is the big problem we're trying to solve. And today, out of the 600 knobs that we can offer, only a few parameters we have populated in DevLink, mainly because we just don't see how they can fit there. So that's the main discussion today. For per function configuration, the main issue there, this is we're talking about virtualization environment, there's a chicken and egg issue here. How do I set up a function that doesn't exist yet? Also, we can utilize what we call DivLink port functions, which is the exact representation of these functions that are going to be spawned dynamically into the system. So we can utilize DivLink port function and combined with DivLink parameters to set up these functions before they are spawned and populated into the system and popped into a container or a VM. So we will give the user the ability to customize these functions before they are used in the system. Today, it's DivLink core function subsystem is missing the DivLink parameters, but it's a simple hack to apply the DivLink parameters to that subsystem so you gain a customizability that for debuggability and RAS features, DivLink is rich of methods and mechanisms. As some examples, DivLink dpipe, which is good for viewing the offloading pipelines, basically the steering hierarchy inside the device. DivLink Health is also a good utility to use to poke around or to have a view in the DivLink, in the device dumps and device internals and see the health of the device and diagnose and dump all the device internals to just monitor the device health. DivLink region will dump the whole configuration space, and DivLink resources will control limits on device-specific resources. The problem is that does not give the full spectrum of what we need. And it's not really implemented by many drivers. Something's missing there. And I think the problem is that these are mainly read-only knobs. You can only read whatever the driver and firmware has in that moment to offer. What we are missing is seatability, controlling what dumps I need to read, what kind of logs I want the driver and firmware to provide, what debug level firmware should be running in, which is very important to have in production systems today, because if you have a report of an issue, the only way to get the firmware to run in a specific debug level is to have these vendor-specific tools. So yes, seatability is missing, and this is something we can use DivLink parameters to utilize to turn on some of these debug features dynamically. Another thing I wanted to explore, but I didn't have much time, just an idea that I will try to explore in the near future, is having vendor extension, which is like a more dynamic approach than just polluting DivLink and the kernel source with vendor-specific stuff. This customizability and high configurability issue existed before Nex. Many subsystems already tried to solve it. Also, we have something in ETHTool that tried to mitigate the vendor-specific stuff, mainly in DivLink, in ETHTool, EEPROM, and register dump. There we have specific vendor-specific code that knows how to parse the vendor-specific registers. But again, you can only read, you cannot set. You cannot set exactly what kind of dumps, what kind of registers you want to read. A good example, NVMe CLI. They solve the issue. They have firmware objects. They can read, log, activate firmware flags, and read vendor-specific attributes by allowing vendor extensions and plugins. So basically, at NVMe, the NVMe stack allows the vendor to have their own extensions to the control layer to provide their own control mechanisms to set up, configure their hardware. Kubernetes, and they have the CNI plugins that vendors and users can provide to configure the network. OpenStack has something similar, and I remember libvirt from back in the day. They also have something that vendors can just plug in, and you can configure a device before it's attached to a virtual machine. So this is not something new. This is something already solved, and somehow in the native layer, we're still struggling. So just to summarize, NAIC attestation is still immature, even with all the div link stuff we talked about. More work needs to be done, mainly adding more knobs and seatability, allowing the device to be more configurable in terms of adding more layers of parameters, more vendor-specific stuff to poke with, to work with, and to experiment with. And the issue here is that we need to decide what are div link parameters and what's the purpose of them, so we can finally lift the embargo on them. By the embargo, I mean the maintainers shooting down every single patch that's trying to add a vendor-specific parameter. So, and it's to me, it feels like there's a wonderland that we're not really utilizing here. So overall, I talked to many people, many customers, developers, testers, all kinds of people from all trades, and they all agree they need this. You can't just teach people how to download all the vendors' specific tools and how to use them. It's a lot of work just to set up single flag. So we need this, let people experiment with the hardware first, then we can figure out what is the standard. And once we come up with a standard, we can delete all these vendor-specific flags and have the standard. But before that, we must allow vendors to have vendor-specific flags. Questions?
Questions, comments, feedback?
Yeah. I mean,
do you have any examples of vendor extensions where the extension was added in NetDev and then we transitioned to a common interface?
Extension, no, but we tried to add many vendor-specific parameters that got shut down. Reasons are, hey, this looks more like gonna fit more vendors, so let's figure out how to do it in a standard way, and just got lost between.
Well, yeah, I mean, some of the things that you had on the slide went in not that long ago. So
yeah,
it's not like we shut down everything, but the problem I see with it is the vendor adds something, and then like we don't even have a good description of what the feature actually does, and then the next vendor comes in. The first one already does not care to talk even to us because the feature is in, right? Nobody cares. And then the second one comes in with a similar feature, and like there is no way for us to align.
Yeah.
Right? Like we don't all work together on the APIs. It's like different vendors pop up with the.
If no one wants to align, what's the point?
Sorry?
If no one wants to align, what's the point?
Right, like we need to find a way to align.
I have 600 parameters. I can align only with 10. But what happens with the rest of the 590?
That's fine, as long as we can align on the 10, right? My point is that we don't seem to align even on the 10.
Yeah, that's the point. We can't align on everything. We need to solve that before solving the alignment. I need some way to access my hardware before I start working on standards.
Well,
because without that, I cannot define what a standard is.
We need a path to the standard too, right? So we started working in the OCP specification.
Yeah.
That's a way forward in my
Yeah, but this is like years, and I'm losing here people that can experiment with my hardware today, which is the point of the whole talk. I want to experiment today to define the future standard. And I have many examples.
Right.
Yeah. For example, hardware GRO, right? It's still not defined the whole standard. it's on and off feature, but we have list of parameters just to tune the hardware GRO. And it's a standard feature, right? So it will take months or years to push these parameters where today I need to experiment with the hardware GRO to know exactly how to tune that.
Right, but the timeout is a simple one, right? Like you can add that, no one will complain. Just not the dev link parameter.
Yeah, but the hardware engine it's not just timeouts. There are many parameters you can set up.
Are you willing to disclose how the thing works so we can understand it?
No, but I'm willing to, I'm willing to expose some of these parameters for you to experiment with, to know exactly what TCP parameters to set up for hardware GRO to work exactly the way you want it.
I think it is a tricky ledge here. You have to allow vendors to differentiate their hardware, right? There's a reason why all these different vendors keep popping up saying, I think I can do this feature better, or I think I can do this market better. And that's where they get in their way of doing something that they think is a better way to do it. So take the GRO or LRO example. We can agree that LRO is a standard hardware feature, but every platform may decide, every NIC may decide a different way that it's going to do LRO, right? And if a vendor wants to expose parameters for a customer to be able to tune, well, those are going to be very unique to a customer, to a vendor, right? So I would love to see the vendor unique tools go away. Like, the number of hours I have wasted flipping ConnectX hardware from InfiniBand to Ethernet, that alone would be more than worth it, right?
I mean,
that's better to run a devlink command that says, no, you default to InfiniBand, but I'm an Ethernet guy. So let's flip this thing to Ethernet, right? So if we want the vendor tools to go away, we have to allow vendor flexibility in commands. And devlink is one way to make that happen.
Yep.
I believe that Jacob had a presentation earlier in this track about YAML and the self-describing netlink. Have we considered possibly using this for the driver, where the driver can simply register a netlink BTF type that's exposed to user space, and then we can say something like netlink vendor parameter change, and it's all self-describing and usable.
Yeah, but still, this will require some channel inside devlink that would allow.
Right. So it seemed to me like the devlink parameters is an open interface where the drivers can say, here's the set of parameters I support. So it's kind of like what you're asking for, but it already exists in this notion.
Yeah.
Drivers get to tell through devlink what it has for knobs and a description of that.
Question over there.
Advantage of having devlink is also devlink provides a standard way of checking things. Like, for example, there are some misconfiguration that we don't want to allow. We don't want to expose it to the user, so he will find it in very hard way. What feature A doesn't work with feature B. So that we can prevent it in driver. Also, devlink provides a security model, which we don't want to lose. Some features are allowed only for user, some features are allowed only for as an administrator to configure.
Yeah, devlink is the closest to the hardware, so it makes sense to use devlink to control the hardware.
I don't disagree, and I understand why vendors need a way to innovate, for lack of a better word. Differentiate. I think I'll give you that much. All right.
Yeah, that's exactly.
But I don't know who's representing the user, right? Because in the world where the vendors provide the APIs, the user is stuck with a single vendor.
You'll be surprised. Many production users have no issue using them.
I understand that, but like there's a risk of a vendor lock-in, right? Because I have not seen the vendors coming back to standardize the interface later, and then like we don't want to just let the vendors run and lock in the users, because then what's the point of the NetDev configuration interface if everybody does their own thing?
You're saying no other vendors is complaining? I don't get it.
No, I'm saying the vendors do not seem to be aligning on anything. So if you
if we're aligned on, okay, have the flexibility to put whatever you need to configure your hardware. We're talking about parameters that would directly access the hardware. I'm not talking parameters that will set up some sort of weird driver stuff. So these parameters will go exactly
directly to the hardware to set up something.
You know, you say hardware, but it is firmware. So let's use the
firmware.
Let's use something.
It's a firmware-centric device. So yes.
Yeah.
I think we all agree on that. I don't see any other vendors here today, but I'm sure we all agree on that. We agree, no?
I agree that flexibility.
Yeah, so that we agree on that. We need some flexibility, and I think DevLink is the right platform.
Yeah, I mean, the params exist, right? And occasionally you're allowed to use them. So.
Yeah, but you're the problem. It's not DevLink. So yeah, we'll see. I'll prepare an RFC patch and.
For what? I mean, you gave an example of Giro hardware.
I'm gonna push as many parameters as I need. That's.
Okay, and we can look through them and decide which of them like don't
but
make
how
sense
can
to
you
run.
decide which of them are standard?
Exactly. How do we decide?
That's the point.
We have to get the vendors together to decide it.
You can't. We have 600. They have 500.
Well, one way to do it is to keep it out of the tree until there is a user with multiple hardware versions.
That's a problem.
That's a problem for you. That's not the problem for the user.
No, it's for the user.
It very much is a user problem.
Yeah,
if you have to get latest and greatest or some feature that won't get accepted upstream, I have to go to Mellanox's website or NVIDIA's website and download an out-of-tree MLX5 driver. That is a problem. That is a user hassle.
Yeah.
So you're doing the job of upstreaming as much as you can, but then when a maintainer says absolutely not on this, you go and do an out-of-tree way of doing it, and you need to tell your customers, hey, go download my latest driver from this website because this feature is out of tree, right? So if you want things to be standardized in tree, you have to allow that vendor differentiation and innovation sides of it, right? They do go hand in hand. There's going to be differences between vendors.
Question over there.
Saeed brought up the NVMe world, which I think has been pretty successful here. They have NVMe CLI and it has like vendor plugins for like Samsung drives or Intel drives or everything else. And they have a pretty robust process where the vendors and the users, they feel like they want to standardize something. They go to the NVMe technical working group and they make a standard and it gets standardized and it comes out, it's standardized NVMe CLI. And I don't see that in the networking space very, very good. I think the OCP program is like really like, could potentially grow into that. But like the users do have to push as a user. Like the user has to come to the discussion and say, I want this as a multi-vendor standard. I want this to be common. And they need to force the vendors to do it. And I'm not convinced it's the maintainer's role to act as a proxy for the users because there's a lot of users. And you know your users, but there's lots and lots of other users out there too. So I think it's very hard for the community to make a decision. Like all of these, say 600 parameters, you go one by one by one, like you're never going to choose. It's all or nothing in my opinion.
Yeah.
When there's not, then it's nothing.
Sorry?
In that case, it's nothing. That's my vote, right? Like
everybody agrees it's everything. It's just you. We have a question, last question, and maybe we can take the rest offline.
Right.
One question over there.
Hi, so just a comment. I'm the S390 maintainer, and I know S390 mainframes are different, but we actually do have a issue with that with our customers, I guess. So I would really advocate also that the vendors get a way to do, because out of stack maintenance in the enterprise world, that's just a no-go. If it's not upstream, our users don't have it. And we do need special features for our machines. And if we cannot provide the tools to make use of the features of these cards if we have no upstream way to access them.
Exactly.
So we're in a deadlock that the hardware provides features that we cannot offer to the users. And I like this idea of self-describing. I don't know, we had to talk about YAML, we had to talk here about BTF and Bpf, where you have always these self-describing structures.
Yeah,
couldn't you have a general way to say something here, type, size, something, push it down?
Yeah, the options are endless. We just need to agree something feasible or not.
Why is it too much to ask for at least 2 users? That's standard in the Linux kernel, right?
2
If
users?
you want to add an interface, you get 2 users to agree and then add the
We have the interface, and we have to use it.
But you
Bpf
don't.
Link
You guys
parameters.
don't want to talk to each other
Talk
for
about
some reason.
the name of the parameter, which we cannot agree on, and we will never agree on. It's a vendor specific. Okay, so we'll take the.
Wonderful thing about standards is that there's so many to choose from.
Yeah. Exactly. Okay, thanks.
All right. Thank you very much. So we have a coffee break until 5, and then the next talks continue here.
How do you like it? Thank you.
Something more. I want how does the name know?
All right, so the next talk is from Aditi around socket termination with intent. Thank you.
Oh, hey everyone, welcome back. My name is Aditi Ghag. I'm a software engineer working on Cilium at Isovalian. And this talk is about Cilium's use cases for terminating sockets in the context of load balancing and policy enforcement. And we will understand what the intent is and ways to tackle it over the course of this presentation. So this is how I organized my talk to set the context for the problems we are trying to solve. We'll have a short introduction to Cilium networking. We'll then go over some real-world use cases to understand the intent for socket termination. I'll then go over some of the approaches we evaluated, and in the end, I'll share some of the notes from the mailing list discussion and call out some next steps in terms of kernel patches. So many of you would already know Cilium is an open source CNI plugin. It provides networking and security for containerized workloads, such as in Kubernetes environments. And in order to do that, it runs a user space agent in the control plane that runs on every node in the cluster. And this communicates with the Kubernetes API server to receive events for cluster entities like pods, services, and policies. And it then shares this state with the data path via Bpf maps. And on the data path side, we have Bpf programs that execute on C group, TC, and XDP hooks. So the data path combines the context received from the kernel events and along with the control plane contextual information to implement load balancing, policy enforcement, encapsulation, and so on and so forth. So let's discuss the first use case. My colleagues have previously talked about socket-based load balancing in Cilium, but let's revisit it in the context of this talk. So Kubernetes has this notion where a set of logical pods are exposed via a service. So service is just a virtual IP, and then Cilium in the data path, it translates the service VIP to one of the backend IP addresses. And it receives this information, or rather it reads this information from the Bpf maps that are populated by the control plane agent. So we have a C group sock adder type program that's executed on socket events. And it operates on this sock adder context where Cilium data path mutates the destination IP address and port. So for a TCP and connected UDP, the service translation from service VIP to backend IP is done in the socket connect and connect calls in the forward direction. And for the replies, the reverse translation is done in the receive message event. And for UDP, just regular UDP, the service translation is done in send message and receive message calls. So what problems we are trying to solve with socket-based load balancing? Kubernetes environments can be dynamic, where containers can come and go. So the one implication of this dynamic nature that I want to draw attention to is what happens when service backends are deleted. As we saw in the previous slide, Cilium does service backend translation where it selects the backend to service a client request. And this selection happens only once in the socket connect call. So when a backend is deleted, TCP clients may get fin or reset depending on whether the service backend does graceful termination or not. So that's a cue for TCP client to reconnect. But what about connected UDP? Connected UDP are unaware of the remote backends going away. So they continue to connect to the stale backend IP address. So as you can imagine, if we have proxies like Envoy running on a node that intercept all the container traffic, it can see extended downtime. And moreover, connections can be idle at times. So if you just react on events like socket message being received or packets being processed, then the idle connections can take a while to reconnect. So we have our first intent, which is the ability to terminate client sockets connected to stale backends so that they can reconnect to the active ones. So let's go to the use case number 2, which is around policy enforcement. Users may want to apply policies on the fly. So Cilium supports L3 and L4 based addresses-based policies where user can dictate the intent where, for example, they want pod A wants to talk to pod B, but not to pod C, and so on and so forth. But there are other types of policies that dictate how a set of application traffic need to be redirected to a subset of pods running in the cluster. So let's take a real-world example. Kubernetes has this feature called as node local DNS, and it's aimed at providing optimized DNS performance. And in general, clusters, clients can connect to local as well as remote backends, which service the DNS request. But as the name suggests, node local DNS, deployments have a node local DNS cache that services DNS request. And in this particular case, users expect that Cilium consistently enforces such policies. So that means even for existing connections. And let's take the example of the Envoy proxy again. In this case, even if Envoy has a long-lived connection, users would want, or rather Cilium would want a mechanism to refresh this backend mapping. So we have our intent number 2, which is the terminate client socket connections prevented by applied policies. And so that's it from the motivation side. We have our use cases, which is not an exhaustive list of things, but hopefully they give a sense of the problems we are trying to solve here. So let's revisit our problem statement and break it down into 2 steps. The first step is how to filter sockets that need to be terminated on certain events. And the second step is how to actually forcefully terminate such filtered sockets. So step number 1, let's say we have control plane events such as a service backend is getting deleted or policy is being applied. In this case, Cilium needs a mechanism to filter sockets based on, for example, the IP address of the deleted backend. And in such case, we evaluated a few approaches. So the first one is using so the kernel has a sockdiag infrastructure to query sockets data. And the sockdiag, as the name suggests, it provides the diagnostic data related to sockets. So this is exposed via the netlink subsystem. And I've highlighted some code snippets on how users can craft netlink messages. So they would set the netlink message type to sort diag by family. And then if they're trying to query TCP sockets data, then they would go ahead and populate this inet diag rec v2 struct where they can set the extension to inet diag info. So, for example, TCP, it provides some kind of filtering. So for TCP, you could say that, hey, I want to get a list of established sockets. So the downside with this approach is that it provides very limited filtering capability. So Cilium will have to do the filtering itself in the user space where it can match the destination IP address or some socket metadata such as socket cookie. More importantly, it requires entering every possible container network namespace on a node, and which can be really cumbersome in high-scale environments. Because the netlink infrastructure, the sockdiag infrastructure in particular, it matches the network namespace of the query with the sockets that are being queried. So The second approach is using the Bpf iterator. So Bpf iterators were introduced in kernel 5.8, and they make kernel data available to Bpf programs for further processing. So sockets, TCP and socket, UDP sockets are the supported targets. As they provide access to the socket structures, the kernel structures, it facilitates flexible filtering of sockets. So you can match on the destination address or even the socket metadata like socket cookie. And it provides the most up-to-date view of sockets. So this is a very promising approach, but as similar to the SOCDIAG approach, it's network namespace aware. The problem is that in BPF programs, Cilium does have additional context, like, for example, network namespace cookies, but there isn't an easy way to map this data path context to user space network namespaces. So we'll keep this approach in mind for now, and let's move to step number 2, which is how to forcefully terminate the filtered list of sockets. So the first approach is kind of intuitive. Whenever Cilium agent receives service backend deletion events, it can add an unreachable route for the IP addresses belonging to this to these backends. So this is what the IP route would look like. The problem is that it's only effective for new connections. And this isn't super helpful because Cilium supports graceful termination, meaning when service backends are deleted, or rather getting deleted, Cilium will let the existing connections to this backends terminate gracefully. But at the same time, it won't select this backend to service new connections. So let's take a quick detour. When a backend is getting deleted, there is a Kubernetes control plane agent called as kubelet that runs on every node. It instructs, so firstly, Cilium agent receives an event for the terminating backend. And at the same time, kubelet instructs container runtimes to send SIG-term signals to the backends. And if the backends have some graceful termination routine, then in those routine, they would send reset signals or fin signals for graceful termination back to the clients. And if there is a graceful termination period configured on backends, then at the end of this period, the container runtimes then sends the SIG-kill signal to the pods. So bottom line is, in the established state, TCP and connected UDP just ignore ICMP errors. And so this doesn't solve our use case. So the next approach is using the sock destroy API that kernel provides. Internally, this API invokes handlers to abort sockets, and these are protocol-specific handlers. So currently, there is support for TCP, UDP, and raw sockets. So the first step, it sets the socket error to econ aborted, which indicates that it's software-caused connection abort. And then it ensures that it sends a reset signal back to the client so that the client can, the client state is, for TCP connection, the client can just terminate the connection, and then it will disconnect the socket state for UDP. So that involves disassociating destination address, port, and then finally cleaning up the socket state altogether. So this is also exposed via netlink. You would, in such cases, users would set the netlink message type to sock destroy. And the expectation here is that users would first query sockets data using the SOCDIAG interface. And then based on the information, the socket information that it receives from that query, it would populate those in the SOCDIAG interface. So this is quite effective, but there are downsides. The netlink infrastructure, the sock destroy infrastructure specifically, it's behind the special config, which is the config inet diag destroy. And this is disabled by default. So this is a common theme, which is the network namespace aware checks that we have here. And additionally, there is no BPF helper available for this sock destroy API as of now. So I send the use cases along with the evaluated approaches on the mailing list. And people see value in having a global socket iterator because it's cumbersome to enter every possible container network namespace on a node. There was a suggestion from Martin on having an all NetNS socket iterator target for TCP and UDP. And as for forceful termination API, we can have a BPF API, or rather, excuse me, a BPF helper. And there was an interesting suggestion for UDP specifically, whether we can connect to some other backends instead of just doing a bot. So thanks a lot for the helpful discussions. So in terms of next steps, I have RFC patches for adding a BPF helper to abort sockets. I've tested this using a new self-test, and I've just added snippet for the helper. So this is what it looks like. The main thing to look at is how it invokes the protocol-specific direct destroy internal API. And I had to extend this, the function signature to accept a third parameter, which is whether to do locking or not. So the iterator, BPF iterator already acquires the socket lock. And so we need not acquire the socket lock again in direct destroy. Just additional note, the self-test mirrors the intended usage of the API, where the self-test attaches two BPF programs. One of them is the C group sock adder program, where it records client socket cookie in BPF map, and these are the clients that are getting connected to servers. And then the second part of the test starts an iterator. The iterator retrieves socket cookie for the socket that is iterating over. And then if it matches with the socket cookie that's recorded in the BPF map, then it goes ahead and invokes this, the new BPF helper. So putting it all together, excuse me. On like load balancing events, BPF iterator can iterate over sockets. It can filter sockets that need to be terminated based on the destination address or socket cookie, matching the socket cookie. And then eventually it can invoke the sock destroy BPF helper. So I think we can optimize this further. We have greater visibility in the data path where the Cilium BPF programs can record client sockets to backend mappings. And we can save these client sockets in a sock hash type map so that when a backend is getting deleted, Cilium need not iterate over all sockets on a node. It can just filter, or rather it can just terminate the filtered client sockets. So this is a summary. Load balancing and policy enforcement use cases may need forceful socket termination. Hopefully some of these use cases wipe with some of the problems that you're trying to solve in your clusters. So the BPF iterator socket target can help us filter sockets, and then the sock destroy BPF helper can help us to terminate sockets so they can deconnect. So I've added some open questions for follow-up. So for example, there was an interesting suggestion to connect to other UDP backends instead of just plain abort. I anticipate we might have to account for locking, similar to the BPF helper changes for sock destroy. And also, I'm not sure if we have conversion helpers to convert from BPF sock adder to like just regular sock adder structure. So something to follow up on. And then there was a note on the mailing list discussion that in future we might have per network namespace socket hash tables. So in this case, it's an open question how we could have like a global iterator. So that's it from my side. Thank you for your time. Are there any questions?
Any questions, feedback? Yep. I'm not sure I understood why you need to iterate all the network namespaces. Is it just a user space mapping problem? Because presumably the application runs in a single one, right? And you know which one it is when you apply the, no?
So what was the last part of the question?
So if you have a policy applied to an application, that application runs in a single network namespace, why do you need to iterate over the entire node?
Right. So Kubernetes pods have their own network namespace. So clients could be running in different network namespaces. So
so you're terminating the client side. All right,
yes.
I missed that part.
Yeah, the backend is already getting deleted. So it's the client side that needs some kind of queue.
Yeah, I think that sock hash or something like that should be super useful. In general, some way to, I don't know, tag sockets so we don't iterate over them is something I guess we need to do, because we also, I think, have some cases where we would like to basically reset the policy of some set of sockets, but iterating through all sockets is expensive. So something we can do here would be great. I don't know what, maybe this map is what it is, or maybe something else, I don't know. But yeah, something to think about, I guess, would be awesome.
Yeah, this is promising. I guess the other option is to store the tag that you mentioned. It could be the socket cookie.
Right, but again, what I need, I basically need, I don't know how many sets of sockets I have, right? I guess if I have a map per set, it might be complicated, but I also need to have, but then I don't need if it's, yeah, I basically need to store some key and a set of sockets, some key and a set of sockets.
Yeah, that's what this optimization is about. There's a question at the back.
One question is, you mentioned you need socket cookie. Why you need it?
You don't necessarily need it. I was just suggesting to him because he mentioned there some kind of data to tag to uniquely identify a socket.
So second question, can you go back to the helper slide you have?
Now the self-test.
Or so instead of helper, so I think it's better to directly expose it, the K function. So the SK port diet destroy. So directly expose this one. I think that may be easier. So for example, instead of taking the socket pointer SK, for UDP, you may directly say struct UDP pointer socket and then expose that K fun specifically for the UDP socket. I think that will be winner instead of wrapping everything here and then you test whether this die destroy is there or not.
Oh, that's an option. Sorry, are you saying that instead of?
So instead of doing all this testing SK to full socket and then SK full socket is now or not, so we can take out all of this and then export the K function, and then the K function will take the UDP socket pointer, and then the verifier should take care of all this type tracking, or SK full sort. All this testing can go away. Yeah, the log. Yeah, the K function, when you export the K function,
But then do you have control of where you can call this K function from? Because it might be like, this might not be callable from everywhere, right?
Yeah, something like what we do in the get sort and set sort, right? So the log socket function will take care of the context.
Okay.
I've at least right now I've followed the usual template where we end up adding a new Bpf helper. This was prior to Alex's talk yesterday. Yeah, I haven't fully grasped the implications of the modern Bpf proposal yet. we could iterate over this on the mailing list.
Yeah, we can take it offline.
Jacob here. So Netlink SockDeck today has like a primitive gem that allows you to filter which sockets you're interested in, as you mentioned. Have you considered extending Netlink so that we can provide a BPF program which decides which sockets we are interested in? Because as opposed to the all NetNS target that you're proposing, perhaps I'm interested just in some network namespaces, not all of them. And by being able to provide a BPF, which is a predicate that Netlink calls to filter out the sockets, that would allow me to implement any condition I want, essentially.
So that sort of becomes the same as BPF iterator in the sense, because the BPF iterator approach has sort of an upper hand because it gives you access to the whole socket structure. So it provides you more flexibility versus in this approach, you have to do two separate queries. One is to query the socket data and then a follow-up query to actually destroy the socket.
Right, it would still be two-step, correct?
Not for the BPF iterator. The BPF iterator, you would end up invoking the BPF helper in the same call.
Okay, I see the advantage there. Another comment I had was about reconnecting the UDP sockets to a different backend. So right now it's only possible to dissolve a connection for sockets that were auto-binded by the network stack. So I'm not sure if you will be able to do it for all connected UDP sockets, because if the user has given you a source port and selected it exactly, you were holding a port log there, and there's nothing we can do about it today from user space, and you can't really reconnect it because you might create a conflict with another socket. Just a thought.
Okay, thanks. Yeah, it's something I need to experiment with. It was a suggestion that came up on the mailing list, and it seems useful, at least for the policy enforcement case, but I don't have the full details.
All right, any last question, comment? Thank you very much. All right, so the next talk is by Mathieu around MPTCP and extending kernel functionality with eBPF and Netlink.
Good. Yeah, so hello everybody. So it is good to be here and speak in front of people. So I'm Mathieu Bart, working in a very small company in Belgium. The company is called Tesseraes. I hope you will be nice with me because I'm not in the company of Matt as initially planned, but Matt is not too far. I mean, yes, he's far because he's more than 7,000 kilometers away, but I think he's connected. Also because he's not present here, so if you have any question, he will be glad to answer instead of me. Anyway. Also, if you have any question about MPCP, Paolo Abeni is also there. No, it's just that he's the most productive MPCP developer for the moment. But also just be careful that it might cost you some beer if you ask him some question. Anyway, about the agenda for today, so of course, going to talk about MPTCP, but not just about MPTCP, but I'm going to introduce MPTCP for those who don't know or don't remember what it is, but don't worry, it will not be too long. I will also quickly list what's new and what has, because that has been requested by, I think, a lot of people, in one person. I will not say who, for you not to blame him, but thank you, Jacob, for the idea. At the end, the goal of this introduction about MPTCP is to understand the key concept needed to follow the rest of the presentation. So MPTCP will be our use case to talk about issues that other network subsystem and probably others can have. So yes, we will talk about extending kernel functionality with a focus on netlink and eBPF, and hopefully have some answer or start discussion about issues. So this will not be a very technical talk. It is late, and I will try to talk more about concept and ideas. I hope that's all right. So MPTCP, what it is. So MPTCP is short for multipass TCP. This is an extension to TCP that breaks the assumption that a connection is linked to a fixed 5 tuple. So in one sentence, it allows to exchange data for a single connection over different paths simultaneously. So you can have more redundancy, more bandwidth, and more many things. Know that you can use multiple paths. A typical use case is represented here with a smartphone having access to 2 different networks. That's very common today, but of course, when TCP was designed in the 70s, that was really not common. When you have access to multiple networks, you might want to use them all at the same time, like they did in South Korea, for example, or you might also want to nicely support handovers, so seamlessly switching between networks when the first symptoms are being detected. So that's what Apple is still doing today with MPTCP to improve the end user experience for mobility use cases. So note that on the wire, we can see TCP packets with some MPTCP options. So each subconnection, so what we call subflow, is a TCP connection. So it has been started with a 3-way handshake, finishing with a FIN exchange or reset, or of course a timeout. But it is important to act like that just to survive on a wild internet with nasty middle boxes that we have today. So a small note also to say that MPTCP is even part of 5G specifications from the 3GPP initiative with the ATSSS module. So yes, it means that if you got a COVID vaccine recently, you might already have 5G in your arm and you're maybe using MPTCP without even noticing. What we have today, so last time we spoke at LPC, it was in 2019. So MPTCP was not even upstream yet. So instead of a what's new, I can present here what's there. So MPTCP is opt-in. If you want it, you can create a dedicated socket with IP proto MPTCP instead of TCP. Then you use it like you would do with TCP. That's it. So thanks to that, it is also easily possible to force applications to create an MPTCP socket instead of a TCP one with a classic LD preload. That's what MPTCP eyes tool is designed for. The goal here is not to go into details about the MPTCP core implementation, but it is important to note that MPTCP doesn't affect TCP performances, and only a very few modifications have been done in TCP code thanks to TCP upper layer protocol to manage the different subflows. So it might be interesting to note that MPTCP extends the SKB structure only when needed, thanks to the SKB extension infrastructure put in place by Florian Westphal at the beginning of the project. For any technical details about the implementation, I do recommend you to watch Paolo's talk he gave at DevConf, if you remember. It was in Brno, and also Florian's presentation about SKB extension from a previous NetDev. So I'm coming back to the slide with the third point. Most of the protocol features have already been implemented. So it is possible to have multiple subflows, announce addresses and priority from one peer to another. It can also support what we call fast close, so it's the equivalent of TCP reset, but for the whole MPTCP connection. We can also explain reset and many other things. Most common socket options from upper protocol are supported. So the complexity is to know what to do when there are multiple subflows, especially if they are created later on during the connection. Typically, socket option values are propagated to all subflows, even the subflows that are not created when the set socket syscall was called. Of course, this needs to be checked case by case. So some options don't make sense for MPTCP, like if they are specific to other protocols. Some cannot work with MPTCP, like TCP MD5's option, there are not enough space. Some only affect the MPTCP socket and not the subflow, like poll-related ones. Some also are only for the first subflow, like TFO, and there are other cases, of course. Still, some socket options deserve more love, and less common ones still need to be implemented. So if you don't know what to do next weekend, you can always look at that. But the two last points here, it is possible to get info from different areas, like MIP counters, INET diag interface, and also MPTCP info. That's a socket option that is similar to TCP info. There are also two path manager and one packet scheduler, but I will come back on that later. So what we will have, here is a short list of what we can expect in the coming versions. So we would like to have more control from user space to support more use cases and more adapted control. TCP fast open support also for MPTCP should come soon. More socket options, maybe TCP congestion control taking into account multiple paths, who knows? I know that this was a hot topic a few years ago, but probably most use cases don't need that, and hopefully even more. So that's it for the introduction for MPTCP. It's time to talk about extensions. So we start here by looking at extending kernel functionality using netlink for the communication between the user space and the kernel space. I already mentioned that MPTCP can expose information to the INET diag interface. This is of course done via netlink, but I don't think it is interesting to present that. It's rather common, and already mentioned that today. Instead, let's look at two different components in the MPTCP infrastructure that are a bit particular and have values to be controlled from user space. So the first component to extend is the path manager. This component is in charge of creating additional subflows, so what we call paths, removing them if needed, announcing addresses, priority, and others. You need it on both ends, but to serve different purposes. For example, it's traditionally the clients who create new paths. This is in fact an excellent use case for the netlink protocol. Here within MPTCP Path Manager, we have two different usages. In fact, we even have what we call two different path managers. We have a classical way where we can change global settings to define some parameters per net namespace. This can be done via IP route to tool, for example, like median network settings. Here you would use IP MPTCP to set IP addresses, endpoints, and limits. Note that the latest version of Network Manager, so version 1.40, I think, has also support for some of these settings. So it is easier today to get MPTCP properly configured. More interestingly, the kernel can also notify the user space via netlink when MPTCP connections are being created, established, and closed. So we can also have the same events for each of flows, and also when some signals are received, like the other peer announcing or removing an address, etc. On the user space side, a tool like MPTCPD can listen to these different events and send some commands to create new subflows or announce addresses. So in short, the user space can control path manager and make decisions per connection. So let's look at the pros and cons. So on the one hand, netlink is well known, well tested, clear, even if this can be improved. So imagine maybe having a nice description in YAML, for example. It is also complete and stable. So it has been existed for a long time. So I probably looked at the same Wikipedia page as the one Jacob mentioned this morning. So yes, it has been created in the 90s. Do you know that at that time, Internet Explorer 6 didn't even exist? Quite a long time ago. Only one small tweak was needed. The goal was to optionally restrict generic netlink multicast event group access for subscriber with capnet admin, quite specific. But in other words, for security reasons, we don't want everybody to get access to the token. The token is used as an identifier in the different events, but the token is also used to create new subflows. So this information could be used to hijack existing connection, for example. That's why we want to hide it and to restrict it to some users. On the other hand, this protocol is not designed to have kernel to user space request. What I call a request is to have the kernel waiting for some feedback from user space to continue. So for example, when a new subflow request is received by a server, the kernel cannot send a message via netlink to user space, take a break, waiting for the user space to reply if the request can or cannot be accepted. So that's not something that we can have. But the kernel can send events to subscriber. The user space can request a modification, but the kernel cannot really block. It could be possible to share some rules to the kernel or add packets in a waiting queue like it is done with netfilter, but it feels less natural somehow, and we want to avoid implementing another netfilter-like architecture in MPTCP. Another thing is when there are what we call too many events. So imagine a busy server dealing with thousands of connection requests per second using in parallel multiple network queue and multiple workers to deal with that. But on the other hand, there is only one netlink socket dealing with all the different events. So imagine that all the events we can have, especially for short connection. So like we have, hello, there is a new connection request, and then the connection is established now. Oh wait, there is a new subflow, and another one. Oh no, in fact, this subflow is closed. No, in fact, sorry, all the connection is closed. So what I just want to say is that you can have plenty of messages, and each time some data are provided, like the token, IP addresses, port, source and destination. So you need all of that to make proper decision, but then the buffer linked to this socket can be quickly filled if the user space cannot process all of them. And that's when you start losing events. So of course you can always tweak the buffer, but then it certainly means that there are some latency between when the event is emitted and when it is processed by the user space. You can probably start looking at having multiple channels somehow, but that doesn't feel natural as well. So you probably need to accept the limitation, which maybe is not a real limitation because this kind of server probably doesn't need to have a user space path manager and do that per connection. It is probably enough to configure the global settings, so maybe that's not a real use case, and then maybe not a limitation, and Netlink is perfect for this job. Anyway, in this example, there are a few events per MPTP connection, but what if you want to make decision per packet that needs to be queued on the best path? We can have a look at that. And Bpf. Bpf is the solution to all our problem. I heard that once, I think, or in fact, plenty of times. So like what you can hear about 5G, but I don't think that there is Bpf causing COVID vaccine, but that's another topic. Anyway, back to the presentation with the last part, Bpf extension. There is another component within MPTP that makes sense to extend, to be adapted to different use cases. This component is in charge of deciding on which path, which available path, and the next packets will be sent to. So it can also decide to retransmit one packet to another path if needed, and that's what we call a reinjection. Of course, extending this cannot be done using Netlink. A scheduling decision need to be done per packet, so it's hard to imagine the overhead of sending a notification to user space, waking it up, having context switches, etc. And that would be for each individual MPTP packet, data and ACK included. Netlink or any other involvement of user space is just too much overhead. Some might say that we could have the user space providing some policy in advance, like with NetFilter, like I said before, but packet scheduling job needs to take into account too many parameters to have good results. So for example, some links might be more costly to use, like redundancy also might be needed in some cases. Some paths might be congested, maybe with buffer bloat. The path might appear to be stalled, etc. So you can even have tricky situations, like the local buffers might not be big enough to support the combined BDP of each path, but then what to do? Which paths not to fully use in this case? So it makes sense to move all this complexity out of the kernel code and focus on generic use cases inside the kernel. So we started to look at the different possibilities to allow the user space to control the packet scheduler. First, it would be silly these days not to consider Bpf for this job. I guess if we didn't, I could not give this presentation today. Here it is. But more seriously, when we look at other modular components being involved in the packet scheduling in the network stack, an obvious one that comes to mind is TCP congestion control. The algorithm is deeply integrated in TCP code. There are callbacks to update some info when packets are received. We cannot really have the kernel waking up a user space application to delegate this specific part. I guess that if we want to delegate that to an application, we would need to delegate much more than just the connection control part, but then we are talking about a different network stack implementation, like with DPDK or its VPP, for example. Back to the TCP/CC in the Linux kernel. Since 2005, the TCP congestion control algorithms are pluggable. So before there were a bunch of conditions in TCP input file with different functions dedicated to different algorithms. So the situation has improved, and each algo is now implemented in a different kernel modules. It is nice. Each algo is isolated. Adding new one doesn't impact others. Multiple ones can also be used on the system for different connections, of course. Of course, it is less good when we think about Spectre and all of that, but there are solutions for that, and I don't think we need to focus on that part now. Yesterday, Martin talked about what happened in 2020. So he added the possibility to create new TCP/CC with Bpf, thanks to a new Bpf struct opt infrastructure. And Cubic and DCTCP algo have been re-implemented to show the feasibility, and the code is similar to the existing kernel module. So that really looks great. That can work for use case in MPTCP with the packet scheduler. So what's again BPF to the rescue? So we are not BPF experts, but one of us, Liang Tang, sorry for the pronunciation, started to look at doing the same with MPTCP packet scheduler. And there are even RFC patches available in R3. It is using the BPF structure infrastructure, and we can declare new MPTCP packet scheduler in BPF like we would do if we wanted to create new packet scheduler in a kernel module. So we would probably engage, we would have probably engaged discussion with BPF maintainer earlier, but before asking if we are going into the right direction, I should probably add a few more things. Before working on that, we had a single packet scheduler, so not pluggable via kernel modules or something else. The isolation was already a bit there, but still the kernel module aspect was not. So anyway, we knew that if we wanted to support multiple packet schedulers, we had to do this isolation work. So that's all right, in fact. But introducing new kernel modules seems a bit old school, but somehow it is required for BPF structure, so let's do that. Also, what bothers us more is that apart from TCP congestion control algorithm, it looks like there are no other use of BPF struct ops. So what I also want to say is that for the TCP congestion control part, the kernel module infrastructure was already there, and adding BPF struct ops seems the right way to do. So it is in continuity with what was already there. So it was making sense, but what about us? Is BPF struct ops what we need, or maybe we are missing something? We can come back to that later. But if we are going to the right direction, we don't have a bunch of questions. So initially, we wanted to avoid maintaining different kernel modules to avoid the same issues as what is visible with TCP/CC side. So kernel module don't allow the fast turnaround for testing new algorithm in production. Plus, there is a maintainability question if there are many modules in the kernel. But here we can also say, fine, we just have to implement one module specific to BPF, and we maintain the generic one. So seems all right. But opening up more flexibility has, of course, impact. Packet schedulers implemented in BPF will have a performance impact if we compare it to the default packet scheduler in the kernel due to the extra layer we are adding and indirect calls, but that's for good reasons, and it is then acceptable. And yeah, again, we are not really expert in BPF, and maybe we should have asked the question elsewhere, but and the other thing is that I don't feel very comfortable because the work was mainly done by Gillian and Matt. But here are the first question. We quickly realized that if there is a possibility to run multiple packet schedulers, then we might need to adapt the API to allow more behavior. We still have plenty of questions related to the API for the packet scheduler, but that's internal to MPTCP. But how is the API considered? I mean, when we talk about kernel modules, I guess it is better not to break the internal API. But if it is needed, we can break it. Here, if the API is somehow exposed to user space via BPF, do we have not to break it and maintain like different API version? Like, so same question for BPF helpers we are introducing. Can we, for example, change the signature? And I guess this question has been replied by Alexei during his talk yesterday, but I guess BPS follow the kernel, so that we can have breakages, and I guess there are solutions to minimize the impact. I guess it's fine. Also, then I have another question. How to deal with atomic operations? Like there are no read ones or write ones, for example, in BPF, if I'm not mistaken. And I'm not an expert, but the workaround that we found is to add BPF helpers with new BPF kfunc to deal with all these atomic operations. So we don't know if it's the correct way.
But I mean, did you look at read runs, write runs by adapting the macros from the kernel and using them in your BPF program? Does it not work for you, or?
It was not working when Galen was looking at it, but we maybe missed something, or maybe
we have Young Hong here, so you can answer. Young Hong. Okay. No? The question is, apparently read ones, write ones don't work if you use them in your BPF C code.
Okay.
Yeah. What we need for the package scheduler is to use, for example, read ones and write ones. But when we try in BPF, or at least maybe at that time it was not working, so we don't know if it was.
We do have atomic instructions available with probably LLVM14. We have a set of atomic add, subtraction, and also multiplication and shift, and also compare and exchange. To be able to satisfy your need.
Yeah, I'm not sure why you need read ones and write ones in the BPF program, because it's already there in the spec, the BPF spec. There's no load and store tiering with the BPF.
Okay. Yeah. Because when also looking at Paolo for the scheduling part.
I was saying that actually I did not follow closely the FC patches, so I have a question regarding why the read-ons is required, what write-ons is required.
No, indeed, it might not be needed. Yeah, maybe what was also done is like they look at the current implementation we have on the scheduler part, but maybe they overlooked at something.
From a logical point of view, I think that the scheduler may need to access some information from the subflows while not holding not adding the subflows lock. And that will be C code. I will use read-ons there.
And I don't know if we need also to look at what's happening on the other subflow linked to the same connection. Some operation. But okay, if there are solutions, and even better if we don't need it, that's really great. Yeah, so then I can look at the next question we have. There are also some security concerns. Maybe that's not really an issue, but for example, like a kernel module, the Bpf module will have access to the connection token. So it is useful because it is an identifier, but it can also be used to create new subflows from other IPs. So we are opening up access to more info via Bpf. And we were just wondering if there are security guidelines somewhere, or if we don't have to worry because it's like kernel module, they have access to everything. We trust them, and that's fine. Probably. That's something also that we will put in cover letters when we will send them to BPF maintainers, because something that might be important to look at. And because I see that I'm a bit late, I will conclude. So we hope that MPTCP will be adapted to everyone's need. We hope to have a BPF packet scheduler soon, and even maybe a path manager, we never know. But yeah, if you have any other questions, remember that Paolo is still there.
Any last question or comments before Paolo runs out? No? Okay, thank you very much.
Thank you.
All right, so the next presentation is by Brian on Perceive hash table traversal. So take it away, Brian.
Hello, hi everyone. Just confirming, can everybody hear me well?
We can hear you well, yeah.
Okay, good. Okay, so my name is Brian Vasquez. I'm a software engineer at Google, and today I'll present a measurement study that it was conducted by Sagarika, which was an intern this summer, and with help from some coworkers. And yeah, I'll present basically why traversing a Perceive hash table is expensive. So the agenda for today, I'll try to explain what is the motivation, what's the measurement that we did, what experiments were conducted, and what is our conclusion for this work. So let's start by the motivation. Traversing a Bpf Perceive is expensive. So before going to that, I want to introduce you or give you a little bit of the context that we are facing. So basically at Google, we have a daemon that is running on every host, and it's tracking every flow within the host, and we use it to shape traffic. Some of the information that we collect is stored in a Bpf Perceive hash table, and because it's tracking like every flow in the host, the table can be large as 40K entries. This flow stat table is dumped in user space for data processing every 5 seconds. So basically, it's an action that we are repeating over and over again. So yeah, it's expensive. And another motivation for this work was some past pitfall. So it's basically not the first time that we realized that traversing a hash table is expensive. So yeah, this is the patch that it was implemented in the past, which it was basically to batch the operations of get next key and get element, because at that time that was where we were seeing or observing in our profiling tools. So yeah, we implemented batch ops. It was great for a couple of months, I guess. It turns out it saved some amount of the cycle, but we didn't look in detail back then. So basically, we only saved the syscall overhead, but nothing more. So the motivation, again, is basically once we switch to the batch functions, like basically the get next key and lookup element disappear from our profiling tool, but we started seeing like Bpf map lookup batch. And to give you an idea, basically when the table is full, like the processing time of this table, it's above half a second. And again, we did this every 5 seconds, so it's a bit expensive. So now this time, like we actually spent a little bit more time understanding what was going on. So where is the cost? So our profiling tool like shows that the work that it was done in user space, basically it was only 30%, which it was just aggregating the data per CPU and reporting the data. But from the entire cost, 70% was spent in the map lookup batch function, And surprisingly, we started seeing that most than half percent of the cost was in the Bpf long main copy. So that's why we went and we try to understand, like, is really Bpf long main copy suboptimal? So basically, we look at the code and it's not really, like, the code is fairly simple. So why is expensive? Like, the data that we were storing doesn't even require, like, to iterate over this loop many times. So it was surprising. So why it is expensive? Again, like, we went through all the profiling tools that we have. So it turns out that from the batch operations that we are doing, almost the entire time is spent in cache misses when reading from the per CPU map value. So it's actually not copying data what is expensive, but it's that the source data that we want to copy is not there. So if you can look here, like, it's a little bit small, but basically 87% of the cost is spent in cache misses in this function. So again, like, we wanted to get more detail of how much, or to get an idea of how expensive was this. So we used K-Stats, which is a great tool that was developed by Luigi. So this tool basically allows to annotate certain parts of the code and to record, like, the time that it takes to do the mem Bpf long copy. And basically, we record that into this tool that will report a histogram of how much it's taking to iterate every single entry. So I'm showing here, like, the code that is needed to get the stats. So it's pretty simple. And there are, like, two versions of how we recorded the stats, because basically K-Stats has a little bit of overhead. So we were concerned about maybe this getting us numbers that were affected by the measurement tool. So yeah, in one of them, like, the annotation is inside. So trying to, so basically we are using K-Stats a little bit more, and the previous one, the annotation is outside, and then we divide by the number of elements that we traverse. So the results that we got, on the left side is the first method that I showed. So yeah, basically I'm showing here, like, two different platforms. One of them is IMD-ROM, which is the Zen2 chip. This platform has a 256 cores, which is a lot. That's also, like, why we picked this platform, to show that the per CPU data structure is a little bit costly. And we also show an Intel Skylake with 100 cores. So if we look at the percentiles, we can see that basically on the AMD platform, like, each entry, like, just to copy just to put the data in the buffer, like, it takes about 15 microseconds, but the tail is 25 microseconds. And apparently the Intel Skylake platform is already, like, good enough. Like, we can see that the 50 percentile is just about 5 microseconds, but tail can be large. But also, like, it's important to know that the distribution is pretty flat. So basically mean and average are going to be really close. And the next table is basically the same experiment, where we measured the cycles, where we measure, basically, instead of the internal instrumentation, we put the instrumentation out of the loop. So we can see that actually, like, the tail got lower. But it still gives you an idea of how much it costs to traverse an entry, which it's quite expensive, especially if you have a large table. So basically, we conducted some results. But before conducting results, I want to maybe explain a little bit how this data structure is laid out. So we understand why it was really hard, like, to find a way to iterate it and maybe do some trick or try to exploit some data locality. So basically, this hash table is implemented like regular hash tables. Like, we have a list of buckets. Each bucket will be a linked list. But also we have the elements. The elements are allocated separately, so we have some pre-allocation going on. But when we have a per CPU data structure, it's important to know that we allocate the structure, we reserve a space for the key, but the value is not there. Actually, the value is a pointer that will point to a per CPU data, which ends up being an array. And basically, with the offset of the CPU, you will have a pointer that is accessing a different memory area. So basically, the value, like when it's per CPU, this data won't be contiguous. And also because when we are adding entries to the buckets in the hash table, like this data also won't be contiguous. So it could be that this entry is in this bucket, but this entry will be in this bucket. So basically, the memory is so sparse that it's really hard, like, to find a different strategy to iterate over the data structure. So basically, the only option that we had, or that it was good in terms of trade-off, it was a prefetch to the rescue. So yeah, like we know that it was some cache misses. So the only thing that we did is to try to prefetch the per CPU data in advance. And we experimented with different values, because also it seems that if we look at the batch function, like there's not much work to do. It's only copying the data and then it's done. And this operation is super fast. So to really exploit prefetch here, like we needed to prefetch some different entries in advance. Like we cannot prefetch the one that we are going to copy. So basically that was part of the experiment that we did. So yeah, here we have the results where at least on AMD, it seems that prefetching 10 entries in advance reduces the average of a single entry when the table is full. I said at least 50%, but it's actually a lot. Like unfortunately, the numbers are a little bit unreadable. But basically, before I said that the average was about 15 microseconds. So when we are at a prefetch 10 entries in advance on the AMD platform, we can basically got almost to 5 microseconds or 5,000 nanoseconds. So we did this experiment, and we also tried to basically see like how it would be when the table is not super full. So here, the blue line, we experimented with 2,500 entries, and we also played with prefetch. But on AMD, it seems that prefetching, it does help. I guess that it's architecture dependent. On the other hand, the Intel Skylake didn't show like good results on prefetching. Like actually, it was adding cost, which means that maybe on Intel, because this platform has less cores, and also the memory hierarchy is a little bit different in the hardware architecture, so it didn't show any benefit. And it actually at some point it does hurt. So you can see how the prefetching actually makes the results way worse than they were before. So the conclusion, and maybe ask for some feedback to the community. Our conclusion is that traversing a per CPU data structure will become more expensive as platforms grow in CPU count, which is a current trend. The current hash table implementation, it's a lot of pointer chasing. The memory is, it is contiguous allocation, but the way we assign these elements to the buckets basically make it non-contiguous, and also the per CPU data makes it non-contiguous. So doesn't allow us to exploit any traversal or any trick at all. So alternatives, we did look into alternatives. So actually we are planning to switch to Bpf Ether to save on aggregation. But again, like from the analysis that we did, it seems that copying the data is not what it is expensive, but it's reading the data, the source data that we want to copy. So if we look at Bpf Ether, actually suffers some cache misses as well when we are traversing per CPU elements. So I put some code of the Bpf Ether to basically show that basically we traverse the same way that the batch traverse in entries, and we have the same mem copy, and the source won't be there as well. So this will be also cache misses. So yeah, like maybe we can save 20% of CPU cycles when we switch to Bpf Ether, but not more. But apparently, if we enable prefetch, which was a quick trick on certain platforms, like we can save 66% of the total cost. So another alternative that we didn't have enough time to explore is maybe implement another data structure. Yeah, we understand that per CPU data structures are good because they allow you to quickly access quickly modify the data. It doesn't have logs, but again, like as CPU count grows in platforms, it will be harder and harder, like to aggregate the data and to access and read the source. So maybe, I don't know, like a hash table that instead of per CPU, it's per networking queue. And yes, this is specifically for networking usage. And yeah, maybe, I don't know, like I haven't looked in the code into that detail, but maybe the TCP Bpf front with the queue lock help. So maybe we don't even need to care about like trying to coordinate how we write to this data structure. So maybe it could be used in our favor. And yeah, I guess that that's what I wanted to present. So any questions, comments?
Questions, comments? I'll ask the obvious question if we can add the prefetch instructions to the ISI. And you can tell me why not.
To the what? Sorry, I couldn't hear.
To the Bpf ISI, right? The prefetch is an instruction. You can just add it and then prefetch it in your Bpf iterator.
Yeah. So that's the point. Like we already sent some patches. It was more like an RFC because we were experimenting.
I think Jakob means like you can actually in the Bpf bytecode you have an instruction to prefetch, right, and then the verifier expands it.
Yeah, that would be a good idea as well. Like the point here is that maybe it makes sense, but for certain platforms, not all of them. So we might need maybe a sysctl tool or something that we could enable it when we know that this platform will suffer because the architecture is different.
The loop doing the for each possible CPU code is a C helper.
Yeah.
So
It might help in the we can talk offline, I guess. Yeah, that's a good idea, unless somebody.
So another idea I had actually a long time ago was to no longer use per CPU data, but per node or per level 3 setup. For example, on AMD, on ROM, we have 8 level 3 cache per socket, so that will be restricted to 16 value instead of 256. And that maybe that's good enough for our use case.
There's actually different prefetch operations. So it seems like your problem is because it's on the CPU that has another memory hierarchy, but the CPUs actually support not prefetching into level 1 cache, but they have instructions for prefetching into level 2 and level 3 cache. And that seems like actually to be the problem here, right? Because you have to walk the things for all the different CPUs. So if you prefetch, you could play with prefetching to L2 or L3 and see if there's a benefit from that, because we want to bring it into the other hierarchy.
Yeah, it can also be useful if we actually go to implementing the packet classifications in Bpf. So we would have to walk a list inside the classifier, and then we would definitely want to prefetch the next element, right? So we will need the expression in Bpf to do it.
Yeah, those are great ideas.
Anyone else?
Can you elaborate on the network queue data structure that you?
So it's similar to what Eric was describing, but instead of using the cache hierarchy or the level of cache, basically it would be like instead of on the AMD platform we have 256 cores, right? So maybe we could have a hash table where we can specify like the number of data points that we want or logs, which could be tied to the networking queues, for example. So in that case, maybe in the TCP, in the TC-Bpf filter, when we are executing these programs, because, and I don't know, like correct me if I'm wrong, but I think that we already have the queue log in there held. So maybe also we don't need another log to implement this data structure, because the Bpf map will be updated at the queue level. So instead of updating 256 entries, like we will update it only the queues. And for example, in these systems, we've seen that usually 16 to 32 queues are good enough to achieve the performance that we want. So basically, this data structure will become smaller. Will be like 16 or 32 data points instead of 256.
Yeah, that makes sense to me as well. Okay, anyone else? Yeah, thank you very much. Cool. That concludes today's sessions. So yeah, see you all again tomorrow. Thanks.